All right, welcome everyone to the Climate Variability and Change Working Group. Just a few logistics before we start. So for the speakers, you have 10-minute slots, so try and finish up at 7 minutes, and I or Aisha will give you a wave when you're at the 7-minute mark. We will pay attention to the Slido, so for the people online, if you have questions, please put them there. You need to go to the Slido and then to the center bay of center green. So I'll start our CVCWG update, and I'll hand it over to Aishu in a minute to go through some. All right, so if you're new or you need a reminder, just want to point you towards the Climate Variability and Change Working Group website. This is, I think, a pretty useful resource because we have a list of all the simulations that the working group has produced. And if you go into any one of these, you can find information on how to get the data, whether that be on the CESM machines or through the web access. So I encourage you to go and look there and see what simulations are available. There's also been work by working group members to produce an archive of data, not just from CSM, but from other models. So this Multimodel Large Ensemble Archive version 2, so this builds on work that was done by Flavio Lehner with a few years ago, and expands an archive of kind of curated data from large ensembles. So now there's 18 models. They're all kind of regridded onto a common grid, so they'll be much easier for you to use, and 15 2D variables available. And Adam has run all of these large ensembles through the Climate Variability Diagnostics package, and if you go to this website, you can see both the plots from the Climate Variability Diagnostics package, and you can get the information on how to get at the data. So we have a few different simulations in the works, nothing really new for you to look at this point, but things that will be coming, so we'll go through those. So one is the pencil model. So we've been talking about this for quite a while. This is an ocean model within the ocean model hierarchy. So it's kind of between the slab ocean and then the full 3D ocean. So with the slab ocean, you just kind of have a thermodynamic mixed layer. You basically just have the kind of heat capacity influences of having a layer of water there at the surface. And the pencil model is a step up in complexity. It's basically a single column ocean model at every grid point. So you have the mixed layer physics represented. So one of the things you need to do with the slab ocean is prescribe the mixed layer depth. And in this pencil model, you don't have to do that. It's prognostic. And then there are terms that make the large-scale circulation in the ocean be realistic, and there's also a bit of restoring of salinity and upper-level velocities to keep it stable. And so this is a project that's been led by Young-Oh and Gokhan, and it's been in the works for a long time, but it is now running, and Young-Oh has now completed 2 500-year-long pre-industrial controls with this pencil model. They plan to release the data soon, and they plan to also make the pencil model available within CSM2. It has to be within CSM2 because it's using POP, not MOM, which is the ocean model within CSM3. And so if you missed it yesterday, there was a poster by Jung-Soo Shin kind of displaying how this model behaves, and here's a figure from that poster where you can see that this pencil model gives you pretty realistic variations in mixed layer depth compared to the fully coupled model, except on the equator where Ekman transport becomes an important part, and I think they're looking into ways of getting that in there. So if you missed the poster, maybe you can see it on the online poster gallery. There's also work going on within the working group on regionally refined configurations. I think this has been a bit delayed just by a lack of capacity for the people that are leading it, but Brian has been working on this regionally refined tropical belt simulation, and I and others have been working on this regionally refined North Atlantic simulation. So just a couple of teasers from these experiments, and hopefully we'll have more details in the coming year or so, but here's an example of the precipitation distribution from Brian in this tropical belt configuration over West Africa, where you can see that the high-res configuration does much better at representing the tails of the precipitation distribution than the low-res. And then in the North Atlantic, the motivation of this experiment was really to look at whether the nature of ocean-atmosphere coupling changes at higher resolution. And here's just a regression of zonal wind onto the AMV index. So basically when you have the positive AMV in the observations, that's accompanied by an equatorward shifting of the jet. This is what the low-res model does. This is an error that, oh yeah, no, they're both CSM2. That's the 1 degree model. And then this is the regionally refined Atlantic. So there are definitely some differences there when you go to this high resolution, and I'm hoping that we can dig into that in more detail in the coming year. There's been work underway to use perturbed parameter ensembles to tune this CAM, including this new machine learning-based warm rain microphysics scheme. So this is work from Adisu and Brian. And an example here is just showing this is the monthly precipitation distribution. And you can see that there are improvements in this machine learning-based parameterization compared to the original physics-based one that's in the model. So that's ongoing work within the working group. Okay, we have plans for a new ensemble, a single forcing ensemble of CSM2, but using CMIP5 aerosol forcing. I think there's been quite a lot of work that has shown that differences between CMIP5 and CMIP6 aerosol forcings have quite an impact on the historical evolution. And what we wanted to do here is not change our baseline, so use CMIP6 pre-industrial control aerosols and add on the anomalies from CMIP5. So it's not exactly CMIP5 emissions, but it's the time evolution of CMIP5 within a CMIP6 baseline. So this would all be within CSM2. That presented some challenges because at certain points in time the emissions can go negative, and so that's why we haven't started these runs yet. It's taken a bit of time to figure out the emissions. We've decided to kind of take the approach of taking any negatives that happen and kind of pass them out to adjacent grid points. So if anyone has any thoughts on whether that's a reasonable approach or not, I'd be glad to hear before we start these runs. But hopefully we can get these going soon. And I think it would be interesting to do this with CMIP7 emissions as well, as a kind of first look at how the differences in the aerosol emissions change what's happening in the model. So I'm going to hand it over to Aishu now for the last few slides.
All right, first is the TBI experiment. That's a clever quantity experiment. Currently, there's 7 groups participate and using 6 model groups. And most of the model groups have finished the tier 1 experiment. And for tier 2 experiment, CSM2 has finished by a Chinese group. And right now, there's a protocol paper has published by in GMP recently. So if you want know more details about the TBI experiment, you can look at that paper. And if you want to analyze the data, just contact me. And the other experiment and program is funded in Europe, is focused on tipping point model intercomparison, which is focused, the research is on tipping point, abrupt change, and thresholds. Right now, there's 6 major domains or research focus. NCAR is actively participating in the TipMap ESM, TipMap Ocean, and TipMap Biosphere. And below those is some experimental design. And if you are interested in this kind of experiment, you can contact me. If you want to run some simulation using CSM2, you can also contact me. And the protocol paper is going to publish for each of these domains. And some details you can look at from the website. And yeah, just anything you want to know, just ask me.
All right, yeah, so we don't have a huge amount of time here for discussion, so I just want to encourage you, if you want to kind of get involved in plans for future simulations for the working group, I'd encourage you to join the winter working group meeting where we will have a lot more time to discuss things. Our kind of near-term plans are once CSM3 is available, we start running the various kind of baseline simulations that we do with the working group. That's kind of the immediate plan. Also, if you're not already on the mailing list for CVCWG, please join it, and then you can hear about new experiments or meetings as they happen. So with that, I think we're at the 10-minute mark, so we'll get started with the presentations. And our first speaker is Keja or Melody Liu on land atmosphere feedbacks on heat waves. I'll give you a wave when you're at 7 minutes. Yeah, so it's just this big one. And if you want to use a pointer, just hold that down at the screen, and eventually it shows up.
Good morning, and thank you for having me here. Today, I will going to talk about the importance of how land and atmosphere interactions modulate the surface temperature variance. So here's a brief overview of the presentation. It is well known that climate models are biased in capturing the mid-latitude land surface temperature variance. And in this work, we will demonstrate that the land-atmosphere feedbacks are dominant. And we also found that the atmospheric circulations in synoptic scales aren't as important as previously thought. And we further developed a theoretical framework trying to explain the land-atmosphere feedbacks using the parameters. And then we found that these parameters are actually naturally embedded following the traditional definition of the mixing length. So to start with, we know that the global warming affects the temperature distribution not just by shifting the mean. The changes in the temperature variance will affect how the future warm and cold extreme events will occur. However, the state-of-the-art climate models are having troubles in capturing both the magnitude and the spatial patterns of the temperature variance. And these problems is more severe in the mid-latitude land during winter. So for example, Simpson et al. 2022 paper found that the temperature variance in CESM1 AMIP simulations are way too large compared to the ERA5. And the temperature variance is largely reduced in the preceding CSM versions. And that's largely because the differences between the two different generations of land model. And the newer land model simulates a more conductive snow layers, which will allow a higher surface energy flux exchanges that acts to damp the temperature variabilities. However, we also know that the synoptic scales of weather circulations are quite important. For example, the regional cold spell events are tightly coupled by the upper troposphere blocking events. So there are a few questions that we want to address. First of all, so how important is the synoptic scale atmospheric circulations in addressing these errors? And second, what's the relative role of the interactions between the land and atmosphere? So to address these questions, we run 4 different numerical simulations using CSM2 AMIP type of simulation. To address the first question, we notch the global wind 6 hourly to ERA5 from the bottom to the top of the atmosphere, and we call these experiments as not UV. By comparing the control experiment with not UV, we can determine the relative importance of the circulation. To address the second problems, on top of the wind nodging, we replace the land model from the current version to the preceding version, CLM4, which is employed in CSM1. And we call this simulation as not UV CLM4. We also run another sensitivity experiments without nudging, but replace the land model with the preceding version. So by comparing these 3 sensitive experiments to the control, we can explore the relative contributions from both atmosphere circulations as well as from the land. And here are the results. So in general, we can see that the CSM2 control simulations are weaker compared to the ERA5. And if we look at the changes due to the wind nodgings, we see limited improvement in terms of the temperature variance in the winter. However, if we look at the 2 sensitive experiments where the lands are involved, we do see a significant increase in terms of the temperature variance when the older land model are employed. And these results are broadly consistent with Simpson et al. And so now we sort of know that to address the error questions, that the importance of the synoptic scale atmospheric circulations aren't that important. So from the previous slides, we kind of sense an importance from the processes due to land. But then we wanted to ask, can we derive a more theoretical framework to quantify the role of the land? So here we will start from the tendency equation of the near surface air temperature. From there, we will be able to derive a scaling framework that has a structure shown here. So specifically, the denominators are the parameters that control the feedback strengths of the land atmosphere. And we also have the eddy, heat, turbulent heat flux, as well as the temperature gradient acts to fuel the temperature variance. And then we will be comparing our framework to the traditional eddy mixing lengths and to see how they connect it with each other. So now let's see how the framework explains our experiments results. Here is also a derivation of the framework. So we start from the simple tendency equations, and then we derive a budget for the temperature variance. And here we perform a variety of parameterizations. Specifically, we parameterize all the dry energy flux using a sensitivity parameter alpha d, and then we parameterize all the terms that are related to latent heat flux with alpha L. Alpha L depends on the soil moisture, evaporative resistance, as well as the background saturated humidity. And then we can derive this following scaling equations. And if you are familiar with the mixing length framework, that we can see that mixing length is naturally embedded with the eddy diffusivity as well as these parameters. And now, so let's first look at the relative partitioning between the mixing length and background temperature gradient. So here we use the smooth potential temperature to calculate the background temperature gradient so that we can minimize the influence from topography. And then we can calculate fractional changes of these equations. So here are the results. The first row shows the fractional changes in temperature variance. And the second row is the contributions from the background temperature gradient that you can see that nothing looks quite similar between the second row and third row. And the third row is the contributions from the mixing length square. And then you can see that the increases in the temperature variance we see in the first row are most likely coming from the contributions from the mixing length. And then we wanted to know what contribute to the patterns of what we see in the mixing length fractional changes. And if our theoretical framework is correct, then the mixing length is a function of both eddy diffusivity as well as these parameters that control the land atmosphere feedback. Here again, we can do the fractional changes with these equations and sort of trying to decompose mixing length into the part that related to eddy diffusivity, as well as the part that encaptures all the feedback strands. And here again, we have the fractional changes in the mixing length square. And then we can evaluate the left hand of these equations separately here, which is shown in the second row. So the similarity between the second and first rows tells you that the changes in the eddy diffusivity is kind of negligible here. And we can also calculate the parameters independently and evaluate the right-hand side of this equation, which are showing here in the third row. So again, you can see that all three rows look quite similar. So here it tells you two informations. First, that the mixing length is constrained by the land atmosphere feedback. And second, that our framework is quite correct. And lastly, here is a total scaling relationship of the temperature variance. Again, perform fractional changes that we can calculate all each different terms. Here again, we already see the contributions from the interactions between the land atmosphere, as well as the fractional changes in the temperature variance. And the last term is the summation between eddy heat flux as well as the background temperature gradient, as we can see that most of the temperature changes are purely coming from the contributions of the land atmospheric feedback parameters. So a few quick summaries here that we show that correcting the synoptic circulation bias does not address the model bias in terms of temperature variance. And then we derive a theoretical framework where we can partition the mixing length into the contributions of the land atmosphere feedback. And eventually we know that accurately representing processes involving the land are quite important for the future projections of temperature variance, as a result, the extreme weather events. And I will stop here and taking questions.
Any questions for Melody, either on the Slido or in the room? I'm wondering, so our interpretation was that snow conductivity was just through upward fluxes was damping the temperature variability. Is your interpretation that that is just kind of damping the extent to which circulation anomalies, I guess, how do you kind of relate that to the mixing length?
So basically, if you think of the physical interpretation of mixing length, it's basically how much you can travel before the air parcel can disappear in the background. So that kind of related how much you dissipate energy. So as for the synoptic scale temperature variabilities, usually the advections are acting as the fuel, so it just kind of enhance the variabilities. And from these equations, you do see that this term is in the denominators, and the strands of this term are always act as the damping. So, and then if here I have a plot of the spatial map of these two parameters. And here, alpha L is much smaller than alpha D, so basically all the dry dampings plays a dominant role here. And that's also kind of consistent with your paper where the snow conductivities and matters, the damping, yeah.
Well, thanks a lot. We'll move on to the next speaker, Prasad Shelke, on lensing through internal variability in heat waves.
Thanks. Well, good morning. My name is Prasad, and I'm a PhD candidate at Victoria University of Wellington from New Zealand. So far, so south. And this could be potentially my last talk as a grad student, so I'm very much excited for it. This is kind of like a fresh results I'm presenting today, so even like whatever you're seeing, it's something I'm also saying like quite a initial level as well. So let's go through it. So as we all know that 2024 has been regarded as one of the warmest year on record by multiple agencies. Several claims of crossing the 1.5 degrees threshold. All of these are actually coming with a price that we pay in terms of the regional extreme events, such as heat waves, cold waves, precipitation, and whatnot. The major thing about this is some of the regions, some of the remote regions in the world which face actually the unprecedented heat waves, such as this one in Antarctica in March 2022. This actually puzzles me, like, it was a major heat wave event, of course, like caused by atmospheric river and somehow the presence of blocking in the Tasman Sea. But if you really see this picture, it's really sad to see ice shelf, which was there for long years, has been collapsing. So this was kind of a motivation for me just to analyze heat waves in the CESM2 large N symbol, which is an integral part of my thesis. So I cannot thank enough NCAR for that. So yeah. Approach is simple, just to analyze the heat wave with the classic definition of when the 90th percentile threshold climatology has been crossed by the daily maximum temperature for 3 or more days. We consider that as a heat wave. And I was more interested to see where the natural fluctuations in the system actually causes the variations in the future projections. So I focused more on the signal to noise ratio. Directly on the results, what you're seeing on the left-hand side is actually the northern hemispheric changes, future changes in the heat wave frequency in summer season. The dark spot or dark plot that you see just adjacent to that is a signal to noise ratio at each grid point. And the same you're seeing on the right-hand side. So what you infer from this is even the increase in heat wave frequency in the summer season has been projected to almost similar in the both hemispheres across 18%. There is internal variability that plays a major role, especially in the polar region, Arctic region in northern hemisphere, and somehow in the Southern Ocean as well. So moving forward, I wanted to see, like, whether the trends are matching with when we take the overall mean of the hemispheric heat wave frequency over summer. So that's basically what I've found out, and I'm pretty amazed to see that in the earliest 21st century, LENS2 actually simulated more heat waves, which is kind of surprising for me. I've also analyzed the cold waves with that, and I get exactly reverse. It's like, in the 20th century, the heat waves, the cold waves were more than anticipated, but in earliest 21st century, they are in in the loop of the observations. So, yep. Overall, what we can see is a stronger trend simulated by LENS2. And for the southern hemispheric heat wave frequency, it's majorly played by the role of internal variability that says us, like, the natural fluctuations in the southern oceans are pretty dominant over the force trend. So I just wanted to see, like, how the polar regions are showing. I've analyzed pretty much a regional basis as well, but I just wanted to show both poles, how they're showing in terms of the trends. What we can see is for the Arctic summer heat wave trends, they're weaker in LENS2 than observed based on the NCEP reanalysis too. Over Antarctica, stronger trends, but very high internal variability. Signal to noise ratio is around 0.25, which is very, very high. And yeah, moving forward, during winter time, surprisingly, the southern hemisphere shows the increase in heat wave frequency by almost 34% compared to the present-day simulations. But I feel like it's moreover driven by the internal variability, and I think more of a bias in the Southern Ocean could be a contributor to this. But overall, I've also found out in the next figure, kind of similar what we have seen in the summer season. It's like in the early 21st century, Lens 2 suggested like more heat waves than NCEP reanalysis in the southern hemisphere as well. So as usual, the stronger trends, which was kind of similar finding compared to the summer season as well. Overall, to the Arctic, the trend was closer in here during winter. It's kind of 1.78% per decade in Lens 2 and almost 1.68% per decade in NCEP reanalysis, which was actually surprising for me because the summer trend, summer heat wave trend was much weaker than the NCEP reanalysis. In the southern hemisphere polar region, Antarctica again, the signal to noise ratio was a bit low, and as we can see, there are lots of variability if we see the red line of NCEP reanalysis. Yes, so I think I finished pretty much early in time, but these are, as I said, like these are just initial results of the heat waves, and yep, it's moreover what I can see is like the natural fluctuations plays a dominant role driving the future trends, and I feel there were some of the regions I've seen in the northern hemisphere where force trend actually dominates over internal variability, which suggests that there could be a higher predictability skills. The region surprisingly was around, I think, North Atlantic Ocean, which is a good signal actually. So yep, that's me, and I really want to thank NCAR scientists for bringing the efforts on like building CESM and as awesome it is, and producing more and more simulations, and especially accessible to everyone, especially for someone like me in the Southern Hemisphere. So yep, thank you so much.
Questions? Yep.
In-state bias, and then whether that could contribute to the discrepancy between NCEP and large ensemble.
Yeah, it's a very good question. So actually, like I'll more specifically focus on the southern hemisphere here. So what happens is, like, you know, the heat wave frequency, or let's say any synoptic parameter in the southern hemisphere is actually, let's say, not very well matched between the reanalysis products itself as well. So like expecting that from model is a bit too much. But in the northern hemisphere, there was a less mean state bias. I've not shown it here. I thought I'll go beyond time. So, but yeah, it is a dominant one. Yes, yeah, thanks.
Nice talk, thank you. I'm just curious, it looked like there was a negative heat wave trend in North America for some of those. So any idea what might have caused that in the kind of central part of North America?
Oh, central part of North America is one of my favorite to work on CSM to large ensemble, because I specifically work on blocking as well, and I've seen, like, you know, the blocking associated heat waves during summertime are projected to increase in Lens 2 as well. So I would just say, like, you know, I'm still studying the reasons behind it, but yeah. We'll chat more about it. Thanks.
All right, if there are no more questions, we'll move on to the next speaker. Thank you. So our next speaker is Jairon, and it says virtual in the program, but he made it here. So he's going to talk about human-driven increases in North American and Pacific trough intensifies winter and spring heat waves.
Okay, yeah, thanks so much for the opportunity to talk, and also for the travel award that allowed me to be here in person today. This work is under the mentoring of Maria Molina, Kirsten Meyer, Katie Dagon, Ayla Simpson, and John Fasullo. And as Ayla mentioned, I'm going to talk about long-term changes in North American weather regimes, more specifically about the Pacific trough and the impacts over North American heat extremes during winter and spring.
Sorry, could you move a little closer to the mic?
Yeah,
Thank you.
Sure. So the main motivation is that there is large uncertainty regarding the large-scale circulation and the surface response associated to it. As a result, there are many differences when we compare observations and models in the historical period. And so the tool that I use to address this question or this problem is the concept of weather regimes. And so weather regimes are large-scale atmospheric flow configurations that are persistent and recurrent, and they are useful because they are a way to simplify the representation of the large-scale dynamics, as well as linking those large-scale dynamics with the surface conditions. So the question is, how are the characteristics of these weather regimes changing over the long term? The steps for obtaining the weather regimes are based on geopotential height fields. We compute the anomalies, detrend those fields, and then standardize them. And then we extract the principal components from the fields, the 12 first principal components, and for those 12 time series, we apply k-means clustering to obtain these 5 classes or 5 weather regimes. And then, as I mentioned before, the focus of the talk is the Pacific trough, which is characterized by this low over the Gulf of Alaska and this high over northern North America. So the increase in frequency that we saw for the Pacific trough was that it went from 12% daily occurrence to 19% from the past to the present. And when I say the past, I'm referring to the period of 1948 to 1977 compared to present, which is 1994 to 2023. And that increase is significant and large compared to other weather regimes during winter and spring. And so those increases in frequency are important because once we have a Pacific trough occurrence, we have also anomalies of temperature and precipitation. So we have increased temperature over northern North America, mainly Canada, and we also have dry conditions over the Rocky Mountains and east of the Rocky Mountains. Given those conditions, we also have increased likelihood of some extreme events when the Pacific trough occurs. So we have increased likelihood of extremely hot days and extremely warm spells, as well as fires, especially over Canada again. As a result of these impacts over the surface weather, when we see an increase in Pacific trough frequency, that increase is also associated to an increase in some of these extreme events. And so, especially over the region south and west of the Hudson Bay, we see this increase in extremely hot days and extremely warm spells when a Pacific trough is occurring. And so if we take a more in detail look for the Pacific trough evolution over time, we see this increase between 1950 and 1990 mainly, and then a decrease after that. And so we have these contradictory signals over time, which are consistent with some literature. On one hand, some papers agree on greenhouse gases deepening the allusion law, which will result in an increased frequency of the Pacific trough. But there's also this well-documented weakening of the allusion law in the recent years that still needs to be understood, and there are hypotheses linking it to aerosols, for example, or changes in El Niño or La Niña state. So the next question was, how well do models represent this trend, and whether or not under the model perspective, these changes can be attributed to internal variability or some specific forcing. And so we took a look at 2 large ensembles, CESM2 and E3SM2, and what we saw is that the large ensembles do not represent the trend for the past period. We see that the observed trend or change is outside the range of both ensembles. However, for the future, both ensembles agree on an increasing trend in the Pacific trough frequency. If we look at the pre-industrial runs, which is the figure on your right, those are the distributions of Pacific trough frequency differences in all possible periods of the same length as the observed record. And what we see is that the observed differences in reanalysis, which are the vertical lines, lay also outside this distribution of internal variability-driven changes of Pacific trough. We also looked at the single forcing experiments, and we see that when we look at the ensemble forced only with greenhouse gases, there is an consistent increase in Pacific trough frequency, both for the past and future period. But for the aerosol forcing, there's a decreasing trend. And so what might be happening in the large ensemble is that these two opposing trends can be canceling each other. And then that, that's involved in the representation of these long-term trends. We also looked at the abrupt quadrupling of CO2 simulation, and also compared the last 30 years of the large ensembles to the present. And we saw that under highly increased CO2 conditions, there is consistency with this increase of Pacific trough frequency in both cases. The next question was, what can be the physical drivers modulating these changes? And then what we found is that the trend that goes from 1950 to 1990 might be linked to this cooling in the northern Pacific that happened before that. And then the change inside of the trend might be linked to the La Niña-like warming over the Pacific, which will be consistent with the teleconnections that we know between La Niña and the northern circulation. And so given that, we hypothesized that maybe if we corrected the sea surface temperatures in the models, then we could improve the representation of those trends. However, if we forced the SSTs, here are the Goga and Toga ensembles, we do see an improvement in terms of the increasing trend before 1990 and then the decreasing trend after that for those ensembles. However, the Pacific trough frequency still changes outside the ranges for those two set of simulations. And so this is the summary of the talk. So I showed you that the Pacific trough frequency has increased significantly over the last 80 years or so. And then according to the models, this is likely outside internal variability, and under the model's perspective, it can be driven due to greenhouse gases. Then since we have this La Niña-like warming trend in the recent past, once an El Niño-like state happened potentially in the future, then we potentially will have also an increase in Pacific trough frequency after that, and the subsequent heat extremes or heat conditions associated to it. More research is needed on the role of aerosols and basically try to explain those opposing trends between greenhouse gases and aerosols in the large ensembles. And another question we have is that we want to look at the high resolution simulations to see whether or not we improved the representation of those trends using those high resolution simulations. And that's it. Thanks so much again.
Thank you. Any questions for Jairon? I'm also looking at the Slido if anyone online wants to ask one.
Thanks, yeah. Nice talk. I was wondering if you have any thoughts on whether the aerosol and greenhouse gas response in CSM are like of the right magnitude. Of course, we don't know them in reality, but since you kind of like point out there's an offset in the model, but that might not be the case in reality. Just wondering.
Yeah, one hypothesis that I have is that maybe the response to aerosols is too strong in the models, and so we see that strong decrease. But again, we try to look at that from the reanalysis point of view, but there's very limited data sets and record to actually assess that. And then, yeah, so potentially maybe the role of aerosols and the magnitude of the role of aerosols is not very well represented, but also it might be that the greenhouse gas is right for the wrong reasons, right? So maybe, it's still an open, hard to assess.
Yep, Aishu. Maybe go up to the mic.
The aerosol forcing change, maybe you can look at the CESM1 large ensemble, which we have a different aerosols, and you may see something similar as ER file. It's possible. Yeah.
Perfect, thank you. I have more homework. Yeah, thanks.
All right, thanks very much. Our next speaker is Jonah Shaw on the emergence of regional warming.
Hi, my name is Jonah. I'm a graduate student, or I guess I just defended my PhD at CU with Jennifer Kay. And today I'll be talking about detecting regional warming, and specifically making that detection as robust as possible while accounting for several different sources of uncertainty. And just to try and motivate this, this is a figure from the most recent IPCC report indicating the year in which these kind of standard IPCC regions are kind of have a detectable change in surface temperature. And I think the reason we're interested in this question is because climate change is fundamentally this regional process, and adaptation and mitigation is also needs to be regionally informed. And so if we really kind of take this figure at face value, you might ask why I'm interested in detecting these changes, because all of these regions have a color associated with them, and they're actually all detectable by 2012. But actually, this is just the top figure of a two-panel figure, and the second panel repeats the same exact analysis, but with a different data set. And so I think just this kind of interchanging your data sets and getting really different answers tells us that there is something going on, that we should be appreciating the uncertainty in our observations when we're asking this question. And so the research questions I'm going to try and answer here are, where actually are these changes robustly detectable when we're kind of accounting for a lot of different sources of uncertainty? And also, how do these different sources of uncertainty, both observational uncertainty and model uncertainty, what are the spatial patterns? How do they influence our regional warming? And just to start, there's kind of some previous literature that does detection of the forced response. We are not doing that. We're working with these historical trends because we're interested in kind of the impacts, which requires us to look at the, observe the historical change in both kind of the influence of the forced change and whatever internal variability realization we've seen. And so how we're going to do this is that we're going to first quantify our historical uncertainty and our surface temperature. And I think normally we think about surface temperature, historical surface temperature, in this very deterministic sense. This is just kind of an annual time series of one of those IPCC regions. Our temperature goes up and down, and there's this kind of long-term warming trend. But really, I think it's better to think about it in a more probabilistic sense, because our records are imperfect. We're not observing everywhere at every time, and we can have biases based on where our instruments are located, and all sorts of other biases that we should account for. And so this kind of probabilistic record is actually just 200 different realizations of historical surface temperature that are all reconstructed from those kind of point observations that are made while accounting for these questions of spatial and temporal representativeness and potential biases in those observations. And we get this record from the NASA GISTEMP dataset. This was developed by Nathan Lenson at Colorado School of Mines and also NCAR. And effectively, our deterministic dataset is just the median of these 200 ensemble members. And so this is a really excellent tool for assessing the role of observational uncertainty in our results. And I think a big takeaway is, whether you're interested in time or emergence or not, these datasets are a really simple and effective way to assess the role of that uncertainty. And so now we're kind of moving on to this question of detection or time of emergence. And so effectively, we take each of these time series, start with 3 years, compute a best or a linear fit to get our trend, add to our 4th year, recompute our trends, and see how they evolve in time. And that's what we're looking at in these kind of red and blue lines. They all correspond to those time series in the left here. In order to kind of assess if these trends are significant, we need to have some understanding of what internal climate variability is, or what kind of trends are expected in the absence of the human influence. And this is this gray envelope here, and we compute it from the CSM1 large ensemble. And so effectively we're just, or sorry, not the large ensemble, but rather the pre-industrial control simulation. So effectively, we're able to resample time periods of the same length many, many times from that 1800-year pre-industrial control simulation, and then explicitly construct a 95% confidence interval to, again, understand what is precedented in the absence of the human influence. And so we can now kind of answer our question of time of emergence, which is abbreviated here by TOE. And so our median time of emergence is this kind of standard method where we ignore this uncertainty in our historical records, and we now define a more strict time of emergence where we require all, or 95% of these different 200 ensemble members to emerge from our internal climate variability. And so we can take this and apply it to all these different IPCC regions and kind of reconstruct a similar figure to what I showed from the IPCC at the beginning. And we can see that, when we just ignore our observational uncertainty, we have some pattern of detectability. And what we're adding here is this strict time of emergence and then the difference between the two, which is just the delay that is imparted by this observational uncertainty. And so effectively what we see when we look at this delay is that there are plenty of regions where that delay is on the order of 0 to 5 years. It's not very large, but there are also regions where the delay is much larger, in excess of 20 or 25 years. So clearly accounting for observational uncertainty is important here if it's making kind of multi-decadal changes in the results of our research question. Of course, I also said that we would be looking at kind of the climate processes that are responsible for these delays. And so I'm just going to show two representative regions to kind of get a sense of what's going on here. And so this first region is West and Central Europe, which is kind of boring. And so we say that it's really characterized by low uncertainty and monotonic trends. Our median kind of deterministic member is really tightly bounded by the ensemble. There isn't a lot of uncertainty. And also these trends do not have a lot of kind of decadal patterns in them. They're pretty flat, they're increasing, and once they all pop out of this kind of envelope of internal variability, they stay out. And so this is a really simple situation in which we can assess this detectability question. If we look at another region, this is the Southeast Africa IPCC region, we have a pretty different story. Not only do we have much higher observational uncertainty, but we also have this decadal patterns in our trends. Specifically, we have this kind of local maximum in our trends around the middle of the 20th century, and then it falls off before increasing again. And so if we just look at all of these kinds of different ensemble members, some of them are detectable, in the mid-20th century, while others are not, and that's really kind of modulated by the presence of these decadal trends. And whether that's internal variability or things like global dimming, global cooling, we haven't looked at it, but the kind of conclusions that we want to draw here are that these non-monotonic warming trends, specifically at low frequencies, and differences in observational quality are really causing the greatest delays in our time of emergence. I also said that I would look at other sources of uncertainty in addition to model uncertainty. And so what we do is we repeat our analysis with an additional 3 Earth system models. So now we're using 4 system models, and we add another observational uncertainty product that also has 200 ensemble members. And so if you mix and match all of these kind of realizations of our historical climate and internal variability, you can generate 1,600 estimates of time of emergence for each region that you're interested in. And just to make a point about these Earth system models, we're not using all CMIP5 or all CMIP6 models. We're specifically using models with large ensembles that have been tested as good, having good regional internal climate variability. So I think it's important to not throw all of our models at this problem, but specifically use the ones that are validated for it. And so now, if we kind of show this plot of median, strict, and total time of emergence, where our delay here is not just due to observational uncertainty, it's due to all of these different sources of uncertainty that we've combined in this kind of new, larger ensemble. And so we effectively see that our delays are much larger, and they've shifted largely towards being in excess of 1, 2, if not more decades. And so all of these sources of uncertainty are clearly really important to account for when answering this question. We repeat our analysis. So our conclusion is that still, despite accounting for all these sources of uncertainty, we're still able to detect warming over in all these regions except for the Antarctic regions. And so I think we're just kind of like playing with this result of uncertainty is really important to account for, but still we're able to detect this regional change when accounting for it. Finally, we repeat our analysis at a much kind of the finer scale that our observational products are available at. And I think this really helps us localize where the delays are, which is largely in South America and sub-Saharan Africa. And I think this really points to the historical way that we observe and kind of aggregate and trust our climate data. Like this is the global South, and this is the impact of our science not being equal around the globe. And it also shows that our trend emergence is just later and less confident at these finer spatial scales. So to summarize, this kind of emergence of regional warming is robust despite accounting for these different sources of uncertainty. And our delays are large. More than 50% of the land surface had emerged by the year 2000, but more than 35% of the land surface is delayed by more than 20 years. And actually, this is now accepted in ERL, so hopefully it will be available in a DOI soon. I'm happy to take any questions. Thank you.
All right, thanks. We are at 10 minutes, so I think we'll skip questions and encourage you to ask them of Jonah in the break. We'll move on to our next speaker. That's Yanning Kuo, and that's about the role of anthropogenic aerosols and ocean warming in driving southwestern US drought.
Hi, my name is Yanning Kuo. I'm a fourth-year PhD candidate working with Flavio Linear at Cornell University. Today I'm going to talk about our finding anthropogenic aerosols and ocean warming are both contributors to the southwestern US drought since 1980 through precipitation changes. So our definition, in our study, the definition of southwestern United States is the box over there from California to Colorado and New Mexico. This is where the Colorado River, the main stream flow through and providing fresh water for the residents over this region. And in the past, since 1980 to 2014, the main precipitation season in DJF, MAM, winter and spring, there has been an observed precipitation decline over the southwest, and it is corresponding to the increasing sea level pressure over the Aleutian Low region, where we show as the red contour lines over the North Pacific. And the precipitation decline for this region specifically has created a lot of social and economic impact. For example, naturally that can create more wildfire frequency in the summer, and this region is heavily with agricultural activities, so that also impact agricultural economic. And so this region, the declining precipitation has been attributed to the tropical decadal La Nina-like SST trend, where there's a well-established teleconnection pattern that when you have a cooling trend over the central part of the Pacific, you expect the Aleutian low to be weakened with an increasing sea level pressure trend. And there has been some study that link the aerosols to contribute the La Nina-like cooling trend since 1980. For example, the paper from Yanting Huang. And we also have a paper that link the trend of La Nina-like SST from aerosols to the southwestern US precipitation drying. But today, I'm focusing on the teleconnection. Basically, in observation, we can link, we can explain this circulation chain and precipitation chain with the La Nina-like teleconnection. And so we usually use CESM to large ensemble or other climate model large ensemble to look at the force response for the same period. And this is probably not surprising to the audience that CSM or a lot of symmetric climate model indicate the historical forced SST is an El Nino-like trend pattern. But what surprises us is that even you have a forced El Nino-like SST trend, your North Pacific circulation and the precipitation for the southwest indicate a more La Nina-like circulation pattern. So the teleconnection explanation in observation is not valid in the fully coupled climate model force response. And so we take a look at the pre-industrial control simulation, where we have a very long record, and then we can identify the decadal transition that with a strongest El Nino-like SST trend. So we do a composite analysis for that. And we see that in pre-industrial climate, when you have an El Nino-like warming pattern, you have a deepening of Aleutian low with increasing precipitation for the southwest. If we do the same thing for the historical simulation, we identify the strongest ensemble members with the strongest El Nino-like transition. We can see that overall the tropical SST is warmer compared to pre-industrial control simulation. And for the North Pacific, what's consistent is that there is a missing typical El Nino-like teleconnection over the North Pacific. And so we run Amy pipe experiment with an El Nino-like SST trend. We use a linear inverse model to generate synthetic sea surface temperature, and then prescribe the synthetic SST that with an El Nino-like SST trend with the radiative forcings to run Amy pipe experiment. And so in this experiment, we showed that there's a consistent missing El Nino-like teleconnection with the post-1980 radiative forcing, even if you have an El Nino-like SST trend. And so with the AMIP-type experiment, we can now easily decompose the contributor. Basically, we run 2 additional experiments, one with the radiative forcing, and then the SST is the repeated seasonal cycle without any trend. And so in this experiment, we identify the North Pacific, and the northern part of North Pacific, especially in the Aleutian, northern part of Aleutian Island, we have an increasing sea level pressure trend. And we compare that with the CSN2 single forcing large ensemble, the aerosol-only simulation. We identify anthropogenic aerosol as the main driver for the northern part of North Pacific circulation change. And this is independent from the SST. And so we move on to the next experiment we ran. This is an experiment that we prescribed only the El Nino-like SST trend without radiative forcing changes. In this simulation, we can still see there's an El Nino-like teleconnection, but it's much weaker than our expectation from the pre-industrial control simulation. And so the El Nino-like SST trend with the uniform warming in the tropics became less effective when we compare to the pre-industrial climate. And finally, we examine whether the 2 drivers, radiative forcings and the El Nino-like trend with uniform warming in the tropics, is linearly additive to when they prescribe together. And we found that in Chem 6, this model specifically, there's a very strong residual, or we call it as nonlinearity, that when we have radiative forcing and the El Nino-like SST trend together, it generates a stronger anticyclonic response over the North Pacific, and that prevents the precipitation to arrive in the southwestern US in winter and spring seasons. And I couldn't go into too much detail about the mechanism here, but in our paper, we found that this is because aerosol and SST, they create 2 distinct circulation change over the North Pacific, and when they have their distinct changes in the upper level jet stream, that further create a barotropic response for this circulation change in the residual plot. And so in summary, the results of this paper, of this project has been accepted to be published, and I think that will be online soon. But the main takeaway from this presentation is that we show anthropogenic aerosols and the mean tropical warming combined together. They increased the North Pacific sea level pressure so that the southwestern US precipitation declined. And the implication from this study is that the post-1980 southwestern US drought, from the precipitation perspective, might be more inevitable than we previously thought. And I will be happy to take a question.
Any questions for Yanning? On the Slido, I'm also looking at that. Yes, I'm wondering, do you have any thoughts on what aspect of the mean warming is changing the teleconnection from El Nino-like SSTs?
I think from our paper, I think we demonstrate that the mean tropical warming kind of increased the static stability, especially for the subtropical high region, and so that also bring another layer of contributing to the drying over the southwest.
Yep, Jaron?
Do you have any insight into the regional effects of aerosols? Like, are they more important in some region? I know you mentioned some changes in the circulation, like in the Pacific, but yeah, what's more important, North America or Asia, or how do you think about that?
Okay, that's a good question. We didn't do a specific analysis for this study about which regional emission is contributing to this circulation change, but there are some papers, and also one of our previous work, we try to do some analysis on which regional emissions are. We correlate the AOD to the SST, La Nina-like SST due to aerosol, and we identify there's a shift mode. Basically, when your aerosol emission decrease over North America and Europe, and your aerosol emission increase over Asia, that specific mode contribute to the La Nina like SST in the Pacific and also the circulation over the North Pacific. But we didn't do the analysis here. Thank you.
Thank you very much. We'll move on to the next speaker, and that's Paul Curtis about equilibrium climate sensitivity in extra long CESM simulations.
All right. Okay. All right. Good morning, everybody. I'm Paul Curtis. I'm a fourth-year PhD student working with Alexei Fedorov at Yale. And today I'm going to talk about a pretty short and simple study that we did on ECS. And this is in collaboration with Nicole Feldl at UC Santa Cruz. So first, what is ECS? So by ECS, we mean the global mean temperature change once a climate has equilibrated to a doubling of atmospheric CO2 concentrations. Recent assessments, such as the IPCC report, which is shown below, and the Sherwood 2020 paper, put the likely bound of ECS between about 2.5 degrees C on the lower end and about 4 degrees C on the higher end. But really, I want to draw your attention to the CMIP6 band there. And obviously, there's a very big spread in ECS within CMIP6 models, with the lower end being about 1.8 degrees C, and some models with a very high ECS around about 5.5 to almost 6 degrees C. So there are a lot of reasons for this spread, but one of the major uncertainties is that these are based on estimates of ECS, and overall, we really have this lack of simulations which are actually run to equilibrium. So one way to get ECS from a climate model is to do an abrupt n times CO2 experiment and run it out towards equilibrium. So these were collected as part of the long-run MIP group. The simulations are shown below. And basically the trend is that for stronger initial CO2 forcing, you see a higher delta T EQ over C. So for example, taking CESM 104 on the left-hand side there, we see that for a doubling of CO2, you get a warming of about 2.6 degrees C, whereas for a 4 times CO2 experiment, once it's normalized, you get just over 3. So it's higher for larger C. But most of the models here were run for about 1,000 years, so it still begs the question, are we running the models for long enough? So in the first part of my PhD, I did a series of n times CO2 experiments using CSM1. So it's quite old, it's CSM 1.0.4. In the atmosphere, it's CAM4 T31 spectral truncation, which corresponds to about 3.75 degrees, so pretty coarse. In the oceans, POP2, so about ½ degree at the equator and about 3 degrees elsewhere. But the main advantage is that it is relatively cheap to run, and so I've run this model now for just over 80,000 years of simulation time. And today I'm going to focus on 8 experiments, which are shown in the table below. So starting at the warmest, so 16 times CO2, and then we have 8 times 4 down to 2 times CO2, 6,500 year control run, and then 3 global cooling simulations too. And just to really emphasize that we are going out to very long timescales here, so 8 times CO2 is about 10,000 years long. So the main advantage is that we have long timescales, and we're also systematically considering global cooling in our model, which is very rarely done. And just to emphasize that, to our knowledge, these are the longest n times CO2 experiments ever used to compute ECS in a climate model. So first we could ask, well, what happened if we stopped integrating the model after 1,000 years? Well, our ECS curve would look a little bit like this. And there are 2 trends to point out here. So looking at global warming experiments, as we move from 2 times to 16 times, what we find is that the normalized warming per doubling of CO2 gradually increases. So this is pretty much what we saw in long-run MIP. And similarly, going colder for stronger initial radiative forcing, we actually see more cooling for the strongest cases. As we go out to 2,000 years, the trends haven't really changed, but I want to point out that there is a non-negligible amount of warming or cooling in both of these warming experiments and cooling experiments. But is 2,000 years enough? Well, no, it's not the full picture. So what happens when we get all the way out to equilibrium, so this is the last 10% of our experiments, then what we find is that actually the ECS, so properly now ECS, is essentially constant for 5 of the experiments. So between 0.71 and 16 times CO2, we have this near constant ECS of about 3.4 to 3.5 degrees C. And it's only in the coldest experiments that we really see a much higher ECS, around about 4.2 to 4.4 degrees C. So I said a lot of the estimates of ECS are based on something called effective climate sensitivity. So this just really starts by thinking about simple energy balance. So N, top of the atmosphere relative imbalance, is equal to the initial forcing plus the climate sensitivity parameter multiplied by the temperature change. And what we generally do is we take an interval like I've done here with the squares, triangles, and circles, and extrapolate the linear trend back down to n equals 0, which gives us our estimate of delta TEQ. So what we find is that for the strongest forced experiments, so 16 times CO2 and 8 times CO2, as long as we're not taking the first 1 to 10 years, actually effective climate sensitivity does a pretty good job of getting the realized equilibrium warming. But as we get colder and colder, we find, and especially in the very coldest experiment, that effective climate sensitivity misses ECS almost completely. So you can look at the coldest one there and see that if we try to estimate the equilibrium cooling using years 300 to 600, then we'd get about 6 degrees C, but the reality was about 4.2. So the variation in lambda, so the climate sensitivity parameter, this is due to changes in shortwave feedbacks. In global warming experiments, this is predominantly due to shortwave cloud feedbacks, and in global cooling scenarios, this is predominantly due to clear sky feedbacks, and in particular albedo feedbacks. This is mainly due to the strong expansion of sea ice into the North Atlantic and the North Pacific, as well as the enhanced snow cover over the land. So to leave you with a summary and some conclusions, so within these experiments of CESM1, we've determined an almost constant ECS of about 3.43 degrees C across a wide range of climates. These correspond to global mean surface temperatures at equilibrium between about 285 and 300 kelvins. And really the main implication is that once we get to the very long timescales, this ratio of delta TEQ over C doesn't necessarily increase for higher C, which is a big result in our opinion, and this is something that really takes multiple thousands of years to emerge in the model. And so really when we're dealing with ECS, we should be running the models for as long as possible, and it also helps to consider global cooling to really have a systematic analysis between cases. And so I'm happy to take any questions. Thanks.
Any questions for Paul? Oh, yeah, go.
This nonlinear behaviors across various degrees of CO2 forcing. I was wondering if you have looked at the role of radiative forcing instead of feedback to set the nonlinear behaviors across the CO2 levels.
So would this be looking at F?
Yes.
Yeah. So I think if I go back, can I go back? So there's a few studies that I think talk about F increasing. So as you increase the amount of CO2, then F gets stronger. So if you look at a curve like this, then one conclusion could be that actually the climate sensitivity is decreasing, right? In a way. We didn't look into this too closely. Our point was just to really actually look at what the equilibrium warming is. Yeah.
Right.
CAM4 physics, which uses an old radiation scheme that's somewhat flawed.
Sure.
And I'm wondering if your results might be sensitive to that, or at least the timescale that you're finding might be sensitive to that, especially if you might be saturating the water vapor bands.
Oh, so I think with regards to saturating the water vapor bands, I don't know if that would happen at 300 kelvins. It might be a little bit too cold for that. I think that typically happens around 305, 310 in some of the models. With the specific scheme in CAM4, I'm not too sure. I think that was something we would need to look into a little bit more. But yeah.
Questions? Yeah, Aishu.
My question is, in this simulation, you do not consider the change of the ice sheet. So when you consider the cooling, you see reduce the CO2, and you can have the CS albedo effect and also snow effect.
Yeah.
But for the warming, if you consider the melting of the ice sheet, do you think the equilibrium sensitivity will change? Could it match your cooling?
That's a really good question, actually. I'm not sure. We can talk afterwards, perhaps. Yeah. Yeah.
All right.
Okay.
Thanks very much.
Thank you.
Okay, our next speaker is Jacob Stuyvenant-Allen on the role of atmospheric nonlinearities in producing ENSO asymmetry within a statistical dynamical version of CESM.
Wow, this is a very loud stage. Hello, everyone. I'm Jacob. I'm a new project scientist over at NCAR-RAL, but this is some work I did during my postdoc with Alexei Fedorov, so same guy from the last talk. How do I go next? There we go. Okay, so ENSO in observations, we typically look at a map like this, which is showing us a linear view of SST anomalies, simply a regression of those SST anomalies onto the Niña 3.4 index. But what this hides is that El Niño and La Niña are not mirror images of each other. And one of the ways in which they're different is in their magnitudes. So if I draw a couple of lines across the Niña 3.4 index in observations, you can see that El Niño events tend to be larger in magnitude than La Niña. And this results in a skewness of about 0.5 since 1980. Another way that they're different is in their spatial patterns. So El Niño tends to be shifted a bit further to the east, while La Niña is kind of centered in the middle of the basin. And there's some variation here, but generally speaking, these are the features we can observe in SST. And I want to highlight just in terms of the linear dynamics, right? Wind anomalies are really important for moving warm or cold water throughout the basin, specifically zonal wind anomalies. And the way that they're doing that as well is that the thermocline is adjusting to those processes. So this is very hand-wavy and linear, but functionally what I want to highlight is that one of those processes, either in the atmosphere or ocean, has to account for the difference that we're seeing in El Niño versus La Niña amplitudes and spatial patterns. And in the literature, people will talk about westerly wind bursts or maybe the role of the nonlinear response of wind stress to SST. And in the ocean, people point to the role of nonlinear heat advection and essentially processes that result in the thermocline adjustment being different for El Niño versus La Niña. And this is a bit of the academic chicken or egg, but I think it is important because if you look at GCMs and CMIP6, for example, the range of skewness is minus 0.5, meaning La Niña is way stronger than El Niño, all the way to 1.15. And CSM2 in particular, for the 1,000-year PI control, has a negative skewness as well, minus 0.2. So this is not something that models are picking up well. I'm going to skip that one. So what we do is we take CSM2 and we design an experiment that allows us to essentially manipulate the characteristics of zonal wind stress within the fully coupled model. And this is commonly called a hybrid coupled model of ENSO. There's a few examples out there. But what we do is we take wind stress anomalies from reanalysis, so they're coming from ERA 5, and those are estimated with simple statistical methods. And we keep the climatology from the CSM2 control. We edit the source code in the coupler, so we're manipulating zonal momentum flux. When the atmosphere is communicating that momentum flux to the ocean, we intervene and say, no, please use the pattern that we are prescribing rather than what you would normally do. In a simple formulaic expansion, you could think of this as a first-order polynomial where your wind stress in the tropical Pacific is equal to a 365-day climatology from the PI control with this additional linear term, which is just the anomaly of wind stress multiplied by the internal Niña 3.4 index. So it evolves freely within the model. And then you can just add a second-order term, so quite simple. And this second-order term is proportional to the square, right, of the Niña 3.4 index internal in the model. Let's take a look at what that looks like in space. So this is an animation showing us the wind stress that we're prescribing in the model. Blue is easterly and red is westerly. So as the Niña 3.4 index becomes more positive, what you see is just an increase in the magnitude of westerly wind anomalies. As it switches back to La Niña, you'll see that the spatial pattern is exactly the same. So those are they're perfectly symmetrical with each other, perfectly linear. Now, if you want to add in a nonlinearity, you can simply do a second order fit on these grid point values. And notice as we switch from La Niña-like conditions all the way to El Niño, that not only do we have different patterns and magnitudes of wind stress, but they evolve in time based off of the magnitude of the Niña 3.4. So these westerly wind anomalies are actually shifting east in the model and more appropriately replicating the actual processes that happen in reanalysis and observations. Okay, so that's our hybrid couple experiment. We run 4 simulations, 2 linear ones. Basically, we modify the strength of the wind stress in the model, and we look at how ENSO responds. And then we run 2 nonlinear simulations as well, where we add in that nonlinear term, and again, we just modify the strength of it. So I'll talk about why we do that. The linear simulation alone can tell us, okay, in the absence of atmospheric nonlinearities, what is the asymmetry that the ocean model produces completely by itself? Without this nonlinear feedback and wind stress, what does the ocean do? Then we can ask the question, do ocean nonlinearities depend on the strength of that atmospheric forcing in a linear framework? The nonlinear experiments will then basically tell us, okay, what's the importance of this nonlinear atmospheric wind stress feedback to underlying SST anomalies? All right, let's look at some results finally. This is just a time series of the Niña 3.4 index. We run this for 200 years. And what we see here is actually really good in terms of ENSO and really good in terms of a hybrid coupled model. So we have the nice characteristic 2.7 to 5 year dominant variability of El Niño and La Niña events. There's irregular and chaotic behavior. If you've seen other hybrid coupled models, they're completely cyclical, whereas this one, because we leave all the other fluxes allowed to freely do what they do, we get quite a nice and chaotic El Niño. And it also gives us realistic amplitudes and spatial patterns. So all in all, I was feeling pretty happy after we ran this first experiment. But note that in the bottom left, you can see that the skewness of this experiment, it results in an ENSO that is negatively skewed. Again, La Niña is stronger than El Niño. When we increase the coupling strength, or just make the wind stress stronger, this gets worse. So the ocean actually produces a negative asymmetry in ENSO without these appropriate atmospheric nonlinearities. When you start to add those in, then we get things that look a lot more like observations. So if you look at kind of the -2 degree C line, our La Niña amplitudes are drastically reduced, and we're getting strong El Niños, much like we observe in observations. And the skewness here is about 0.2, but only by adding the full nonlinear term can we get statistics which look exactly like we see in observations. So this is really highlighting that nonlinear, the atmosphere is the critical driver of creating this fundamental asymmetry in ENSO. Here I just want to show, let's see, oh yeah, this got updated. So I'm not going to talk too much about these pictures, but a lot of other work has showed that ocean nonlinearities are important as well. And what I want to draw your attention to, if you look at the red shading, the bottom 2 panels are our nonlinear experiments. And what we're showing is basically nonlinearities in the ocean only arise when you have the appropriate atmospheric nonlinearity. So in the chicken or egg question, the atmosphere is really driving this feature that we see in good performing climate models and in reanalysis. So can ocean nonlinearities alone create asymmetry? Well, not the correct one. Without the wind stress nonlinearities, ENSO is actually negatively skewed. Do ocean nonlinearities depend on coupling strength? Actually, this exacerbates the problem. So if you just add more momentum flux into the model, you're going to make your ENSO technically worse. But if you add in the appropriate nonlinearities, this is when you start to get an ENSO that behaves much like what we see in reanalysis and observations. So I'll leave, if I can go back one, yeah. I'll leave my conclusions up here, but what I want to highlight as well for CESM3 is that there's a problem with the El Niño to La Niña-like phase transition. These are just some Hofmüllers, and what you can see is in the linear case on the left, you have a El Niño event which exists for almost 2 years. You have anomalies which persist throughout the tropical Pacific. And with the nonlinearities, part of this paper that I just submitted, so fingers crossed, but part of what we show as well is that the actual transition gets a lot better when you have the appropriate atmospheric nonlinearities. So some of those problems might come from not prescribing or not having the correct response to tropical convection and wind stress anomalies within this tropical Pacific. So I'll end there. Thank you, and I'll take any questions.
Thank you. Any questions? I guess I have a question. So it seems like you'd need to run a long time to really know the true nonlinearity. Do you have kind of like a key diagnostic you'd recommend, like some nonlinear regression onto Niña 3.4 or something for model evaluation?
Yeah, I think Andrew Wittenberg, I think, came out with a paper that said you need 200 years of ENSO statistics to trust them. But in our simulations with CSM, it was actually quite stable. I would be checking results 50 years, 70 years, 100 years. And I didn't find that it changed that much. So maybe that's a bit good in terms of like model development for ENSO. Did that answer your question?
So I guess I was thinking of, rather than just kind of measuring the nonlinearity, if you had, say, a 30-year run, would you recommend like regressing wind stress in a particular region onto Niña 3.4 to see whether you're kind of capturing the processes that are relevant?
Yeah, you can do that and do a second order polynomial fit as well. So you'll get a second term, and you could compare that with reanalysis. In CSM2, it's way too weak. I'd be happy to share that with you.
Yeah, we can talk
Okay.
in the break. That would be good. All right. Thanks a lot. We'll move on to the final speaker before the break. I think, yeah. Asaya Badurunisa Salinity on looking at moisture sources and pathways for South American rainfall in variable resolution CESM. So if you hold that and point it, it'll appear there. It's
I see, okay. Hi. Okay, so I'm here to introduce to a new set of simulations, new set of interesting simulations that we can use to study the moisture sources and pathways, especially for the tropical South American rainfall, and to study its variability. Okay, so tropical South America is one of those regions where we don't have enough data or literature to characterize the trends in the extreme rainfall events. So all the gray hexagons that we see here, or the tropical South American region, means we don't have enough data. So we are trying to do like a comprehensive study to get a detailed understanding about South American hydroclimate. For that, we are using a high-resolution climate model simulation. And this is part of a bigger project where we also use lake sediment records from tropical lakes, even lakes from remote islands within the Eastern Pacific. So more about our high-resolution simulations. We are running different experiments, but I'm going to talk more about the historic, like preliminary results from my historic simulations. So when I was writing the abstract, I was more ambitious, but right now I only have 23.5 years of historic simulation, so it's going to be like very preliminary output from the historic simulations that I have. And technically, this is not a high-resolution simulation. This is a variable resolution simulation with a nominal 1 degree grid over the entire globe with high-resolution nesting over our region of interest. And when it comes to broader South America, we have 0.25 degree resolution. And by improving the horizontal resolution, we are actually able to capture some of the finer precipitation, details or precipitation structures, which is actually very important for us. Especially, we are going to use this information to like compare with proxy records, which is coming from local, like a specific grid point where the proxies represent localized climate variability. Moving on. So more about moisture tracking. So the moisture tracking in CSM GeoTrace, or the model that we're running, we can actually define the source regions. And from these different source regions, the possible source regions, we can track the moisture until it rains or snows into some region. And this enables us to answer a lot of questions. I'm sorry, okay, I'm just figuring this out. So this enables us to answer a lot of questions, but in the interest of time, I'm just going to show a few tracked moisture from like some of the important source boxes. So we have 17 source boxes from which we are tracking moisture. and then one all land box and one all ocean box. So these four are the most, like, the oceanic source boxes from which we get a lot of rainfall to the tropical South American region or the monsoon region. And it's not surprising, all of them are Atlantic source region, and during the monsoon season, we get strong wind coming from the Atlantic into the tropical South America. And there are some source boxes in Pacific from which we get moisture coming into the South American region, especially the regions which is to the west of Andes. But regions that is to the east of Andes, it's mostly the moisture is coming from Atlantic source boxes. And the one source region that I want to focus on for this talk is the northern South American land box. So that is the contribution of local recycled moisture or the evapotranspiration which is happening over the land. So the values that we see here is the contribution to the total rainfall. So we see that this northern South American land, or the Amazon box, this green box here, actually contributes about 10 to 40% to the total rainfall, which agrees with all the previous studies. And then this 10 to 40% value, this value differs between seasons, and also it shows a large internal variability. And it changes with modes of variability, so I wanted to see how modes of variability like ENSO or Atlantic Niño, so these are the two modes that actually drives the internal climate variability over the tropical South American region. So during a typical El Nino event, what happens is there is this enhanced convection over tropical Pacific. So we know that it results in a subsidence over the Amazon region, and it results in reduced rainfall over Amazon, or we see Amazon drying. So do we see that in our simulations? Yes, we do see. So when precipitation is regressed onto the Niño 3.4 index, we see this negative precip anomalies over Amazon, but we wanted to see if this teleconnection, do we see this negative anomalies in precipitation which is tracked only from the Amazon box or the tropical South American region, the role of the local evapotranspiration or moisture recycling. So I did a El Nino composite and a La Nina composite, and during the El Nino season we see negative anomalies, means there is less contribution from evapotranspiration or local moisture source, and during La Nina there is enhanced moisture source coming from the Amazon box. And going to Atlantic Niño, so Atlantic Niño is similar to ENSO, zonal fluctuation in sea surface anomalies over the tropical Atlantic. And during the positive phase of Atlantic Niño, we get the eastern Brazil gets positive precipitation, a lot of flood events over the eastern Brazil, and Atlantic Niño activity is actually maximum during the austral winter season, which is JJA season. So during JJA season, this positive anomalies actually extends even further to the west. Do we see that in our model? Yes, we do. We get this positive anomalies over the eastern Brazil, and then what about the precipitation which is tracked only from the Amazon source box? So we do see a reduced negative anomalies, positive anomalies, increase in contribution from Amazon source box to this region during the positive phase of during Atlantic Niño, and during Atlantic Niña there is a reduced contribution from the Amazon source box to the precipitation over eastern Brazil. So either this is local recycling of the moisture responding to the ENSO, or maybe it's actually reinforcing the ENSO teleconnection over these regions. So yeah, these are the key takeaways are moisture tagging and does enhance our understanding of the sources and pathways shaping the region's hydroclimate. And actually, these findings does highlight the complexity of regional precipitation responses and the need to isolate the role of climate change from internal climate variability modes, maybe like using large ensemble simulations in future. Thank you. And I want to give a huge shout out to Ellen Rhodes for developing the grids, and Adam and Jesse for developing this GeoTrace branch of CSM2, and Sophia for all your help, and our collaborators and all the funding agencies and people who work in these funding agencies. Thank you.
Thank you. Any questions? I mean, you're using regional refinement, so it seems like a nice opportunity to look at the impacts of resolution. Have you considered running a low-res version for comparison?
We did run a NE30 PG3 simulation, test simulation, but I didn't do a comparison, but I did a comparison for nominal CSM1. And we are able to capture more finer details, especially in the standard deviation of basin. Yeah.
Any other questions? All right, if not, I want to thank all the speakers again, especially for keeping to time. And we'll reconvene after the coffee break.
Now it's almost time. And welcome everybody come back to the second session of the CVC-WG summer working group summer meeting. And we will start. And first of all, when the speaker comes here, when you speak, you just close to the mic so the online people can hear more clearly. And also for this remote, the top button that's for the laser pointer, the second button, the big one, is forward, and the small one is backward. Okay, now we start. The first speaker is Wei Liu.
Thanks, Aishu. Hello, everyone. My name is Wei Liu from UCG website. So today I'm going to talk about simulated Antarctic sea ice expansion, reconciles climate model with observation. Okay, so the motivation of this study. The left panel shows the observed Antarctic sea ice area from satellite, basically the black curve, since 1979 to recent years. So you will see a very robust sea ice expansion before 2015, and afterwards we have a sea ice decline. On the other hand, if we look at climate models, we will see most models will simulate a sea ice decline through the whole period. So here I'm showing the CESM M2 large ensemble simulation, shading for the intermember spread, and the blue curve shows the member average. So you will see a very robust Antarctic sea ice decline. And this is not alone, and this sea ice decline can be seen in both CME5 and CME6 models. On the other hand, if we look at the sea surface temperature change, and the previous study showed that the top panel is observation, we will see over the Southern Ocean from 79 to recent years, we will see a very robust, weak, but robust Southern Ocean sea surface cooling. If we look at the multimodal mean, and we will see instead of cooling, the Southern Ocean show a warming trend. Now we can see the issue, and either in Antarctic sea ice and also in the Southern Ocean sea surface temperature trend. So the model show a decline of Antarctic sea ice, but the observation is expansion. And on the other hand, for the model show the warming, but observation show the cooling. Now my question is that, are they related? Okay, so here is my scientific question. First, will a simulated Antarctic sea ice expansion render the Southern Ocean surface cool, or the other way around, given the ice-ocean coupling? Or to what extent can the bias of Antarctic sea ice change account for the bias of Southern Ocean SST change during the 3 to 4 decades since satellite era? And the last question, how will the Antarctic sea ice expansion associate with other components of the Earth system? So I use 2 papers to answer these scientific questions. All right, so first, let's look at the model simulation. And as I mentioned before, most CME5 and CME6 models simulate Antarctic sea ice decline since 79. However, I still can find there are several models with some ensemble members that can simulate Antarctic sea ice expansion consistent with observation. So I list all these models on the right in the table, and also with the ensemble members showing the sea ice expansion, and also the other members showing significant sea ice decline. Panel A shows this result, and the black curve show observation. And on the other hand, we can see the red curve shows the expansion group, and the purple curve shows the decline group ensemble mean, with shading for the intermember spread. Then panel B shows observed sea surface pattern for the sea ice concentration change for observation, C for the expansion group, and D for the decline group. So we can see the historical ensemble simulations from several climate models show the sea ice natural variability enables the models to simulate Antarctic sea ice expansion during 79 to 2014 under anthropogenic forcing. And this highlights that if we only see the variability mechanism, yes, it could be possible that this natural variability of Antarctic sea ice on decadal time scale can simulate the expanded Antarctic sea ice during this period. So this is very different from previous mechanism because we don't need any interference between the ocean, sea ice, and also atmosphere. Then let's look at the Southern Ocean sea surface temperature change. Again, the panel A shows observation from 79 to 2014, and the B is expansion group, C is decline group, and D is the difference between the two, decline minus expansion. So we can see, yes, if we can have an Antarctic sea ice expansion, it can allow us to see a cooling change over the Southern Ocean, but only to the north, to the south of 50 degrees. To the north of this latitude, roughly, and we can now see the cooling change that is different from observation. So I infer that this could be related to the tropical variability. On the other hand, if we look at the difference, and we can see overall it gives us a bipolar pattern, and we can see the cooling over broad southern hemisphere, especially if we look at the tropical Pacific, we can see the connection between the Southern Ocean and the tropical region in the Pacific. That has been well discussed in many previous studies, show the teleconnection. And also, this is not alone. If we look at the Atlantic, we can also see the linkage between the Southern Ocean and the near tropical regions. We can also see this Antarctic sea ice, if can well simulated the expansion, it can also influence the ocean heat uptake and also subsurface temperature. Panel A shows observation, temperature change do not mean. If you look at the high latitude, we can see a cooling change in the upper 100 meters. Similarly, we can see the pattern in the expansion group. However, if you look at the decline group, and we will not see the cooling change in the upper 100 meters close to Antarctic, instead a warming change. So if we look at the difference, we will see very robust. This Antarctic sea ice expansion can give us this very robust cooling change. So this is because the net downward sea ice transport that can allow fresh water to be extracted near the Antarctic and released into the open ocean, which will influence the stratification and also the cooling in the surface open ocean water. Reduce the vertical mixing to warm the water beneath, so that is the mechanism for the sea ice influence the ocean subsurface temperature. So one may wondering, and I just grouped the model members that can simulate the Antarctic sea ice expansion or decline. However, there are many other processes going on, so people may be wondering, how can you infer this difference is mainly due to the Antarctic sea ice? So to prove that, and I conducted a sensitivity experiment. So I use CESM1 chemical physics, and I gradually increased the snow and ice emissivity over the Antarctic sea ice area. So it's a time-involving factor. I give this number. I keep it linear because I don't want to add some nonlinear thing. So you will see the, this experiment is under the historical and RCP scenario. So for the original historical and RCP simulation for the CESM1, which is shown in the blue, we will see still a very robust decline of Antarctic sea ice from 79 to 2013, which is different from observation in black. However, if I just modify this emissivity and I can allow the model to simulate an increasing change over Antarctic sea ice, which is shown in the red curve. So this modification can be viewed as an ice forcing. It's adjust the model to reflect the correct response of Antarctic sea ice to external forcing. So the spatial pattern is shown in the bottom, and for the observation in B and the expansion group in C and D for the decline group. So that allows us to look at the influence of Antarctic sea ice from this scenario, and also we can look further for the Southern Ocean surface temperature and salinity. So this is my result, and observation for the sea surface temperature change in E and H for the sea surface salinity. So we will see if we compare with observation, if we have the Antarctic sea ice expansion, we can observe a very robust cooling trend around Antarctic to the south of 60 degrees, and to the north, that is a warming trend. So for the decline group, similarly, from the previous slides, and it's very robust warming trend through all the Southern Ocean. On the other hand, if you look at the surface salinity, we will see the observation give us a increased trend for the sea surface salinity close to Antarctic, but outside would be the freshening trend. This feature is well captured by the expansion group. However, the decline group give us opposite trend. So that is because the Antarctic sea ice expansion in the expansion group can bring a very robust increasing trend to this region, because sea ice forms around the Antarctic coast move northward due to meridional wind drift and melts in the open ocean, so in lower latitudes. So that's why we can see the sea ice increasing trend around Antarctic, but decreasing trend over the lower latitudes. Okay, so here is my conclusion. First, I found that historical ensemble simulation with multiple climate models give us the result sea ice natural variability can allow models to simulate Antarctic sea ice expansion from 79 to 14 under the anthropogenic forcings. Along with sea ice expansion, Southern Ocean surface and subsurface temperatures can cool up to 50 degrees north, and that is consistent with observation. In the other hand, and I skipped the mechanism, but I have this in the backup slide. Neither the Southern Ocean Southern Annual Mode nor the IPO, Interdecadal Pacific Oscillation, can fully explain the simulated Antarctic sea ice expansion. However, if we look at the expansion, it's closely related to the surface meridional winds associated with the zonal wave 3 pattern. And further, Antarctic sea ice perturbation experiments demonstrate that the linkage between the Antarctic sea ice expansion and the high latitude Southern Ocean surface cooling and stratification. So that's all I have. Thank you very much.
Thank you. We have to move on.
Running time?
Yeah.
Thanks.
Next presentation will be given by Yue Dong on Southern Ocean and ITCZ.
Okay, good morning, everyone. I'm Yue Dong from UCLA. Following the previous talk by Wei, this is another talk looking at broader impact of the Southern Ocean. And we specifically focused on the strength of the Southern Ocean teleconnection and trying to ask how much tropical response we should expect from the Southern Ocean teleconnection. And in the end of the talk, I hope to deliver that the currently simulated Southern Ocean teleconnection strength is likely underestimated due to models' mean state biases. Yeah, so similar to the previous talk, I'm also motivated by this observed SSD trend over recent decades, where we see this pronounced cooling over the tropical Eastern Pacific and Southern Ocean. Also, over the past long-term record, we see this co-variability between these two regions, suggesting the close connection between these two regions. Also, in idealized modeling studies, we often see if you perturb the Southern Ocean in slab ocean model, fully coupled models, we often see a remote tropical or subtropical SSD response featuring this La Niña-like SSD pattern. So far, the proposed mechanisms involve first the mean state wind advection in the tropical Eastern Pacific, and further, this SSD can be amplified by west feedback, the wind evaporation SSD feedback, and also subtropical cloud feedback. Especially the subtropical cloud feedback has been identified in this nice paper as a key driver of the intermodal spread in Southern Ocean teleconnections. But then, based on this mechanism, we also find that surface winds, especially mean state winds tied to tropical mean state circulation, and probably also precipitation, are also key to the teleconnection. So our guiding question is really, what's the role of the tropical mean state climate, especially the location of ITCZ in the Southern Ocean tropical teleconnections? Specifically, we ask if in one single model, if we were to correct the double ITCZ bias, can we see changes in the simulated tropical response to Southern Ocean cooling? And if so, does it hold for multiple models, eventually explaining the intermodal spread? And if yes and a yes, we find a robust ITCZ modulation of this teleconnection. And we ask, does it come about through changing cloud feedback or through other process? So in this work, I'm gonna show a set of idealized CES1 simulations we run, and also a 2 existing model intermodal comparison project allow us to assess intermodal spread. So part 1, CES1 simulations. I use this slab ocean version of CES1 Camp4 model, my favorite model, which you can see later why. So with fixed radiative forcing, fixed Q-flux climatology, we can run this long-term control simulation to get a mean state. And then on top of that, I impose this regional Q-flux anomaly in the Southeast Pacific to force the Southern Ocean to cool. So you can see some weak tropical La Niña-like ST response, all consistent with previous studies. But in this model, it also has a pretty typical intrinsic model mean state biases, including double ITCZ, the tropical zonal mean precipitation too symmetric between the 2 hemispheres, and also too weak cloud feedbacks compared to models like satellite observations. So what I'm gonna do use this model is to, in addition to this base set of simulations involving a control run, involving a Southern Ocean cooling experiment, I'm gonna provide 2 additional sets of simulations, also involving a control and experiment. Except in the control level, I'm gonna do some modifications to address each of these ITCZ or cloud feedback biases, so we can assess how this process change or influence the Southern Ocean teleconnection response. Okay, the first set of a simulation, let's call it flux adjusted or flux adjustment, because I use a modified Q-flux climatology to force the global SST mean state to match observation. And as a result, we see the tropical mean state precipitation looks much better compared to observation, show this asymmetric pattern. And I should also mention that in this set of a simulation, cloud feedback, especially subtropical cloud feedback, doesn't change because we didn't specifically change model physics. So it's just the boundary conditions. And another set of a simulation in the control level, we explicitly change model physics in the radiation code by artificially increase low cloud cover sensitivity to local SST anomalies to match satellite observations. So in this set of simulations, we have stronger cloud feedback, especially over the subtropical Eastern Pacific stratocumulus stack. And this change doesn't actually result in any substantial, you don't see the color because we don't actually see substantial changes in the long-term mean state of precipitation SST. So in this set of simulations, we got a better cloud feedback, but still double ITCZ bias. So now we have 3 different control runs, which feature different biases, and we're gonna apply the same amount of a Q-flux forcing to see how tropical SST response varies. And turns out in this tropical La Niña-like SST response got amplified in both of these modified experiments, especially in the middle column where it would change the ITC or change the mean state SST distribution, precipitation distribution without changing cloud feedback, but still that leads to a strong tropical SST response. So where does it come from? Is it through the cloud feedback or a different process? So we perform this surface energy budget analysis and then find for left column, for the flux adjusted round, and the right column, the cloud adjusted rounds, compared to the base to understand what causes this additional tropical cooling in the bottom, in the top. And we found for cloud adjustment, probably as we expected, the additional cooling primarily coming from the middle right second panel, coming from the shortwave cloud radiative flux, which is as expected because we explicitly changed the cloud feedbacks. But for the left column, for the flux adjusted round, we found additional cooling actually more from, or broadly coming from latent heat effect due to wind changes, suggesting stronger west feedback in the subtropical trade wind regions and along the equator, because now we have a better ITCZ, we have stronger southeasterlies, the trade wind regions, and also across equatorial surface southerlies, which enhance this mean wind advection. So part 1 in this CES1 simulations, we separate the different process, and we find, yes, indeed, changing mean or improving the mean state does lead to strengthened tropical response to Southern Ocean forcing, and that's mostly through the west feedback, not through the cloud feedback. So next, we're gonna ask, does this process hold in other models in a multimodal project? So we looked at this nice community effort called ETMAP, where in which the fully coupled models are forced by this zonal band of heat fluxes, and all of the models tend to show first Southern Ocean cooling because it's directly forced by radiative forcing, and also tropical response. And in a previous study, they find the different varying degree of a tropical response is correlated with models of tropical cloud feedback. But here we want to test, does it even related to the tropical ITCZ? So you can see here the zonal mean precipitation, all the models share this double ITCZ bias, but also large spread. So let's define this asymmetric index and then plot it against model simulated tropical Eastern Pacific cooling average over the white box. Now you can see in general models have more asymmetric precipitation mean state, which means smaller double ITCZ bias, also tend to simulate more stronger tropical East Pacific cooling response, which you can also see these regression maps showing that better ITCZ mean state indicates stronger tropical ST response to Southern Ocean forcing. And this is because these better mean states are associated with stronger southeasterlies in the top right, and also cross-equatorial southerlies, which promotes, like we show in the slab rounds, promotes stronger west feedback and the mean wind advection, which contribute to this tropical cooling response. So when I say this strong correlation, I found it very interesting because we know in the previous study, came out 2022, the tropical ST response in the middle is correlated with models cloud feedback. And this time, we find the same tropical ST response is also correlated with ITCZ bias. So we asked, are these two quantities or even correlated? So we just happen to capture the physics instead of some meaningful physical statistics instead of a physical mechanism. But turns out the answer is no. The correlations between the precipitation index we define to quantify the ITCZ and the cloud feedback metrics are not strongly correlated. It's pretty weak, it's insignificant, and it holds for this subset of 18 maple rounds and also the broader CMIP6 ensemble, suggesting that the intermodal spread in ITCZ and the intermodal spread in subtropical cloud feedback, they don't really explain each other, or at least a large portion. So their influence on the tropical SST response may also operate separately through cloud feedback versus a west feedback process. So the last application is that, what causes the Southern Ocean cooling in the first place still remains a debate. But one of the hypotheses, in addition to natural variability from previous talk, that the Antarctica ice sheets melting. So this is another nice recent community effort called SOFIA, where several fully coupled models all include or add this additional freshwater anomaly around Antarctica to simulate Southern Ocean and global climate change. On the right, you see the multimodel mean. They all simulate Southern Ocean cooling and some degrees of a tropical response. And we apply the same analysis and find, again, models with more asymmetric precipitation and smaller ITCZ bias in the mean states tend to simulate stronger tropical response per degree of a Southern Ocean cooling through the same mechanism because stronger mean state winds. So from here, we can probably infer that since all models share this kind of a systematic double ITCZ bias, then the realistic Southern Ocean teleconnection to the tropics in nature could have been stronger than we currently simulated. Before I conclude, it's just last slide, I promise. This is Southern Ocean pacemaker simulations in two versions of CESM1. Where the Southern Ocean SST anomalies are nudged to observations, we see the remote response. And this paper by Sarah Kent et al. 2023, they find the CESM2 tends to simulate stronger subtropical or remote response, potentially due to this model has stronger cloud feedback. I just wanted to quickly show that actually CESM2 is also one of the models that has much better ITCZ mean state and stronger trade winds in the tropical Eastern Pacific region, which according to our laboratory rounds, according to the intermodal regressions, can also contribute to this subtropical Eastern Pacific ST cooling response. So this summary of the talk, I think basically the key message to the polar community is that to more realistically assess the global impacts of polar climate change signals, we actually need a better tropical mean state to be able to simulate this teleconnection. Well, for the tropical communities, we actually need first Southern Ocean signals, and then the better tropical mean state to better represent the recent SST trends in the tropics. Thanks, and then I don't know if we had time to take questions.
Okay, thank you. We have to move on. We run out of time. Yeah, we have to move on. Yeah. Okay, next speaker is Glenn Liu. He's talking about the sea surface salinity and the non-salinity climate.
Hi everyone, thanks for the chance to speak today. So I'm going to present some recent work I've been doing with my advisor Young-Oh Kwon and collaborator Claude Franquinol. So this work concerns the question of what is the importance of ocean dynamics for North Atlantic climate variability, particularly on low frequency timescales. And oftentimes such studies focus on SST variability, but what can we learn by looking at salinity instead? So say you have a temperature anomaly. That anomaly is damped to the atmosphere via air-sea heat fluxes. But for a salinity anomaly, you don't have the same atmospheric damping. However, both variables are impacted, presumably by the same ocean processes, like diffusion and mixing, horizontal advection, and vertical processes like entrainment. So you can often think of salinity variability, particularly the damping of salinity, as sort of the representation of the sum of all these ocean processes. But considering all these different processes, how do these different processes individually impact salinity variability? And what can we then, in turn, can that tell us anything about the role of these ocean processes for North Atlantic climate? So for this study, I really focus in on the sort of vertical entrainment, local vertical entrainment, and try to investigate that using a simple model. You might be familiar with the Franquinol and Hasselmann stochastic model. So the idea here is that temperature changes are driven by atmospheric forcing, which acts on much faster time scales. So you can think of it as white noise of a certain amplitude. And you also have damping to the atmosphere, whose strength is determined by a linear coefficient, lambda A. All of these parameters, however, do vary seasonally. And when you think about the winter, you have much deeper winter mixed layer depths in the ectotropics. In the summer, the shallow thermocline insulates anomalies from the previous winter of interaction from the atmosphere. And the following fall, as the mixed layer deepens again, these anomalies are entrained back into the surface, leading to winter recurrence, known as the reemergence mechanism. So you can represent that in the stochastic model of the addition of an entrainment term. And what I'm showing here is the persistence or autocorrelation function of SST anomalies. And you might notice that the white line, which is CESM1 with full ocean physics, is represented pretty well by a simple stochastic model of 3 terms in orange, suggesting that it's a pretty good representation for SST just considering these processes. But the question is, does this also apply for salinity as well? So for salinity, we can use stochastic evaporation and precipitation forcing. Again, there's no heat flux damping, but we have the same entrainment mechanism. Furthermore, these anomalies beneath the thermocline might be damped by subsurface processes, so we can include a simple damping term to represent that subsurface damping. So I won't go into the details of the parameterization in the interest of time, but essentially we estimate these parameters based on CSM1 large ensemble, the historical period, and see if the simple model can replicate salinity behavior in the full physics ocean model. So to start off, let's think about kind of the autocorrelation function again, and a kind of simple quantification of the strength of reemergence. You can just difference the winter maximum with the summer minimum to get sort of an index of reemergence. How does this look like in CSM1? We have the pattern here, strong reemergence where you have deep wintertime mixed layer depths, no surprise, and some kind of larger values in the subtropics. So does the stochastic model reproduce this? And we integrate the stochastic model for 10,000 years at each point. We do this calculation, and you can see it does a pretty good job. So again, there's no horizontal circulation in this simple model, but it seems to be capturing many of the features of seasonal differences in persistence. Let's kind of zoom in on a point with pretty strong salinity reemergence to understand what's happening. So again, I'm showing the wintertime autocorrelation for CSM1. This is the target. We have the stochastic model with just entrainment, no subsurface damping, and see that that's not enough. Sea surface salinity is too persistent. But when we add in subsurface damping, that substantially improves the representation of salinity salinity persistence, but it's still too persistent on longer timescales. And I just wanted to bring in SST. As I mentioned earlier, the stochastic model does a much better job with SST, and, but you can see the importance of subsurface damping really comes in for salinity. So we've been talking about persistence. But what about variability and the amplitude of variability and its patterns? So I can take the average of SST over the basin, apply a 10-year low-pass filter, and regress that back to the SST anomalies to get the pattern of variability for CSM on top and stochastic model on bottom for SST. The takeaway here is that the pattern is pretty similar, but the stochastic model is underestimating the level of variance at low frequencies. And we have the opposite problem for salinity. In this case, salinity is too energetic in the stochastic model in the absence of horizontal dynamics. You can see here that the variance has about 1.6 times the level of variance in CSM1. So the kind of takeaway here is the missing dynamics from the stochastic model beyond entrainment, such as horizontal circulation, seem to have different impacts on SST and SSS. So that brings me to the main takeaways. We see that a simple model with no horizontal circulation does a pretty good job of capturing the pattern of seasonal differences in reemergence in a model of full ocean physics. We also see that subsurface damping is pretty important for capturing the level of long-term persistence in salinity. And finally, kind of the main takeaway here is like, what have we learned about North Atlantic climate? We learned that these sort of horizontal ocean processes impact temperature and salinity differently. So you can't necessarily generalize an impact on salinity and use that to apply that to SST. So yeah, that brings me to the end of the talk, and just wanted to thank the organizers for travel funding to attend this event. And yeah, happy to take any questions.
Any question?
Thanks, Glenn. That's really neat work. I was wondering if you'd explored the use of a linear inverse model as a multivariate stochastic integrator and something to take into account non-local effects.
Yeah, I have not explored that, but it'd be really interesting because this is a fully local model. So yeah, we don't consider any of the non-local effects, but it would be really fun. We could talk more about implementing that, but I'd be really interested.
Any other question? Oh, I have a quick question.
Oh, sure.
Possible you make the green curve is more close to the white one? Like now you said you added a subsurface damping term. And
yeah.
What else you can do to make it the salinity perform better?
Yeah, that's a good question. I guess one thought is maybe some sort of way to add horizontal advection into the model. So maybe that could provide an additional source of damping to salinity, but still thinking of how to do that in a fully local model. So maybe some way to kind of parameterize the effect of horizontal advection. But yeah, that's a good question, and still need to think a little bit more about how to increase complexity to reach that level.
Any other question? No? Okay, let's move on to the next talk. Thank you. Next talk will be given by Kai Huang. He's research on the QBO and MJO.
Cool. So good morning. I'm going to present our recent work on the QBO-MJO connection. And this work was done in collaboration with local NCAR scientists as listed here. So yeah, I will begin with some brief introduction of the QBO-MJO connection. So the QBO was found to have very significant impacts on the MJO, like it was found nearly 10 years ago. Like if you look at the MJO propagation amplitude, and if you define the QBO at 50 hectopascal level, you will find MJO tend to be stronger and more likely, more likely to propagate across the maritime continent in the QBO east season than the QBO west season. And if you track all the MJO events in the NDGFM season from 1979 to 2020, and you will track all 81 MJO events, and you subset them into the QBO east phase and QBO west phase, and then do a difference for the Hofmuller diagrams in the precipitation anomalies, you'll find much differences over the Western Pacific and maritime continent region. That is inconsistent with our findings here, like MJO is stronger and more likely to propagate across the maritime continent. And there are several unique aspects of this QBO MJO connection. First, is seasonality. This QBO MJO connection is only seen in the winter seasons. And second, the location preference. Like the QBO's influences on MJO is centered around the maritime continent region. And then the uniqueness, like among all the other convectively coupled equatorial waves, MJO is the only one to feel the impacts from the QBO. And then the last, its emergence, like you can only detect the QBO MJO connection in the reanalysis datasets after the 1980s, but before the 1980s, you don't see such strong connection in the reanalysis datasets. And in the past decade, several mechanisms are proposed trying to explain the QBO MJO connection as listed here, but I will still say the connection is not thoroughly understood. Other than that, all climate models suffer from the missing of this QBO MJO connection. And even with a prescribed stratosphere through the nudging, so the QBO signal is the same as the observations, still the QBO MJO connection is missing there. And last, the QBO MJO connection is somehow magically slightly captured by the forecast system and some of the MJO case simulations as listed here. So it turns out, like, if you look deeper into the QBO's modulation on the MJO, you will find QBO not only modulates the MJO propagation and amplitude, it also modulates the environmental conditions for the MJO convection to happen. So here, this diagram actually are showing you the environmental moist static energy anomalies for the MJO precipitation anomalies in the x-axis, and also at different days of the MJO as listed by the y-axis, and day 0 is when the MJO convection is over the Indian Ocean region. And so if you look at the shading, colorful shading here, it actually tells you at a specified MJO precipitation anomaly and at a certain day of the MJO life cycle, what will be the environmental MSE anomaly be like. And you can do that composite for the 28 MJO events that in the QBO easterly phase and 34 MJO events in the QBO westerly phase. And you do a difference between these two diagrams in the QBO easterly minus QBO westerly, you'll find some interesting features here. So first, after day 0, you'll find the positive MJO precipitation anomalies, the environmental MSE actually get increased in the QBO easterly phase, and vice versa for the negative MJO precipitation anomalies. That is to say, like, when the MJO convection happens in the QBO easterly phase, even with the same precipitation anomaly intensity, the environmental MSE is actually higher, provides more energy for the MJO convection to consume. And the MJO is therefore become more mature and more efficient in removing that MSE anomaly, like in the QBO easterly phase than in the QBO westerly phase. And if you are familiar with MJO dynamics, this is actually a very favorable condition for the MJO to develop. And other than that, before day 0, from day roughly -5 to -15, you will see a very interesting precursor of higher MSE, even for the negative MJO precipitation anomalies before day 0. So remember, like, the MJO convection is a dipole mode. Like, to the east of the MJO active convection, it is a suppressed convection phase, and at front of the MJO active convection. If you somehow get higher MSE to the front of the MJO active convection, then in the following days, when the MJO active convection moves there, it is obviously get stronger and more mature. The question is, like, what is really going on here in these preceding days of the MJO active convection? To investigate that, we did another composite analysis, but for the moisture anomaly and dry static energy anomaly vertical profiles, also binned by different MJO precipitation anomaly values for day -15 to -5, where this producing, higher MSE anomalies happens. And if you do the differences between the QBO easterly and QBO westerly phase, you'll find, like, for the mild to negative precipitation anomalies of the MJO convective system, in the middle to lower troposphere, you will see a very overall wetting and a warming signal here. It seems like some convective processes are happening here in the QBO easterly phase. And then we also checked the vertical profiles of the MJO vertical velocity, but we do not see the corresponding changes in that. That is to say, like, this wetting and warming producing, signal to prepare the MJO convection to better develop in the QBO easterly years are not coming from the MJO system itself. So where does it come from? it turns out it is coming from these changes in the MCS or mesoscale convective systems. So here the maps are the composite maps for the MJO precipitation with bandpass filtered precipitation anomaly, which are represented by the contour lines here. And the MCS precipitation are represented by the shading colors here, yeah. So we did the composite for the QBO east phase and west phase, also based on the RMM index for the MJO. So the top two panels are actually showing you the days, a composite for the days where the MJO are inactive, that is when the RMM index amplitude are below 1.0. So in the QBO east years, if you look at the shadings here, you'll find much increased MCS activities or precipitations west of the maritime continent. While to the east of the maritime continent region here, the MCS precipitations are suppressed here, and vice versa in the QBO west phase. Like to the west of the maritime continent region, you get decrease in the MCS precipitation, but to the east of the maritime continent region, you get an increase. So I won't go into the details why this happened, but this is relevant to QBO's ability to modulate the MCS propagating behaviors, like it is more westward propagating in the QBO east years and more eastward propagating in the QBO west years. Other than that, we can also do the same composite analysis for these two variables, but based on the RMM phase when the MJO are in the active phase, that is when the RMM amplitude are greater than 1.0. And these maps are showing for the MJO days in the QBO east phase. Like in phase 1, the MJO convection is mostly here, and MJO suppressed convection is west of the maritime continent region. But in phase 1, you already see some scattered, MJO convection. In phase 1, in the MJO suppressed convection, you already see some NCS activities here. And in the next phase, phase 2, it gets collected by the MJO convection envelope and become part of the MJO convection. And at the same time, the new MCS activities are identified again to the east of MJO convection. And in phase 3, it is absorbed by the MJO convection envelope and become part of the MJO convection. And what's more interesting is when the MJO is about to cross the maritime continent from phase 4 to phase 5. Like, look at here in phase 4, the MJO convection is mostly over the Indian Ocean and the western maritime continent west of the 120 degree east. But east of the 120 degree east, in the suppressed phase of the MJO convection, you get very strong activities in the MCS precipitation, and which you will not see if you look at the climatology. Like here is actually the whole of the MCS activities. But with the help of the MCS convective precipitations, in phase 5, the MJO follow the path of this preceding MCS precipitation and propagate across the maritime continent as a result. So that is for the QBO east phase. How about the QBO west phase? So we did the same composite analysis here. And it is very interesting, like in phase 1, you get a decent amount of the MJO convection here, but in the suppressed phase, you don't get much MCS precipitation over the maritime continent. And as a result, in phase 2, like the MJO convection cannot develop very well. It here, like phase 3, when you see these stronger MCS precipitation anomalies over the Indian Ocean, and then in phase 4, like you get decent amount of the MJO precipitation again. And in phase 4, like when the MJO is about to cross the maritime continent region, compared with what we saw at the QBO east phase, where you are seeing this, enormous amount of the MCS precipitation anomalies here, but in the QBO west phase, you don't see it here. Like it is very suppressed, and as a result, MJO could not propagate across maritime continent region without these preceding MCS precipitation anomalies. So finally, some take-home messages. First, we found that QBO could modulate MCS propagation over the maritime continent region, leading to more local MCS activities over the Indian Ocean in the QBO east season. And this increased MCS activities pump moisture from the boundary layer to the free troposphere, creating a favorable weather and warmer environment for the following development of the MJO convection. And then MJO is therefore become stronger in the QBO east phase and more likely to propagate across maritime continents with the guidance of these MCS precipitations. And now I'm trying to use this potential new theory to explain the several unique features about the QBO MJO connection. First is seasonality. This is probably due to the fact that MJO cross the maritime continent through the southern sea surface, where the MCS activities are strong only in the borrow winter seasons. And secondly, the location preference, because that is due to the MC is the area with strongest MCS activities in the tropical Indo-Pacific region, and uniqueness. That is due to the fact like MJO relies more on the moisture variation than other tropical convective systems. And the emergence, like, that is probably due to a data quality problem. Like, no MCS satellite observations are fed into the real analysis datasets before the 1980s. Maybe the QB-MJO connection is always there, but due to this data quality problem, we cannot detect that in the real analysis datasets. And why this is missing in the in the climate models, that is due to the fact that the MCS simulation remains a problem there, and why this is somehow detected in the real analysis and prediction system, even with the biased MCS simulation there, that is probably due to like the regional wetting and warmer effects of the MCS could be assimilated into the initial field of these systems. So these systems could capture the QB-MJO connection there. And I will stop here and take any questions.
Okay, thanks, Kai. Since we are run out of time and we don't have the question for now. If you have any question for Kai and Wei and Yue, you can ask them offline. Next speaker is Charlotte Dimond. She's talking about the climate sensitivity.
All right, good morning. So this is a talk that is really just asked the question, how does the treatment of some of our parameterized physics in the CESM2 affect its mean state and variability? And I tend to approach this problem really from the perspective of trying to understand how does it affect the Madden-Julian oscillation. But for here, I'm going to try to take sort of a broader scope and just introduce this with a couple of figures from a recent paper by Aaron Donohue, who has shown that for many of CMIP, from CMIP 3 through CMIP 6, most coupled models tend to underestimate ocean heat transports and overestimate atmospheric heat transports. And one of the leading causes for this bias, according to their paper, is that the models are extracting too much energy from the ocean surface in the subtropics through evaporation. So, of course, some of this excessive evaporative heat or evaporative flux from the ocean can arise from things such as too strong winds, too warm SST, perhaps too dry upper marine boundary layer. But the question I'm going to address today is, what if there are biases in the way we're actually computing the flux that could contribute to this? And so we've done some previous work that has shown that when we change the bulk surface flux parameterization in CESM2 to that by developed by Bill Large and others, Large and Pond, that we tend to get an improved simulation of the MJO in atmosphere-only simulations. And so this is the next step to say what happens in the coupled system. And the take-home message is it's very complex, but I'll try to walk you through this. So this is just a quick picture to show global latent heat flux estimates using a variety of reanalysis products. In the top two rows, satellite products here, and some other types of products or hybrid products. The algorithms used to compute the fluxes are listed next to the titles. You can see that all of the satellite products use the core flux algorithm developed by Chris Farrell. And so we're going to implement the core flux algorithm into the CESM2. This has been done before, but I want to show you a couple of additions that we've done. One of the motivations for this comes from a paper by Brunke et al. In 2003 that showed that the Core 3.0 algorithm is among the least, or the overall least problematic, that's their phrase, bulk flux algorithm. So despite the biases you may have in your wind speeds, for example, the idea is you should at least be computing the fluxes to the best of your ability. Okay, and so here are what could be improved. Good, you can see this. So the first is the bulk transfer coefficient. So if we swap the large and Jaeger, the gray curve bulk transfer coefficients with those from the core, you can see that we should overall reduce the evaporation from the global oceans. But the core algorithm has two additions that we are also implementing. One is the ocean cool skin effect. Molecular thermal conductivity limits, it actually reduces the few upper millimeters of the ocean surface temperature by about 0.3 Kelvin compared to just below this very thin layer. The second one is the diurnal warm layer effects. Now, Large and Caron actually implemented this in CESM 1, I believe, when the ocean and atmosphere are coupled once per day. But you still need this when you have a 10-meter vertical resolution, as shown here with the blue curve, versus 10-centimeter vertical resolution. This is done with Mundi. So you will drastically underestimate the effect of ocean diurnal warm layers without this. Okay, so what we did is we are going to show you some comparisons between the default model, which I've labeled Large and Jaeger in gray, the CESM, or the core bulk flux algorithm with just the exchange coefficients, and then what I'm calling the core 3.6 plus, which includes the cool skin and diurnal warm layer effects. So just to get started, when we implement just the core bulk coefficients in the CESM2, this is fully coupled. These simulations were all run for about 35 years. We can see that somewhat contrary to what I expected, we see a reduction in global sea surface temperatures. But when we add on the cool skin and diurnal warm layer effects, this is offset somewhat. And so the total effect is shown here. And if you're familiar with CESM2 SST biases, you can see that this effect would offset some of the biases in that model. When we look at rainfall, the main take-home message is that we seem to see an enhancement of the Hadley circulation. So we have more rainfall in the tropics along the equator, slight reductions in the subtropics. And in the interest of time, I'm going to go straight to the MJO. So what we're looking at is these are Hav-Muller diagrams of MJO propagation from the Indian Ocean across the maritime continent, which is shown with the box, into the Western tropical Pacific. And so the numbers that you see here, this is the standard deviation of rainfall at this base point. This is slightly underestimated in the default surface flux parameterization. When we go to just the bulk transfer coefficients, you can see that the coherence of the MJO is degraded, although the amplitude of the MJO in the Indian Ocean increases. When we include the cool skin and the diurnal warm layer effects, we see a recovery. We see a reduction in the variance, but it's still greater than what you saw in the default. And we have largely restored the eastward propagation of the MJO. And within this box, you can see that we have better coherence across the maritime continent. When we look at ENSO, what I'm showing here, this is the autocorrelation. This is from the ERSST from this period, which is the closest available match to the time period of our simulations. The longer term variability is shown on the light gray curve for reference. So just to give very broad sweeping statements about what the biases are in ENSO, for the default case, we can see that ENSO is too periodic and it has weak asymmetry compared to observations. When we move to the core bulk transfer coefficients, this too strong periodicity remains, and the weak asymmetry remains as well. It's not until we include the cool skin and diurnal warm layer effects that we see changes that tend to reduce the overly periodic behavior of ENSO, but also improve the asymmetry of the signal. So this is just a quick summary. These are very new results. There are an infinite number of problems we could look to explore. I'm a tropical person, so this is what I've looked at. But the main take-home points are that the bulk transfer coefficients alone can actually have negative impacts on variability compared to the default surface flux configuration in CESM2. It's not until we go to the inclusion of the cool skin and diurnal warm layer approximations that we see the greatest improvements. And then I just want to close with some thinking ahead towards CESM3. When we go to the MOM6 ocean, the near surface vertical resolution will increase from a 10-meter depth in CESM2 to 2.5 meter depth in MOM6. This means that the diurnal warm layers and perhaps rain layers, which I haven't talked about here, can be directly simulated. The cool skin effects must still be parameterized. And then why the core bulk flux algorithm? Again, it's one of the least problematic algorithms when compared to direct covariance flux measurements. It was developed specifically with global marine surface flux measurements collected from various field campaigns. And then getting the flux right seems to improve some aspects of variability with what I feel like are maybe rather minimal changes to the mean state, although more scrutiny of that point is needed. So I will close there.
Because of time, we just move on. Thanks.
All right, thank you.
Okay. Our next speaker is Crazy. And he's
in recent years, I spent a lot of time producing new parameterizations of organized convection for climate models. And this has used a new idea about the coherent structure issue, representing organized convection as coherent structures in turbulent environments. And we've got had a lot of success in terms of GCMs. In fact, for the NCAR model, the DOE model, and the the British UM, we have an increased representation of the Madden-Julian oscillation. So, in fact, that is the major. It's not working. Oh, here we go. In fact, I'm particularly interested in different types of Madden-Julian oscillations. You notice here that this is a Madden-Julian oscillation, and there is definitely signs of what ends up by being tropical cyclones. So that means there's a totally different transport methodology. And so I'm going to compare now the vertical momentum transport by the MJO and the association with these tropical cyclone-like circulations. I'm going to be using super parameterized numerical simulations and the analytic representation of that. It's not working. How do you go? See. In fact, this is the representation. This is the representation of a change from convectively coupled systems like MCSs to the MJO in a global model with organized convection explicitly simulated. And I'm going to be looking now at the don't know why this is not working.
Would you like me to advance them for you?
Yes?
I can advance them for you if you like.
Yes, please. Please do. Next one, please. The MJO system occurs after a particular length of about several days, about 40 days in the simulation. And you'll notice that the vertical structure is very interesting. There are strong westerly bursts. The westerly bursts are a very interesting business in terms of the MJO and its effects. Next. And the middle diagram here shows the typical circulation in an MJO. The vertical, tilted rearwards, and of three types. Next simulation. The interesting point about this is that there is the presence of Rossby gyres in the simulation, just like what there was in the first diagram I showed you. And in fact, these Rossby gyre-like circulations within MJO circulations, I think, is a very important thing. Next picture. So I'm going to compare the vertical momentum flux now in due to the vertical convection, the organized convection in the MJO. You notice that there's the vertical momentum fluxes are negative. That's quite typical in MCSs and in the MJO. And on the left, on the left here, you see the analytic model, and the other side is the numerical simulation by Grabowski. And you notice they agree quite well. And the vertical negative, the vertical momentum flux contribution produces westerly wind burst type circulation. Next one, please. This goes over to the Rossby gyre-like circulations within the MJO. And you notice on the right, again here, the numerical simulation and the analytic model. It's very, very similar. In fact, the red region is where you get westerly wind bursts. This one here should have the red circle, the red diagram in the middle. So that means that the generation of momentum flux, and particularly to the westerly wind burst, is a very important part of the whole circulation. So what are the takeaway comments here? I've shown here that the analytic models agree very well with the numerical simulations. And the MCSP, the representation of organized convection, overcomes the gray zone problem of representation of organized convection in GCMs. And this means that that extends traditional parameterizations. And the convective momentum flux by the MJO and the Rossby gyre-like circulations in the MJO, in fact, in certain circulations, is an important part of the westerly wind burst, and therefore in an unusual situation as well. And it's also salient to the MJO that Kai was talking about. So there's a new approach, basically, to representing the MJO in climate models that has a definitely effect. And the Rossby gyres, in fact, the contribution by the Rossby gyre-like circulations exceeds that due to the MJOs themselves. In fact, this may actually explain partly why the El Nino situation is very different, has very different distributions of heating, and some of them are stronger than others. I would suggest that it's the horizontal transport due to the gyre-like circulations within the MJO that's causing that change of amplitude. But this is totally a theoretical
and numerical result, and I would be interested to know if there's any realism in reality, so to speak. Thank you.
Have a couple of questions. If not, let's move on to the next talk, which will be given by Quasi Quagrin. We'll talk about how do atmospheric rivers change under warmer climate versus climate engineering.
Just give me a second to pull up your slides.
Well, as they pull up my slides, I know a lot of people will be wondering, is this Quasi? Yeah, this is Quasi. I'm the other one, so yeah. Just to clear your mind, this is Quasi Quagrin. Okay, thanks a lot for pulling up my slides. So today we want to talk about atmospheric rivers in the stratospheric aerosol injection experiment. This is work that contributed to my PhD. So I recently defended, and I passed, yeah. So this is work that has had contributions from my advisor, which I'm very thankful for, Dr. Travis O'Brien, and another Quasi, and Ben Kravitz, and Simon Towns. So let's talk about atmospheric rivers. So these systems are very large moisture transports that bring a lot of rainfall to the cold polar regions. So what I'm showing here in this movie here is water vapor that is in the atmosphere. This is in the Atlantic. And you can see these orange long lines. So these are what we call atmospheric rivers. So the panels A and B are showing us the plan view and the cross-section view of atmospheric rivers. These have been identified mostly over the West Coast as baroclinic wave propagating rivers in the atmosphere. So they bring a ton of water vapor, and they can cause a lot of precipitation and lead to a lot of dire consequences. So why do we care about these atmospheric rivers? Because one, they bring good amount of precipitation to water-stressed regions and also help in drought relief. However, they can contribute to extreme precipitation globally. Like the literature has shown that atmospheric rivers can cause a lot of flooding events. So this event here, which is Bloomington, Indiana in 2021, was an atmospheric river event that brought about 6 inches of rain in 8 hours. So they can bring a lot of rain, a ton of it. This is also downtown of Bloomington. We had 1 casualty from these extreme precipitation events. So they are very important. They also happen in Santa Barbara and most of the West Coast. They bring a lot of mudslide and landslide. This event, which is not playing in Santa Barbara, had about 10 foot of landslide. So we had buildings that were tearing apart because of that back-to-back atmospheric river event that was happening there. So they are catastrophic when they do happen at the extreme level, but they are good as well. So we want to see how they will change in the warmer climate, but also look at how they will change under stratospheric aerosol injections. So the problem is that we do not really know how they will change under SAI, but we know that under SAI, there's going to be a reduction in the global mean surface temperature. So that means that we would expect that precipitation will be affected, but we don't know what the sign or the signal for these changing atmospheric rivers will be. So that's what we're going to talk about. So the data we use the SSP 245 scenario, which is more representative of the current pathway I think we are trajecting on, and then also compare that with the SAI 1.5 from the ARISE simulations. So what we do is that we split the duration into the near future and the far future, the mid future, sorry, and then we detect atmospheric rivers using this toolkit for extreme climate analysis, which was developed by my advisor and some colleagues. We then characterize atmospheric rivers based on their impact to see how they will affect precipitation. So now let's look at some results here. Just to give us an understanding of what we are looking at, the
the first row is going to be talking about the near future, the second row is going to be for the mid-future, and the last row is going to be for the entire duration, which is from 2035 to 2069. The first column is for the SSP experiment, the second column is for the SAI experiment, and the third column is the difference between the SAI and SSP atmospheric river days. So what we are looking at here is the atmospheric river days per year. So a couple of things to note is that during under the SAI experiment, we have a retreat of atmospheric rivers from inland regions. We can see this in the North American region and also in the Australian coast. So we see that under SAI, we have this reduction in the number of AR days, whereas under SSP, we have some atmospheric rivers penetrating inland. And recently, my lab and I in 2024 did a work on emergence of atmospheric rivers in the Midwest, and we can see that even represented here. So these are not just West Coast phenomena as we initially thought, they happen in the Midwest as well. However, although we have this fewer inland ARs, under SAI, we have more oceanic ARs happening, which was quite interesting for us to see. We have these about a magnitude of 15 to 30 more ARs happening per year in the oceans under SAI. So that was a cool result to find. We tried to find out why this happens in our paper that is currently under revision. Also, we look at the latitudinal extent of atmospheric rivers, and we see that under SAI, we have more ARs restricted to the mid-latitude as opposed to under SSP. So this means that under SAI, we would expect that most ARs will be region-focused, that is more in the mid-latitude. And this is quite interesting. We might think these intervals are small, but 1 degree is to about 100 kilometers. So we are having a change of location by about 5 degrees, that's about 500 kilometers. Putting that in miles, that's about 200 miles change in the location of atmospheric rivers. So the SAI experiment changes what we see in atmospheric rivers quite a lot. So I want to characterize atmospheric rivers based on a scale that is a Ralph et al. Scale, which tells us about the impact. So how long do we have an atmospheric river over a location, and how does it affect precipitation? So we have weak atmospheric rivers, which are about 250 kilogram per meter per second to 500. And we have the exceptional atmospheric rivers, which can bring about 1,250 kilogram per meter per second of moisture to a region. And when they persist for longer times, they can lead to heat waves. We've seen that in the Pacific Northwest, heat waves and all that. So yeah, we would also want to look at moderate and good ARs, which bring not extreme rainfall, but good amount of rainfall to the region. So we'll characterize all that in just a bit. So in this panel, what we are looking at, these two panels, we are looking at the difference in the categories of ARs that happen under SAI relative to ARs that happen under SSP. And what we see is that under SAI, we have an increase in the beneficial ARs, that is ARs that do not bring a lot of rainfall or are not that catastrophic. But under SSP, we saw that there was going to be an increase, but it's reduced totally under the SAI. And we see this happen in both the Northern Hemisphere and the Southern Hemisphere. One thing that we see is that we have more Category 3s that are projected under this SAI experiment in the Northern Hemisphere relative to the Southern Hemisphere. And then the longitudinal extent also tells us something similar, but just tells us the locations. We see that there's going to be, there's a projected increase in Category 3s, especially over the Pacific region. So we are still concerned about why do we care. So we want to look at precipitation because nobody is living in the atmosphere to be affected by ARs, but when they do precipitate, they affect us. So we want to look at how precipitation changes. So what we see is that these figures are similar to what I showed initially. The last column is what we are going to be focusing on. We are going to talk about the changes in precipitation. So under SAI, we have more drier, we have less precipitation compared to the SSP. One thing that I want us to note, which probably affects us, is the West Coast precipitation from ARs. We see that we have a reduction in precipitation under SAI over the West Coast specifically, and also over Southern America, the East Coast of North America and Southern America experiences these reductions. So A few conclusions. We did a couple more to test why we see these changes. It's basically thermodynamics, that the thermodynamics outgrow the dynamics. So that means we have more water vapor in the atmosphere and the SSP. That's why we are having all these changes. So the conclusions we draw from our experiment with this one scenario, I would want to highlight on that because this is just one scenario of SAI experiment, is that SAI has a potential to reduce AR-associated rainfall and also has the possibility to reduce catastrophic atmospheric rivers. That means we'll not be having these extreme category 5s and 6 that are very, very, very destructive. And the last thing is that SAI increases beneficial rainfall. So that means people in the California coast where they need a lot of water and there's a lot of drought, they can benefit from these atmospheric rivers that do happen over there. So thank you. And I would like to thank my collaborators and everybody who played a part in this. Yeah, thanks a lot.
Thank you. We can have one question.
Thank you. Nice talk. So I'm curious, first question, in SAI, are the aerosols homogenously distributed? And second question, if so, in a real-world application, they might be distributed in isolated locations, and what might that effect be?
That's a very good question. So that's something that we are thinking of addressing. I think in the ARISE simulation, they are homogeneously distributed at 30 degrees north, 30 degrees south, and 15 and north. Yeah. So they are homogeneously distributed, but we are trying to see, since this is just one experiment, it's difficult to quantify the differences or the biases based on the locations, but it will be something that will be very interesting to see. I know Christine Schultz has a paper that looked at just the West Coast and looked at the GLANCE SAI experiment, and they show that there are some inhomogeneities even in the location of ARs and all that. So it will be very, very interesting to see, but this is like a very new branch looking at SAIs and ARs and the SAI. So yeah, we'll try to answer that question in the near future, but yeah, thanks a lot. Yeah, thank
you.
Thank you.
Well, the next talk will be given by Harusuki Hirasawa. This talk also on the geoengineering. This is instead of a sulfate injection, this is for cloud brightening.
Okay, yeah, good morning, everyone. So I'm going to be presenting some results from a development of a scenario that we're hoping to include into the GeoMIP intercomparison, focusing on using mid-latitude marine cloud brightening simulations to get something closer to what the SAI community has developed for their scenarios. And so this is work that I've done. So I ran some CESM and E3SM simulations, and then my colleague Matthew at the University of Exeter ran some UK ESM simulations for this work. So yeah, marine cloud brightening, it is one of the main proposals for solar radiation management or solar geoengineering. And so in contrast to SAI, which focuses on stratospheric aerosols, marine cloud brightening aims to leverage the Toomey effect specifically. So it's this idea that if we inject aerosols into the lower marine boundary layer over the oceans, they will interact with the clouds, increasing the number of cloud droplets, and then each of those cloud droplets will, since they're smaller, they'll reflect more incoming sunlight. And so that will, in turn, reduce the shortwave downwelling at the surface and create cooling. So this is then modulated by adjustments in the clouds. So when we were putting together the design for this protocol, we sort of wanted to address three main questions. So first is how we represent the MCB in the GCMs. The second is where MCB should be deployed to get perhaps more ideal or more less harmful climate impacts. And then once we have that information, we can run some of these scenario simulations to determine when and how much MCB is required to cool. So the approach we're taking is to apply increasing sea salt aerosol emissions. This is a figure comparing 6 different atmosphere-only models
And so the solid lines are showing the all-sky forcing, and then the dashed lines are showing the cloud component of that forcing. And so what we find is that, so first off, we specify an increase in accumulation mode sea salt aerosol. This is not as simple, this is not really a simple thing to do. So depending on the model, accumulation mode aerosol means different things. And so actually a lot of the variations we see across the models is the result of different emission rates. So since the mass of aerosol emissions scales as the cube of the dry radius, if you have a larger aerosol emission, the mass emission scales quite quickly. And so, yeah, since we have this large uncertainty in the aerosol radiation from the, in the ERF due to these injected sea salt aerosols. So in our case, we're looking at a range from, for example, at 50 teragrams per year, from -7 watts per meter squared in NORISM and all the way down to essentially a negligible forcing in the GFDL model. So in order to ensure that we're getting similar forcings across the models, we are explicitly defining a fixed SST simulation in order to benchmark the forcing that we get from sea salt aerosol. And the idea is that rather than specifying a set amount of sea salt aerosol emission, we have all the models determine what sea salt aerosol emission gives you a target ERF, in our case, 2 watts per meter squared. And so the other thing is, recent work on MCB simulations has found that when you apply marine cloud brightening in the subtropical Pacific and Atlantic, you end up producing this La Niña-like cooling signal. And in a lot of cases, this is probably undesirable to, for example, in CESM, which is in panel G here, we end up getting some regional warming as a result of MCB. And so when we apply MCB in the subtropics, that might actually exacerbate warming regionally. However, when we shift the emissions towards the mid-latitudes, we find a couple things. So the first is that at least in CSM and E3SM, actually the forcing is more efficient at mid-latitudes because there's more low clouds to brighten. And then we also find that the feedbacks are less negative in the mid-latitudes, and so we get more cooling per unit forcing when we are applying MCB in the mid-latitudes. And then finally, we see that in general the cooling is more uniform, and so we don't get any of those regional warming signals that we got, for example, with the subtropical MCB case. And so so going forward, we decided to focus on this mid-latitude ocean MCB scenario strategy. Since, I figured I'd include this because this is sort of relevant to our, when we're designing the controllers. So the algorithm that adjusts how much MCB we're putting into that atmosphere. Actually, when we compare across the models, the subtropical versus the mid-latitude MCB cases, the response timescales are actually quite different. And so in general, the global temperature response tends to saturate much more quickly to a constant sea salt aerosol forcing in the subtropics rather than in the mid-latitudes. And then we also get fairly substantial differences across the models too. So in the case of UKSM, it takes there's an E-folding time of about 5 years versus almost 15 years for E3SM. Okay, and so the actual protocol that we're using is going to be similar to a proposal for SAI, which is that MCB begins in 2035. And then we target the MCB emissions in order to maintain temperatures at 2020 to 2039 global mean surface temperatures. So this is roughly a 1.5 K target. And so these are the emission rates on the top row, and then the temperature time series on the bottom row for the 3 models that we ran. And so I think one thing to point out here is that if you take a look at the y-axis on the top row, we are using a fairly large range of emission rates across the models. So in UKSM, we need as much as 100 teragrams per year, but in CSM, we only need about 5. So there's a very large uncertainty in the aerosol forcing that we get across these models. But regardless, when we
calibrate the MCB emissions and then we apply them in these simulations, we are able to maintain this 1.5K target pretty successfully. So when we take a look at the actual temperature patterns we get, so on the top I'm showing the SSP 245 temperature anomalies. In the middle, this is the anomalies in the MCB simulation. So this is greenhouse gases plus MCB, and then on the bottom, this is just taking the MCB signal. And so you can see that, for CESM and UKSM, I've computed the statistics. For E3SM, I only have one ensemble member so far. But you can see that there's a significant reduction in the temperature anomalies globally across the three models, and there's much fewer significant land temperature changes in CSM2 and E3SM. And then in the case of UKSM, actually, we're not quite cooling enough, especially at northern high latitudes. And then I think as a final point, we wanted to compare MCB and SAI. And so on the left, on the right, I'm showing a comparison of MCB in A, C, and E. This is the same anomalies as before on the previous slide. And then on the far right, these are showing the SAI, equivalent SAI simulations from ARISE. And so you can see that, in general, the precipitation anomalies are fairly similar in the middle row. This mid-latitude MCB scenario is able to produce a temperature response that is a temperature and precipitation response that is broadly more similar to SAI than previously tested MCB scenarios. Mid-latitude MCB is more efficient at cooling and provides a temperature response that is more similar to ARISE SAI. And then there's this large uncertainty in the CSOL aerosol emission forcing, and so we want to encourage people to do explicitly defined fixed SSD simulations to ensure that we're understanding these uncertainties. Thank you.
We can have one quick question.
I'm wondering about the hemispheric asymmetry, and in particular, since the background aerosol would be so different, would this cloud susceptibility be different, and would you have to account for that, and if your controller does account for that?
So yes, we do find that this, especially the Southern Ocean regions, the red boxes in the Southern Hemisphere, we do get more forcing per unit mass emission, especially in CSM and E3SM. We do we do try to account for that, but our controller is just one-dimensional. It only accounts for the global mean surface temperature, so we're trying to account for the hemispheric asymmetry by just setting the relative emission rates in the two hemispheres. So there's more emissions in the northern mid-latitudes than the southern mid-latitudes.
Okay, thanks.
Thank you. Okay, now let's move on to our session last talk. We'll begin by Irene Isami. She's also going to talk about the marine cloud brightening and impact on seasonality.
Hello, everyone. Thank you for staying for the last talk of the session. So I'll be presenting some work today that I worked on in collaboration with Jack Chen here at NCAR. And it was just accepted for publication with GRL. So if anyone's interested, please scan the QR code to read the paper, but I'll show it again at the end. And I think I can skip this because we just saw it. So previous studies of marine cloud brightening, or MCB, show that while it could reduce surface temperatures, it also commonly results in uneven cooling patterns and a perpetual La Niña-like sea surface temperature response, which was just mentioned. And this is exemplified in the plots shown on the slide here, which really highlight that La Niña-like state. Chen et al. 2024 explore susceptibility-based cloud seeding strategies, finding that by deploying MCB over the 5% of the ocean surface most susceptible to cloud seeding, they get these uneven cooling patterns and La Niña-like state. However, by targeting least susceptible regions over a larger percentage of the ocean, they're able to get a more uniform cooling pattern and also avoid triggering La Niña. They find that the 20% least susceptible scheme is the most uniform impact of the experiments they tested. So these are the cloud seeding masks from Chen et al. 2024. And this study uses monthly varying masks. So the top is for December and the bottom is for June. Note that the 20% scheme largely covers the wintertime mid-latitude regions, whereas the 5% scheme largely covers those tropical and subtropical regions, which is what we want to move away from. So we adapt the 20% scheme into new cloud seeding masks, which also cover 20% of the ocean surface, but over more uniform regions, largely within the mid-latitudes and a single hemisphere at a time. And we simulate MCB with CESM2, fully coupled with 3D ocean and active land and sea ice. And for this project, we don't inject sea salt aerosol, but actually just simulate MCB by artificially increasing the cloud drop number concentration of clouds within the boundary layer to 375 per centimeter cubed within the model grid boxes specified by our cloud seeding masks. And our MCB experiments are initiated in 2035, which is when they branch off of our control experiment, which follows SSP2 4.5. And our target is to restore present day or control 2020 to 2039 temperature and precipitation conditions. So we first started our study with shorter sensitivity experiments testing the deployment of single hemisphere MCB within the months of local winter and summer, which are expected to induce different levels of cooling. And the surface temperature response of our MCB experiments here compared to the present day level suggests that summer seeding leads to a significant amount of cooling, up to 3 degrees Celsius in some regions, but the cooling patterns are non-uniform, largely cooling the seeded hemisphere. And our winter seeding strategies lead to a more uniform impact on temperature, but there is minimal cooling achieved here as the surface temperature response resembles that of SSP2 4.5. And we also consider the impact of our experiments on precipitation rate, specifically focusing on whether or not we shift the ITCZ. So the graphs here just give you an idea of whether or not the ITCZ is shifting north or south. And we find that these summer seeding strategies shift the ITCZ toward the opposite hemisphere MCB is deployed, so shifting toward that warmer hemisphere, whereas the winter seeding strategies do not demonstrate that same shift. And we confirm this with the spatial distribution of precipitation rate response, where we find that the summer seeding strategies lead to changes in precipitation along the equator, where that ITCZ is, whereas the winter seeding strategies lead to little precipitation rate response, which is statistically significant. So the results of our sensitivity experiment suggest the local summer seeding strategies lead to these undesirable side effects, whereas our local winter seeding strategies avoid the side effects, but they don't produce enough cooling. So we create 2 new scenarios in which we extend MCB into the fall and winter months for 6 months of the year, and we run these simulations from 2035 to 2069, and these are still single hemisphere experiments. So we find the fall plus winter seeding strategies lead to a larger impact on temperature than the local winter only strategies, but the cooling patterns are non-uniform, largely cooling oceanic regions. And we also see that the 2 strategies here shift the ITCZ, so we deem these strategies not viable for climate intervention. So to avoid these side effects, we combine the fall plus winter schemes into a single scheme in which MCB is deployed for each month of the year and for 6 months of the fall and winter in either hemisphere. And we find the fall plus winter in both hemisphere scheme and 20% least susceptible scheme from Chen et al. 2024 demonstrate a similar performance to one another, both maintaining the present-day global annual average surface temperature and precipitation rate relatively well throughout that 35-year simulation, albeit with slightly more intense cooling from our combined scheme. And we also get a more uniform impact on temperature with the fall plus winter seeding in both hemispheres scheme compared to the other experiments that we tested. And we also avoid shifting the ITCZ. And finally, we consider the impacts of our MCB experiments on the El Niño Southern Oscillation with the Niña 3.4 index. Just for the sake of time, I'm going to look at the sensitivity experiments only here. So the percentages shown on the screen here represent the time spent in La Niña from each of our experiments. So each of the sensitivity experiments lead to an increase in frequency in time spent in La Niña compared to the control for that same time period. However, there is an interesting seasonality aspect to this, especially in the southern hemisphere. We find that the summer seeding strategy within the southern hemisphere triggers a larger impact on ENSO than the winter seeding strategy, whereas for the northern hemisphere, we get a more similar impact from summertime and wintertime seeding. So in conclusion, I just want to highlight that the seasonality of MCB deployment is important for climate outcomes. For instance, it can affect the cooling pattern, shifting the ITCZ and ENSO. And again, there's that preprint link if anyone would like to read the paper. And thank you so much. I'll take any questions.
We can have a couple of questions.
Hi, I'm wondering if like you're focusing instead of the most sensitive, the least sensitive regions. Is there another way that you would pick your regions based on their sensitivity that you think would help like maximize the cooling per area seeded and also reduce the effects? Like, do you need to do the least sensitive regions, or is there another spatial pattern?
I think that study that I referenced, Chen et al. 2024, kind of shows that these least susceptible regions are better at avoiding these undesirable side effects than the other regions that have been largely focused on, like the tropics and the subtropics. Does that answer your question?
Yes, I'm wondering what about the 75% in between? Like, have you looked at how, like, patterns of picking those and what kind of results it would give you?
I haven't looked at that specifically, but in the Chen et al. Paper I mentioned, they explore a couple of different seeding areas, so from like 10 to 40% of the ocean surface. So they do kind of explore some different regions that are being seeded, but the 20% scheme was more uniform in its impact, which is why I based my maps off of those.
Well, thank you.
Thank you.
Nice talk. I'm curious, and maybe from the last MCB talk as well, given the sensitivity to localized regions, do you have a sense of like what the likelihood of transport into a sensitive region might be if these things were deployed, I guess? Does that make sense?
I'm not sure I'm understanding your question.
Yeah, so if like you emit in the mid-latitudes, for example, and you have a tropical cyclone, you could, or some sort of circulation feature that could bring those aerosols or marine cloud brightening compounds into the tropics, right?
I think the idea of the mid-latitudes is to kind of place this along the storm tracks, if I'm remembering correctly, so that it should kind of distribute that cooling from the mid-latitude regions.
Okay, thank you.
Thank you.
All right, now we conclude our session. Let's thank all the speakers and the poster presentators one more time. So after the meeting, if you have any questions or comments, you can send an email to me, Sarah, and Ayla. And if there's any activities currently going on at CVCWG, if you want to participate, just also tell us. Okay? And thank you, and hope you enjoy the rest of the workshop.
start? All right, hello everyone. We're going to get started with this optional session on the faculty network for teaching. Thanks for taking time out of your lunch break to come and hear about this. So I guess Cecile is going to kick us off introducing what this is.
Does it move? Yeah. Okay. Yeah, then the first point, it's what it is. Before we start, if you have any question, we were told you should use the microphone, even that we are a small group, because this is recorded and we can have some people online. Then basically we are establishing a faculty network for teaching with CSM. And the goal is really to support exchange of information and resources to help faculty that want to incorporate CSM into the classroom. And we have a really good example here. Jen has been teaching with CSM since 2011, 15, since 2015. Then what we have done so far, we sent a survey to look at what are the needs and what are the interests, and we got like over 70 faculty that responded to the survey. Then we held some virtual forum in March and in April, and we gathered feedback. And based on the feedback, we created a website with some information, and we will give some information about the website here. And today we are meeting here in person to present this effort. Then what we have done so far, then this is basically the insight of the survey. We had 69 replies from 60 different institutions. And also among the people who are using CSM for teaching right now, we had 30 people that use derecho and 9 that are using university cluster. And we asked them what are the barriers to use CSM in the classroom. Some people had a problem that CSM is very expensive. They had also limited capacity and time to build a curriculum with CSM. Some lack computer resources. Some say that it was also very difficult to port CSM into the local cluster. And also sometimes the integrated students don't have the skill to process the output and also to run the model. And then they were also interested in using the CSM modeled output. You know that we have a big bank of run that people can look at the lens, some simulation. And then the answer was, yes, people are interested, but only if they can select from or modify previously created analysis exercise. And also they were interested in using the CSM output, but basically in the framework of multimodel ensemble. Then based on all this insight and the discussion, we create, in response, we provide a centralized location, and this is the website over here. Still in development, we are adding still stuff, and each time when we add a new section, we put the new date, then you know if anything has been added since your last visit. What is on the website? Then first, we have some information about the computer resources. For example, the people didn't know how to request a classroom allocation on the ratio. If you are in the state and you want to use CSM to the university for class purpose, you can have an allocation. How much is it? You know the size? 500,000 core hour, that would be for your class. Also, we have put some porting instruction, and there is also some information about the container. It's available soon, but I think you posted something last night. And also we provide here the tutorial material that we use for the CSM tutorial at NCAR. The CSM tutorial is this 1-week tutorial that we have every year during the summer. We have lecture to simulate the climate, and we have also practical, and I'm sorry the color are not really good here, but we have also practical material to run CSM. Then the lecture, all the slides are there. There is also YouTube video, then we are providing everything that we have there. We are also providing a CSM tutorial at AGU. It's a smaller tutorial, it's a half-day tutorial, and it's focused on running really CSM. We don't introduce any lecture, but this is a very basic lecture, what CSM is about. But we have practical material that we run on the Amazon cloud. And also we created a forum, discuss CSM forum for faculty, and there will be a link on the website if you want to have questions. And I think I'm going to let Ayla.
Yeah, so like Cecile said, we've kind of created this. There's a forum, the website. We also have this Google group. So if you're interested, please join the Google group. And the idea here is that for faculty to connect with one another and share information about their classes or their experiences with using CSM, not necessarily for us to be giving information, but for everyone to be kind of connected to each other. So please join this, and if you have trouble finding it, you can contact us or Elizabeth after this session. So what are we going to do now? Well, we're going to try and build this community of people that can get together and start talking about teaching with CESM. We're also going to fill out the website more. If you go on the website, you'll see that there are things that are not complete yet, like these sections here about configuration options and computational performance. But there are other things, like Cecile pointed out, that are on the website. If you have things that you think would be really useful information to know for the purposes of teaching, please let us know, and we'll endeavor to add that as well to the website. One thing we're trying to do in the coming months or so is to kind of set up a pilot program. So looking for a few individuals who are really planning to kind of develop a class using CESM, where we would guide you through that whole process of applying for computing time, setting up the model for your experiments, and then using the model with your large class of students. And so the idea would be that these individuals who get that experience could then kind of maybe pass on some information to the rest of the network. And so the idea here is not that we would kind of develop a class kind of in terms of the science, that's kind of for the professors to do, but that we would guide you through how to get CSM up and running for the purposes of your class, and what the best options would be for that, and how to get the computing time. So if you're interested in participating in that pilot program, like I said, we're looking for a few individuals who are wanting to develop a class and get the resources and then go through with that with the class. Please contact Elizabeth, and her email is up here on the slides. So I think that's all we have in this kind of presentation of what this is. Like I said, this is not for us to kind of be providing classes, but more to be kind of facilitating faculty talking to one another and gaining experience with using CSM in their classes. And we have Jen here, who has a lot of experience. I don't know if you want to say a few words about your experience, and then we'll have more time for discussion.
Yeah, hi, I'm Jen Kay. I'm a professor at the University of Colorado, and I've just been helping with this effort a little bit. We did have a couple of online discussions too, and I know some of the folks in the room were also online for those. And it was clear that there's a lot of people using CESM in the classroom in very different ways, and so it probably depends on what kind of role you have at your university, whether you're going to teach a class on numerical methods, or you're going to teach a class that's environmental science for non-science majors. There's a full range of things that we teach. I guess I'll just comment briefly on what I know best, which is what I did, which was to develop basically a model hierarchy class. So we start with just, zero-dimensional energy balance model, move to one dimension, add poleward heat transport, and then kind of culminate at the end of the class with running CESM and students doing projects. And Cecile and I worked really closely together to kind of develop those materials. I taught it this last year. So that was like for students to run experiments on derecho, to answer an authentic research question. Obviously, these questions were very parsed, right? It's a mixed undergrad, grad class. But you can ask some pretty fun questions, like some of the students have CO2 immediately and just asked, how long do you need to detect that? And so they were doing this in CESM2, and turns out if you have CO2 from 2025, it doesn't take long to detect it in the climate system, right? So those are the kinds of things you can build in that, and the amazing thing about CESM is some of the ways that you can change huge aspects of the model are just a single line of code. And so it's not a huge computational lift. We had students who had zero high-performance computing experience come in, run the model, and do experiments with it, which was really cool to see unfold. So I'm really happy to chat with people and happy to help support this pilot program as people need. Obviously, developing the materials, that's a lot of work. I'm happy to share, but probably I don't want to just post it online for all my students to copy the answers. Anyways, you get where I'm going if you teach. But yeah, hopefully that's helpful to hear just a little perspective from me.
And this is what, yeah. And also what I want to add is that sometimes it's hard when you are alone in the classroom. How many students did you have?
Yeah, there's 25, 24.
Yeah, then she was with 25 students. And then it's kind of tricky if you have people that are completely clueless with Unix and how to open terminal. But then you were teaching using through the Jupyter Hub. And then they were opening the terminal in the Jupyter Hub. It was for everybody. You had people that were running CSM from the tablet. They were students. I was amazed, but what they can do. And then they can, it's to be afraid about installing from many platforms, different terminal and helping with the student with this, then using the Jupyter Hub can really help to avoid all this issue.
I also had them working, which really helped because you could have a survey about what students' experience was before. And obviously you don't want to teach necessarily the whole time with the experienced people kind of helping the inexperienced folks, but I found that at least for getting this off the ground, it really helped to be intentional about who was working with whom in the groups.
So while most of the work here goes into the development of curriculum, we just want to say on the technical side, we want to lower those barriers. Like a lot of the issues that people noted that they have is how do you port it, how do you get people running, people who don't know Linux. Some of this, even if it's not within the scope of your class, if these are issues you struggle with, reach out to us because we've talked with Sizzle about putting together like a Unix basics class or a Jupyter basics. These are all things we want to hear from you as what we can do to run training before you get to your class to teach the science. So just speak to us. Any technical barriers, we're happy to try to work with you. I'll leave the science barriers to you guys. So yeah, thanks.
If there is anybody online, you can post a question on Slido. We are sorry we could not have a Zoom, interactive Zoom, but there were too many people to be able to do an interactive Zoom.
Does anyone have any questions or any things you'd like to see within this network? Yep, please come up to the mic.
Great talk, by the way, but I'm coming in as a GVP fellow, so my background isn't necessarily in these higher powered computers, so I am sort of getting a crash course on Unix, Linux, and just even hearing how in the classroom it's navigated by group activities. I just know coming in, I've definitely felt the need to sort of definitely watch, but a combination of reading about Unix and Linux and the history, and then combining, I have previous R background and everything, so hearing that you also want to decrease some of those technical aspects when you're just really coming in the room. It's nice to hear that, and just as someone coming in with sort of a more GIS background, yeah, I feel the benefit of, you know, sort of, how can I say, I guess the learning from the classroom and going from the student up and sort of really observing, you know, working in a group and everything. So just thank you for your work on that, and it's nice to hear about it, so thank you.
Yeah, I'm happy to share. I mean, literally, students didn't have any experience at all. And so I would give like 2 lectures, you kind of prime them as the semester goes, right? So by the time you're coming in to run CESM, you've already heard me wax and wane about Unix a couple of times. And you had to log in, you know? We figured out logging in. That was a whole day, just logging in, you know? But then I did a lecture, and it worked well because if you have an hour and 15 minutes of class time, you don't necessarily want to spend the whole time just lecturing, right? If you spend 15 minutes or 20 minutes logging into a supercomputer, ooh, how fun is that? So anyway, students really enjoyed it, and I think building it up, I'm happy to share that kind of sequencing.
Thank you. This is really great, so thank you for all this work. I was actually very interested about what you said, because the way I was thinking about developing a class was really more starting from the 0-dimension model all the way to the 3D, and I was worried that 3 credits, it's a lot to both teach students, you know, how to do the analysis and how to run the model and how to, you know, all the physics behind it. So maybe, did you, in your experience, that was enough? Like 2 1 hour 15 lectures a week was enough for them to get on board with all of this?
I think it depends on the major. So we have an atmosphere and ocean sciences major, and this class is a methods class that's taught for seniors. So they've already taken a bunch of atmosphere and ocean sciences. So it's not, there's a couple of minors that took it that probably have had a lot less background, but I would say, you know, they had a lot of the physical background. They just hadn't seen it maybe written out and seen this kind of hierarchy approach. And so, yeah, that's where I think knowing your institution and kind of knowing your students, you're going to know best how to set things up and how much to leave to the students and how much to kind of do in the background to make it really straightforward for them. Yeah.
Okay. Well, if you could share your material, that would be absolutely lovely. Thank you. Yes.
Other thoughts? Anyone want to volunteer right now for the pilot program?
Yeah.
Okay. Yeah, I mean, let us know also like what time frame would be the right time frame for you when you're developing the class, and when you would like to do that, and so then we can plan like when is. I mean, no, you don't have to right now. Okay. Yeah. Sounds good.
First of all, I also wanted to say that I really appreciate this effort. Well, Jen, I was in your climate modeling class, really learned a lot. It's a cool opportunity for students and then for visitors like me. And I also want to mention that when I was a graduate student, I learned how to run CSM from a climate modeling class that Cecilia Bitts developed at University of Washington. And for a long time during my graduate and postdoc research, still refer to CC's instructions for how to run prescribed ST simulations. So it was super helpful. But then my question is, for this kind of classes, as a student, I benefit a lot from this student project at the end. So you can come up with your own ideas, adding ST anomalies here, or changing fields, or flatten Antarctica, something like that. Then it's a cool opportunity for students to learn. But then on the other side, as an instructor, I was wondering, would be possible to get some technical support from NCAR experts to help students achieve their goals? Because I imagine for a class like 20-ish people, they might have very diverse interests, and some of the simulation, I'm afraid I might not be able to really help them to achieve the specific simulations. So in that case, would it be possible to?
Let me comment quickly that I do have them brainstorm their own simulations. They have to submit a proposal on what they want to do. And then I steer them towards things that are really easy. So there's, there's a lot of instructional kind of guidance. If somebody wants to flatten Antarctica, it turns out that's not that hard. But other things are actually harder to do in CESM, and that's where I think like my own technical background really helps a lot, because I have a sense of what you can and can't do. They also do all of their projects in groups. So even if you had 25 students, I only had 5 projects, which makes a big difference, because basically I do all of the projects before they do the projects, because I want to make sure that they work. So yeah, I think getting some support from NCAR, or maybe a list of, these are the types of projects that are easy to do, and here's how to do them, so that it feels authentic to the students. Maybe they quarter CO2 instead of having CO2, but you have the instructions on how to do it, and you know that it works, kind of thing.
What was useful at the time is that we knew a little bit about the project that they were doing, they were going to do. Then we do only 2, we instruct how to run CSM in 2 lectures, and it's very, very short, and they can run it. But then we will target, I know somebody wanted to change CO2, then I explain how to change CO2, I put this. I will customize the slide, but we can, or how to change the SST to, at the end. And what was, I remember some students wanted to do projects that were not difficult to do, but technically it would be easy, but it will require much more than the amount of computer time that they had for the classroom. Then it was also something to know. It was not this time, but it was the time before. I remember students wanted to run stuff that would take much more computed resources that we had. And then it's good to have some expertise, but then it's something that probably NCAR can help to say, is this project is possible with this amount of computer time?
And I think the hope is that this network would be somewhere where you can all learn from each other in experiments that you've done. So of course you can post on the CSM forum, but then this network is maybe also another place where if you're trying to do a simple experiment, you can ask other professors that might have already done it, how they did it. And maybe if that really takes off, we could come up with a list on the website of simple experiments. So it's not the whole class, but just how do you change CO2, and have examples there.
But now that I think about it, because what you say that you don't want to post everything on a website because the student will find a solution and just do copy-paste, then maybe we need to have something that's behind a password or password protected for this group. I don't know.
Yeah,
I didn't really think about this, but it's...
I feel like it depends on whether they're being tested on the technical things or the interpretation. Like, if it's just, if you want them to find out how to change CO2, then yeah, that's a problem if we just put it on the website. But if it's just for the teacher to know how to do it, then I feel like that will be okay. We can see how it goes, I suppose.
Sorry, 2 dumb technical questions. So the first one, you said that you're having the groups working, do like a project together. But then how does it work for the accounts? Do you have an account per person, and then they decide one of them that runs the whole thing?
Yeah, so when Cecile and I did the, like, how do you run CESM, everybody had to run just the vanilla base version of the model. And that was like 10% of the project. You ran the base, and everyone had to do that. And I just looked in their Scratch and made sure they produced some output, and, And then with the projects, so everyone ran the model. But then with the projects, only one person ran the model. And the nice thing there is, with these groups, I have them self-report back what they contributed, and I had them make a plan together. So, if somebody's strong and technical, they'll run the experiments, and that's okay. Everyone ran the model, right? But some students will be more excited about the technical parts, and some will be more excited about the plotting of the output, and others will be more excited about writing it up and interpreting it. And I mean, it's really nice. That's how things work in the professional spaces a lot. You're not necessarily doing all of the things, and so I think it's a good learning exercise for them too, to figure out what they like, or some chose the thing they found challenging because they really wanted to learn it, and they knew if they were in charge for their group, they'd have to do it. So yeah, you see a lot of personalities come out in this.
other part of the question, because in our department we have Natalie Mowell that has been running the CESM tutorial, and I think it was last year that somebody sort of by mistake spent the entire classroom allocation. So is there a way?
Yeah, this was not the issue. I can't
okay,
what the issue was. It was because the instruction was so good last year that most of the students finished the project, while in previous year only a very small proportion will finish. Yeah, it was, and it's why we run out. Yeah, it was not, at the beginning we were afraid a single person use everything, but it was not the issue.
Okay, so is there a mitigation strategy for this? Right?
Yes, so I do this with new users all the time. You can take a project code and create a sub-project which has only a limited amount and then add to that all the time. So it mitigates against disaster. We're happy to help with that, but you can do it right through SAM, yeah.
Okay, so I've been teaching, I created one small modeling course, which I limit student number, try to limit student number below 10, because I asked them, each of them, to set up their own sensitivity experiments with CSM, so they have to come up with their own small scientific stories and change the parameter or the code and do the test. And because I'm also giving the course based on my own small cluster, so I asked them to run only for 2 years. They have to find something to do so they can see the changes in like a short time period. So that's what I've been doing, and I found, you know, when I taught about the basics, about Earth system modeling, students seem to know all of it. But when they start to get practice, then they found it so hard. I have to teach, I have to spend one class on logging in the supercomputer cluster and teaching them the basic commands, because there's an undergrad course. So the basic commands for Linux system, like for one single class. And also, my students found the most difficult part would be the data analysis part. Because, you know, even though I show them the tools to visualize the output, they don't really understand the long name of those variables. And even they can read it, you know, the words, but they don't know how these variables are really calculated in the code and how to really interpret the change in terms of what processes was considered in the model. And I think it will be quite helpful if the analytical tools for CSM covers more variables and have a better, say, explanation on each variables or most popular variables. And so, for example, I'm working on the ocean biochemistry part, and I try to limit my students' topic within the ocean modeling part, but still sometimes it's very difficult to explain all these variables and how they are calculated to each students when they are doing 10 different experiments.
I appreciate that comment very much, and I will say it's really hard in one semester to teach everything that's going on in CESM. So just admit defeat and don't worry about it, right? I think you want to give them a flavor of how much complexity is in this model and the types of processes. So if you can go deep on a couple of things and really explain how they work, I think that I find that really successful. But also, I lean into things like the global mean temperature or things like that, so that I'm not necessarily having to explain the details of how every single, process in the model works. There's no way that you're going to do that in a single semester. And so that's my perspective on it. And I'm curious, in terms of the analysis tools afterwards, I'm building simple scripts from them, and they're analyzing output from models as a part of their homework before they get to run CESM. So they know how to calculate a global mean and make a zonal mean and really simple things by the time they get to run CESM. And if they say they want to make some really complicated plot, I'm like, do you know how to make that plot? No, okay. Do you think I'm gonna make that plot? You know, like, let's talk about the budget of time. And so like there's a lot of really practical conversations that you have with them, and I think they leave with a lot more appreciation of first what they've learned, but also how much they don't know and how much effort really goes into the more complicated experiments and diagnostics and things like that. I don't know if that's helpful, but yeah.
Yeah, I totally agree with you, and I did similar things, but you know, right now we have some ocean modeling competitions going on in China, and they use CSM as their basic tool, trying to push students to compete, like setting up CSM runs, configure it, and optimize the simulation. So students really push me into more complex setup. Like they want to learn more about the model, and so that's why they want to explore. Like I have to spend more time. That's quite time consuming for me. So it'll be great if there's additional help from the community.
The tutorial is also an amazing resource for going deep on any particular component model. And then once they're asking questions that are so deep that require reading the scientific literature, send them to the scientific literature. You don't need to be an expert about everything. Like, I think that's actually really empowering for students to realize that their professors don't know everything, right? Like, I don't know everything. No one does.
Yeah. And the one thing I was going to add on this, although maybe there's a caveat now, is you said you run 2 years just from limited compute time. I would prefer, broadly speaking, for nobody to feel limited by compute time. If you have 100 students and the classroom allocation is enough, come talk to us. We're happy to try to work with CISL to get you more. That shouldn't be a limiting factor. Running for 2 years is sometimes really good because it's faster, but if you wanted to run for longer, we can do that. The one caveat that I don't know, you mentioned students in China. I don't know if you're at a university here or in China, but if there are, there may be limitations on the classroom use, so I'll have to check on that. If we don't have any problem with getting access for students from China, but if the university is, if you're in China, then that might be a problem. I'll have to check on that. So yeah, but come talk to us if you need compute resources. All of our tutorials, like if we do the training on Linux, that is open to anybody, even if they're from China. We've had Chinese students before, so yeah.
Yeah, and just to mention again that as well as the big CSM tutorial, we run these half-day ones at AGU. So if you have students that are going to AGU, they could sign up for those. Did you have a question, Flavio?
Also is volunteering with a really academic question, so I'll take this opportunity to make a brief advertisement for another dimension that is available that NCAR can provide. And I hope I'm not freeloading too much on this wonderful work that you're assembling here, but this may be more of an advanced topic, but if any of your students or if you're interested in data assimilation, CESM can be used to do data assimilation work. And we also have an extensive tutorial that can take students from simple models, just 3 variables, the Lorentz butterfly model, all the way up through CESM to do data assimilation. So we'd be happy to talk to you. Thanks.
Yeah, any more questions and any more interest to be in this pilot program? And you don't have to decide on the fly, but...
Is that a question, or?
Can you come to the mic, because...
I was just raising my hand for the pilot program.
Yeah, then please send an email to Elizabeth Fairclose. It's the email that you receive. All the email, and yeah. It will not be hard to find her secret email. I really want to reiterate that I have been in a class since 2015, and as a professor teacher. So it's amazing what the student can do. Yeah, it's really fun to see them.
All right, I guess we'll have another 10 minutes before the session starts. Thanks again for taking time out of your lunch break to join this.
This is perfect.
Oh, you brought your laptop up?
Yeah.
A different
There you go. It doesn't, I'm just going to keep it here.
Well, I have to bring mine up, though.
Or you can give me your presentation.
How do I
Send me your presentation
Okay.
on Drive.
Send a copy. Okay, I'll email it to you.
No, but I'm just, are you presenting as well?
Yeah.
I'm just using
The slide.
this.
Okay. Use
And
the
then just
I
go,
might attach it as a link.
like, because I have my script.
But
up
how
there.
do you put in here?
Oh yeah, there we go. So that's mine.
Well, how do you
But
connect to the computer?
It's not connected. I just manually change both
Here, let me send it
so that I have
through.
my script on me.
Let me send it through.
Sorry, what were you saying? Sorry, what? Oh, yeah.
There's no presenter view if that's,
There's no presenter view, so if you don't need a presenter view on your notes, you can just present. Otherwise, you can bring your laptop with you. That's what I'm doing.
Yeah, I'm sending mine to root drive.
And that way you can have the notes with you.
Okay. I'm sending, it's like a link, so you're gonna have to like
They didn't
it's in person? Not yet. Give me. Let me just introduce you first, and then you can start. Okay. All right. Welcome everyone to our Ocean Model Working Group session this afternoon. Let me just, before we get started, remind you to remember the UCAR Code of Conduct, consider new ideas, encourage innovation, offer constructive feedback, acknowledge teamwork, show appreciation, and share the air. The usual, and I'll thank you in advance for doing that. So our first speaker this afternoon is Ting-Ting Zhu, talking about evolving Southern Ocean overturning in warming climates.
Thanks for having me. My name is Ting-Ting Zhu from UC Riverside. My advisor is Professor Wei Liu. Today I'm going to talk about evolving Southern Ocean overturnings in warming climates. The westerly wind stress can drive equatorial equipment transport, which can generate the Euro-rearming smog, also called deconsel or wind-driven overturning circulation. This overturning circulation is characterized by equatorial flow at surface and the polar and the upwelling of the deep water. The upwelling of deep water can steepen the aspinal slope. The baroclinic instability can flatten the aspinal slope and generate the eddies eddy-induced overturning circulation, which counteracts the Euro-rearming smog. The eddies induced smog act to compensate for the Euro-rearming smog, regulating the residual overturning circulation. Therefore, the Southern Ocean overturning circulation is a residual result of these two opposing overturning circulation. The eddy-induced smog can partially compensate for changes in the Euro-rearming smog induced by shift in zonal wind stress in the southern hemisphere. However, the degree of compensation is uncertain and influenced by surface buoyancy. In future climate warming with changing wind and changing buoyancy, the eddy-induced and the Euro-rearming smog response and the complex interactions and compensation between them are still uncertain under future climate scenarios. These uncertainties limit our ability to predict Southern Ocean's contributions to climate change, highlighting the need for further investigation. The Southern Ocean smog has changed in recent decades. Here we use ECHO dataset from 1992 to 2017. The figure shows the zonal mean westerly wind stress trend shows red color, and its climatology shows black color. As you can see, the westerly wind stress has a polar shifts and intensification trend. This trend also can see from its spatial map. Associated, the Euro-rearming smog also trend with a dipole pattern with an intensification trend in the south and a weakening trend in the north, indicating a polar shift and intensification trend. The eddy-induced smog has an intensified trend which can provide partial compensation for the Euro-rearming smog. As a result, the residual smog mainly reflects the trend of the Euro-rearming smog. Besides changing wind, we also can see the buoyancy forcing has changed, which can contribute to the Southern Ocean smog dynamics. In brief, a polar shift and intensification trend has been observed in the Euro-rearming smog, while the intensified eddy-induced smog provides a small compensating effect. To see whether this trend will happen in future climates, we further investigate the Southern Ocean smog response in past and future warming climates using CIMA 5 and CIMA 6. For future warming climates, we focus on SFP 5.5's high emission scenarios compared to historical. And besides, we also focus on the past warming climates, in warming period, which can be considered as an analog for future climate projections. For future warming climates, here shows the zonal mean westerly wind stress. In SSP 5.5 shows red color, and in historical shows blue color, and the difference shows black color. can see the westerly wind stress shift pullover and intensified, same as what we observed in recent decades. Correspondingly, the Eurasia mark also trend has a dipole pattern with an intensification in the south and a weakening center in the north, indicating a pullover shift and intensification. The eddy-induced mark has a complex pattern, has a tripolar pattern with a strong weakening center, which can provide strong compensation for the Eurasia mark. Because of this strong compensation, the residual mark shows a uniform intensification. In the past warming climate, we also can see the westerly wind stress shift pullover, but the westerly wind stress weaken a little bit, which is different from what we see in the future climate. Correspondingly, the Eurasia mark also shifts pullover with a strong weakening center due to the weakened in westerly wind stress. The eddy-induced mark provide a weak compensation. As a result, the residual mark shows a non-uniform intensification because of the weak compensation from eddy, which is different from the future warming climates. In the future warming climate, the Eurasia mark undergoes a pullover shift with strong eddy compensation, sustaining a uniformly intensified residual overturning. The pullover shifting has been confirmed in the past warming, but with weaker eddy compensation leading to a non-uniform intensified residual overturning. Besides changing wind, we also investigate how changes in buoyancy forcing affect the Southern Ocean overturning circulation. Because the eddy-induced overturning circulation is proportional to the isopinal slope, so we further analyze the isopinal slope change in both future and past warming climates. As you can see, there's flattened isopinal slope in both future and past warming climates, which can explain why there's weakened eddy-induced mark. The flattened isopinal slope is caused by the change density flux. The top right panel shows the total density flux, which comprises the density flux due to the heat flux turn and due to the freshwater flux turn. Can see compared to historical, there's a decreased density flux in future warming climates, and this decreased density flux is mainly due to the heat flux turn with a small contribution from the freshwater flux. Same story happened in past warming climates. Therefore, the weakened eddy-induced mark in both future and past warming climates is driven by a flattened isopinal slope primarily caused by increased surface heat flux. Associated with the buoyancy forcing change, the water mass formation also changed in the past and future warming climates. This figure shows the area for surface density in SSB 55 shows red color, in historical shows blue color, and their difference show as black color. So compared to historical, there's a lighter surface density in future warming climates. If you look at water mass transformation, both historical and SSB 55, there's a lightening transformation, but the lightening transformation shifts northward in future warming climates. When water accumulates in a certain density of decrease in a certain density, the imbalance should be resolved by the downwelling or outwelling. Because, for example, because there's lightening transformation, water in a lighter density will accumulate, which can drive downwelling. Because the lightening transformation shifts northward in future warming climates, the downwelling and outwelling also has been shifted northward. As a result, compared to historical, you can see there's a downwelling and outwelling on the both sides of around 50 degrees south, which is related to the weakened eddy-induced mark, as we mentioned earlier. And besides, around the Antarctica, there's a downwelling anomaly, which support the bottom water mass formation in the Ross Sea and Weddell Sea. Similarly, in the past warming climates, we also can see the lightening transformation shift northward, but it has larger displacements, as well as the outwelling and downwelling has larger displacement. The associated buoyancy forcing changes have driven northward outwelling around the Antarctica with larger displacement over the past warm period, promoting the bottom water formation in the Ross and the Weddell Sea. Associated with the overturning circulation change, the response of Southern Ocean ventilation also changed. The ventilation can be measured by the ideal edge, which represents the average time since the water last resided in the surface layer. In both future and past warming climates, we can see there's enhanced ventilation in the subduction branch. This enhanced ventilation is caused by the intensified overturning circulation and thereby the enhance the subduction branch. Compared to the future warming climates, the subduction is enhanced and deeper and widespread in past warming climates. This characteristic also can see from each different models, especially from IPSL simulation. Therefore, along with overturning circulation trend, the ventilation intensifies in the subduction branch, especially during the past warm period. In conclusions, first, under high emission scenarios, the urea minimal shifts polar with strong eddy compensation sustaining a uniform residual overturning. In the mid-Pliocene, a similar shift occurs, but weaker eddy compensation leads to an uniform residual response. The associated buoyancy forcing trend have driven up northward upwelling around the Antarctica with larger displacement over the past warm period, promoting the bottom water formation in the Ross and the Weddell Sea. Alongside trends in the Southern Ocean overturning circulation, the ventilation linked to the subduction branch intensifies, particularly during the past warm period. This intensified ventilation has critical implications for climate feedbacks, impact ocean heat uptake, carbon storage, and air-sea interactions. That's all about my research. Thanks for attention.
Questions, come up to the mic, please. List here in your last point, critical implications for climate feedbacks, et cetera. I wonder if you could speculate on what some of those might be.
This slide?
No, just the very last slide with your 3 points on it.
Oh, last slide.
The conclusions.
Oh,
yeah,
conclusion, sorry.
Yeah, we were just on it.
Oh, it's out.
Is it gone now?
Yeah.
Oh, we're back. Yeah, just here. So, critical implications. I wonder if you could speculate on what some of those critical implications might be.
You mean the climate feedbacks?
Yeah, any of them.
Oh, I see. Yes. I think the enhanced. Sorry. I think the enhanced ventilation. That's the ocean can uptake more heat, heating from the atmosphere, so they can, I think, can modulate the global warming. That's one part.
Can you go to your conclusion slides, please?
What? Oh, conclusion.
The first point is there's the shift in the wind.
Yeah.
And then you say that enhances the buoyancy forcing around Antarctica. But none of these models, so if you have power shift on the wind, you have more warm water going towards Antarctica. And none of these models have an active ice shelf or ice sheet model couple. If they were, then you would have extra buoyancy forcing around Antarctica. You think that would change your second bullet point?
Mm-hmm. Can you explain a little bit?
Like, none of these models have an active ice sheet. So they're missing, if you were to drive more heat towards Antarctica with an ice sheet model, you would increase the melting. And then you would put more fresh water
Yeah.
around Antarctica.
Yeah.
But these models don't have that.
Oh, I see.
We can talk offline again.
Yeah, 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 sure. Thank you.
Anthony? While Anthony's coming up, we will have a discussion at the end. Last session, the last talk in this session is discussion. So our next speaker is Anthony Thomas, and talking about evaluating Southern Ocean heat uptake. Go ahead, Anthony.
Good afternoon. First of all, I would like to thank NCAR for having me here. My name is Anthony Thomas. I'm a third-year graduate student at the University of California, Riverside. Today I will be talking about evaluating Southern Ocean heat uptake in high-end low-resolution climate models, with specific emphasis on the HARGEM 3GC 3.1 and CESM 1.3 models. This project was done in collaboration with my PhD advisor, Professor Wei Liu. Okay, I would like to start with a brief introduction on why I was focusing on the Southern Ocean. So we know that in the recent decades, the Southern Ocean is going through a lot of changes. It includes the warming within and as well as north of the Antarctic circumpolar current. We also seen the Southern Ocean is getting warmed all through up to the upper 2,000 meters as well. In addition, we're also seeing the Southern Ocean is showing trends of freshening south of 45 degrees south, and it is also extending into the ocean interior as well. In addition, we are also seeing increase in the zonal wind throws in the southern hemisphere, which represents intensification of the westerly winds in the Southern Ocean. And in response to that, there was an increase in the eddy kinetic energy in the Southern Ocean. So which means that it's really important to have the mesoscale eddies resolved in the ocean models while we are dealing with the Southern Ocean dynamics. And it was found that the explicitly resolved mesoscale eddies reduce subsurface ocean model warming drift, improving the realism of water masses relative to those in the standard models. And a study by Hewitt et al. 2017, they mentioned that the accurate simulation of climate change responses in the Southern Ocean was reported to be critically dependent on the mesoscale eddies. So that's kind of the motivation for our study, that we are trying to compare a very high resolution ocean model from the high-res MIP, and compare it with the low-resolution model, and compare both of this with an observation benchmark, and to see how well the resolution increase in the horizontal resolution is helping in understanding the Southern Ocean dynamics. So for as a observational benchmark, we are using 3 observational-based datasets, which are the Ishii et al., IAP, and EN4.2.2. We are analyzing from the period 1958 to 2014 within the region of 30 degrees south to 70 degrees south in the upper 0 to 1,800 meters. And all the observational data are interpolated to Ishii vertical levels for consistency. Moving on to the climate models, we are using 2 different high-resolution models. One is the HARGEM 3GC 3.1 from the UK Met Office, and the other one is the CESM 1.3 by the IAS program. Both of them are participating in the high-res MIP protocol, and we are using 2 different simulations, the historical 1950 and also the control 1950. We are doing a drift correction using by removing the linear trend of the control 1950 from the historical 1950. Looking in detail about these 2 climate models, we have 2 resolutions. We have the low resolution ocean, which is at the standard nominal resolution, that's at 1 degree, and we have the high resolution that's at 0.1 degree, and that's the same for HARGEM and as well as the CESM model. So in order to separate the temperature trends, we are using this heat and spiciness decomposition method, where we are decomposing the total temperature into the temperature changes associated with the heave and the spiciness. So heave is associated with the temperature change that is caused by the vertical movement of the isopycnal layers, and the spiciness is associated with the changes along the isopycnals. So basically, the heave is mostly correspondent to the changes that are influenced by the zonal wind stress or surface wind forcing changes. And the spice, or the changes along the isopycnals, are majorly driven by changes in the surface heat fluxes. So moving on to the results, this is, at first I'm showing the ensemble mean of observations, that's in the panel A, and in panel B and C, that's the hard-gem model, the high resolution and low resolution versions of the hard-gem model. So first of all, if you're looking into the observations, we can see that the observational-based datasets are consistently showing a cooling south of south of 55 degrees south in the upper 100 to 200 meters, and also to the north of 55 degrees south, the observations are showing a warm tongue that is extending equatorward. When comparing it with the hard-gem model, both the high resolution and low resolution versions are failing to reproduce that cooling that we are seeing in the southern part of Southern Ocean. But then the high resolution version is producing a deeper and stronger warming north of the 55 degrees south. And we just did, so like I mentioned, I did decomposition of this total temperature trend into the spiciness and heave components. We then looked into how the heave and spiciness trends are changing in the observations and the hard-gem model at first. So here the central panel depicts the spiciness trend, and the bottom panel depicts the heave associated trends. So what you can see here is that in the observations, the surface cooling south of 55 degrees south is mainly driven by a negative spiciness trends, and the subsurface warming north of 50 degrees south is arising from the heave associated positive contribution. And when you're comparing it with the hard-gem model, especially the high and low resolution models, and specifically looking to the south of 55 degrees south, both of the models are in the spiciness trends, both of the models are showing warming instead of the cooling that we have seen in the observations. And to the north of the 50 degrees south, the warming tongue is associated with the heave component, similar to that of the observations. But then the deepening of the heave component is, the high resolution model is showing more stronger and deeper heave, which is more closer to the observations. We also parallelly checked the CESM 1.3 model, both the high resolution and the low resolution versions. And this figure is similar to the figure 1, where I'm showing the total trend of CESM, high resolution and low resolution with the observations. So here again, both the CESM 1.3 resolutions are failing to capture the observed surface cooling south of 55 degrees south. And they're also underestimating the warming north of 55 degrees south in both resolutions when we are comparing with the observational mean. And the high resolution version is showing a deeper warming tongue, but with a weaker magnitude than the high resolution and the low resolution, than the low resolution and the observations. We also did we then looked into the spiciness and heave decomposition for the CESM model, and similar to hard-gem model, the CESM high resolution and low resolution are showing warming to the south of 55 degrees south in terms of the spiciness. And to the heave, we are seeing an increase, the heave component, similar to the hard-gem model, that's the major contributor for the deepening of the warm tongue. But then it's comparably weaker and shallower when compared to the observations. So given that there is a difference between the resolution-dependent spatial variations of the heave and spiciness and as well as the total temperature trends, we now look into the physical mechanisms that might be causing these changes. Specifically, we start with the hard-gem model. So from this point onwards, what I'm showing is the anomalies with respect to the 1950 control. And here, so the panel A is the net surface heat flux anomalies, with the red line representing the net hard-gem high resolution model and blue line representing the low resolution model. And in panel B, that's the decomposition of the net heat flux into net turbulent and net radiative, with the purple line representing net turbulent and green line representing net radiative fluxes. So jumping quickly into the key conclusions from this slide, when I'm looking into the high resolution models, it's showing a net surface heat flux anomalies, positive net heat flux anomalies from 70 degrees south to 35 degrees south. And these positive anomalies are largely due to the enhanced turbulent fluxes, especially the right and sensible, especially the south of 60 degrees south. And this explains the positive spiciness trend and the absence of observed surface cooling in the high resolution simulation. And to the north of 60 degrees south, there's a continued positive net heat flux, which is driven by the turbulent and radiative contributions. It's aligning with the approaching warming in the spiciness. Looking into the Hudson low resolution version, it shows a weaker net heat flux anomaly south of 64 degrees south compared to the high resolution. And this is because the positive radiative fluxes are being offset by stronger negative turbulent fluxes, leading to weaker surface warming and the spiciness trends south of 64 south. So from 64 degrees south to 45 degrees south, there's an increase in the net heat flux, which is peaking around 57 degrees south, and again, due to the turbulent flux changes. In parallel, we check the surface flux anomalies in the CSM model. So looking into the high resolution version, it's showing a positive net heat flux from 68 degrees south to 47 degrees south, and peaking at around 58 degrees south. And here in CSM high resolution, the radiative fluxes are dominating south of 61 degrees south, and to the north of 61 degrees south, it's the turbulent fluxes that are dominating. Whereas in the CSM 1.3 low resolution, the positive net heat flux from the 70 south to 30 south is peak. We are seeing a positive net heat flux from 70 south to 30 south, which is almost peaking around 56 degrees south, again, driven by turbulent flux changes. And south of 60 degrees south, the positive radiative flux nearly getting cancelled by the negative turbulent fluxes. So the key takeaway from this slide, and if I'm connecting it back to the other slides, is that when we're looking into the surface, the Southern Ocean, we can see like in both the high resolution and low resolution versions of the CSM, both HUDGEM and the CSM, we're seeing a surface warming, and this is kind of like due to the changes in the spiciness component. And when even there are, and it's not uniform actually. There are localized changes in this warming trends, and when we are looking into these surface flux changes, we could see that these surface flux changes are basically aligning with those changes in the spiciness components. And they also are showing these localized changes. So that explains the spice pod, and then we looked into the heat-induced warming to the north of 50 degrees south. So for that, as I mentioned before, the heat component is mainly driven by the changes in the zonal winds. So we looked into the zonal wind changes. Again, it's anomalies with respect to the 1950 control. And so here in panel A, that's the zonal wind stress anomaly with red line representing the HUDGEM high resolution and blue representing the low resolution, and the control is in the background. Panel B is the wind stress curl anomalies with red representing the high resolution and blue representing the low resolution. And C and D are the spatial patterns of the zonal wind stress anomalies in the high resolution and low resolution. So quickly jumping into the main conclusions from this slide. When you're looking into the high resolution models, the zonal wind stress anomalies are showing a positive, it's showing a dipole which is nearly centered around 42 degrees south, with a positive to the south and a negative to the north. And this indicates the poleward intensification of westerlies. And similarly, in the low resolution, we could also see the same dipole pattern, but now in the in the low resolution version, the dipole center is further south, almost like around 46 south, and then the positive is to the south and negative is to the north. When you're looking into the wind stress curl, the positive anomalies in the high resolution are starting from almost, we are seeing positive anomalies to the north of 55 degrees south, which is almost peaking at around 46 degrees south. And then there is the negative curl anomalies south of the 55 degrees south. And in the low resolution, we're also seeing these positive anomalies, but then the positive anomalies are beginning at almost around 58 degrees south. And then it's peaking around like 48 degrees south. And then we have the negative anomalies to the poleward. So, so together with the poleward intensification of the westerlies and the positive wind stress curl anomalies, it is inducing a Ekman convergence, and which leads to the deepening of the isopicanal in this region that represents the deepening of the heave-induced warming in the Southern Ocean, especially in the HUDGEM model. We didn't got the data for the CSM to show here, so I'll just quickly jump to the conclusion here. So these are the conclusions from my study. We have seen subsurface warming patterns. Example, the warming tongue north of 55 degrees south. Both of both the resolutions are capturing, but then the high resolution versions are reproducing the deeper warming chunks due to stronger heat contributions associated with positive wind stress curve anomalies. Surface cooling south of 55 degrees south is absent in all models, and it all simulates spiciness-driven surface warming instead of cooling. And this is linked to the underestimated sea ice expansion in the climate models, causing excess surface heat uptake in the region south of 55 degrees south. And turbulent heat fluxes acts as the main driver of spiciness-induced surface warming, and radiative fluxes play a contributing role. So in general, each of the resolution has its own positives and negatives, and when each resolution is showing a regions and process-specific strength and limitations. That leads to the highlight that we need to, there's a need to be improved, the need for improved surface turbulent flux simulations, CS dynamics, and wind forcing in the climate models to represent much more accurate Southern Ocean dynamics. With that, I will conclude, and thank you.
Any questions? Very nice talk. Yeah. So do you have any hypotheses as to why none of these models get the surface cooling south of 55?
So, all right, okay. So I just looked into the sea ice concentration, and when you're comparing it with the hard SST, so I use a hard SST as an observation benchmark, and in the recent decades, almost like after 1990, the CS variability is showing positive trends in the observations, whereas in the models, they're not capturing that CS variability. So probably due to the decline of sea ice or the variation in the sea ice in the models, there could be more open ocean available, and then more surface heat flux is coming into the region south of 55 degrees south, which might be the reason for that warming to the region south of 55 degrees south in the models compared to the observations.
You are looking at the high-res MIP simulations, right? So if you look at the actual historical simulations that we have done under the Mesa Calip or IHAS project, which are available, we have 10 members, you'll see that at least 3 or 4 of them will get the Southern Ocean cooling. Okay. I don't think that high-res MIP is the right framework to look at this because it has other issues with the TOAs and all that stuff.
Okay.
Yeah.
Thank you for the insight.
All right, thank you again, Anthony. I think we're going to move on to the next speaker.
Yeah. And how do I point?
Yep. Okay. It's Rudra. Yeah.
You can call me Rudra.
Rudra.
Yeah.
Tucker. All right. Next speaker is Rudra Tucker from Wisconsin-Madison. All right, go ahead.
So good afternoon, everyone. My name is Rudra Thakur. I am a PhD student at the University of Wisconsin-Madison in the Department of Atmospheric and Oceanic Sciences. And now we'll be shifting gears to North Atlantic region, and I'll be talking about Northwest Atlantic marine heat waves and whether we need high-resolution models to simulate those events. I would like to thank all of my collaborators and also the Ocean Model Working Group, and especially my advisor, Professor Elizabeth Maroon, for all the support and just being amazing. So what are marine heat waves? Marine heat waves are periods when ocean temperatures stay unusually high, particularly above a certain threshold, and then extend for time. In this talk, I'll focus more on the Northwest Atlantic region for marine heat waves, and this region is especially important because the warming is nearly 4 times faster than the global ocean average in this particular region. It is also shaped by dynamic ocean currents like Gulf Stream presence, which makes it really interesting to study. So 2 most widely studied marine heat waves in Northwest Atlantic occurred in 2012 and 2016. These events stood out because they had unprecedented warming, they had record-breaking warming during those years, and also had significant impacts on marine ecosystem. Both these events were triggered by poleward shift in jet stream, which caused positive anomalous heat fluxes into the ocean, which initiated SST anomalies. And then the ocean advective processes kind of amplified and sustained those anomalies for summer and fall in these different events. This also highlights that there are multiple processes, both atmospheric and oceanic, that shape the life cycle of marine heat waves. And so the ability of the climate models to simulate these events depend on how well they capture these key mechanisms, and that will be the focus. This brings to our question. So how and why do marine heat waves differ in eddy resolving and non-eddy resolving ocean models in Northwest Atlantic region? The impact of model resolution in Northwest Atlantic region is not a new idea. Previous research has shown that model resolution affects mean state biases. And a quick shout out to Ping Cheng's great talk on this yesterday, where he highlighted IHESP's improvisations. So here's an example from Zhu et al. 2022, which shows that the Gulf of Maine, which is in the white box, tends to be colder and fresher in high resolution. Colder and fresher in high resolution models as compared to the low resolution ones. This is likely due to a more poleward extension and then detachment of the Gulf Stream in low-res models as compared to high-res, which affects the water mass placements, temperature, salinity, and also impacts stratification in the ocean. So if model resolution affects the background ocean state, how does that translate to marine heat wave behavior? And to understand how biases between high-res and low-res models affect marine heat waves representation when both are forced by the same atmosphere, we use the Community Earth System Model Forced Ocean Sea Ice Simulations, or FOSSEs. So FOSSE consists of simulations where both low-res and high-res models are driven by the same atmospheric forcing from JR 55. The low-resolution version has a 1-degree ocean model resolution, and all the parameterizations are turned on. In contrast, the high-resolution model is 1/10 of a degree, and all the key parameterizations like Gent-McWilliams and Fox-Camper are turned off because they explicitly resolve those eddies. Since the ocean heat budget closes in FOSSEs, these simulations are ideal for diagnosing the mechanisms behind observed marine heat waves, and yet they have been underused for this purpose. To evaluate how well the models perform, we'll compare them with some observational benchmarks like OI SST for sea surface temperature and EN4 objective analysis for subsurface conditions. So moving on to some results. Let's look at how these two model versions compare in their mean state climatology. The shading in this figure shows salinity averaged over the upper 110 meters from 1983 to 2018. And the red and the orange contour lines represent the 15 degrees Celsius and 4.5 degrees Celsius isotherms, respectively. So when we compare the model climatologists to EN4, we see that the low-res FOSSE has warmer and saltier Gulf of Maine, which is again in the white box, as compared to both EN4 and high-res models. And no surprise here, but high-res does better job and is well comparable to the observations. These temperature and salinity biases in the mean state are important because they kind of help set the background conditions for marine heat waves. And from this point on, all of my figures will be highlighting for that white box. So all of the line plots are for Gulf of Maine, not the entire Northwest Atlantic region. So let's revisit the two marine heat waves that we discussed earlier. The top row now shows the absolute sea surface temperatures from high-res FOSSE, low-res FOSSE, and OI SST for the 2011-12 event and the 2015-16 event. Consistent with the mean state bias, low-res FOSSE is significantly warmer in Gulf of Maine and almost 5 degrees above observations during both the events. And in contrast, you can see high-res FOSSE captures SST much closer to the observations. Since marine heat waves, however, are typically studied using anomalies, the bottom row shows the SST anomalies for the same events, and this is where it gets interesting. So for 2011 and 12 event, the high-res FOSSE actually closely matches the observed SST anomalies, while low-res FOSSE underestimates the marine heat wave. However, during the 2015 and 2016 event, neither model clearly outperforms the other, and both have discrepancies when compared with OSST anomalies. In the interest of time, I'll focus on just the 2015-16 marine heat wave. And although neither model better represents the observed SST anomalies, this simulation still allows us to explore how the event evolved, and more importantly, how the underlying processes compare between the models. This gives us a way to assess whether the mechanisms driving these marine heat waves are being realistically captured or not. To understand what's driving these marine heat waves, we perform a heat budget decomposition integrated over the upper 110 meters of the ocean to account for the mixed layer dynamics. And anomalies are calculated relative to 1983 to 2014 climatology. And the breakdown is pretty straightforward. The total temperature tendency just equals the sum of contributions from surface turbulent heat fluxes, radiative heat fluxes, total resolved advection, and then subgrid scale processes. However, it is important to note that subgrid scale processes here are two different things because the two models have two different parameterizations. So in low-res FOSSI, all parameterizations are active. So this term is largely governed by KPP, diffusion, Gent-McWilliams parameterization, and Fox-Camper parameterizations. Whereas in high-res, because eddies are explicitly evolved and represented, only KPP and diffusion play a role in that particular term. And a huge shout out to Annalena Teppenmeyer to help me with the heat budget decomposition. So to some results again, the figure here shows the total temperature tendency on y-axis and the time on x-axis, and both low-res FOSSI and high-res FOSSI exhibit positive tendencies during winter that initiated the marine heat wave and sustained over the summer. In fall, the high-resolution model shows an increase in the intensity of the marine heat wave, that's the mountain-like peak in the fall, aligning with the observations at this time, and something that the low-res model completely misses out and does not capture. So now to understand what drives this temperature tendency, we can now do the heat budget breakdown. The red line here shows the turbulent and radiative heat fluxes overlaid on the total temperature tendencies, and it's clear that the initial ocean warming in winter is almost mostly driven by changes in turbulent and radiative heat fluxes in both high-res and low-res. Further investigation shows that these are largely driven by the turbulent heat fluxes, and that makes sense that because this event was caused by the polar shift in jet stream, there should be more anomalous heat fluxes into the ocean, and both the models actually kind of show that. But interestingly, the low-resolution model shows stronger anomalous warming than the high-resolution one, raising the question why this difference occurs. And it's a very nuanced point, but I think it's important to show that and not just cause questions. So this schematic here shows the difference between low-res and high-res climatology and how it affects to these heat fluxes, and it goes back to the mean state biases. So because the mean state SST is higher in low-res, there is a larger reduction in turbulent heat flux out of the ocean for the same reduction in wind speed. So they are both forced by the same atmosphere. You just see there's a larger difference. And this means that the mean state biases directly impact the representation of marine heat waves in these models. It is also clear that turbulent heat fluxes alone do not explain the full evolution of the marine heat wave, especially the fall intensifying of the marine heat wave. And it is actually showed by the resolved advection in the high-res over fall. Yeah. So based on observations, a study was published by Perez et al. 2021, which kind of finds that this particular fall anomalous warming was caused because of warm core eddies present in that region. And that makes me believe that this advection could be coming from the eddies. And that would also explain that why the low-res is not showing any resolved advection patterns, because these eddies are kind of lumped into the subgrid scale parameterizations rather than explicitly resolved. So do the subgrid scale processes in the low-res model show similar patterns in advection when we look at the subgrid scale parameterization? And the answer is no. So parameterized eddies have minimal effect in marine heat wave intensification in low-res FOSSIs. We can examine the spatial patterns of total advective tendencies in both the models. So in the low-resolution model, we see kind of a dipole emerging in the Gulf of Maine, which nearly cancels out, resulting into an almost neutral net advection effect. Whereas in contrast, the high-resolution model exhibits strong positive advective anomalies in Gulf of Maine, especially in the coastal regions and also at the southeastern Gulf of Maine region. To isolate the eddy contributions, we separate the eddy advection from the total advection in both the models. And now the low-res model still shows an opposite sign dipole, so it's flipped from the total advection, but it still kind of cancels out, and there is not much advection or any warming tendencies emerging out of it. Whereas in the high-res, it's clear that most of the total advection is driven by those eddies. And I don't have that updated figure because of the NCAR maintenance, but that southeastern anomaly that you see, when you zoom out of that region, it's actually coming from an eddy that was shed off from the Gulf Stream meanders. So it highlighted that how Gulf Stream, or representation of Gulf Stream, might also be influencing this marine heat wave representations in FOSSIs. This kind of brings me to the summary. So CSM FOSSIs are great tools. Go use them to understand marine heat wave evolution from heat budget analysis perspective. High-res FOSSI better captures the mean state water masses, resulting in more realistic marine heat wave simulations. The mean state biases in low-res, and particularly coming from the higher SSTs, lead to larger anomalous turbulent heat fluxes during the 2015-16 marine heat wave or winter. And then resolving these mesoscale eddies improves the marine heat wave representation in the Gulf of Maine by capturing the Gulf Stream variations that could drive and intensify these events. And I'm not showing the 2011 and 12 event here, but both the cases kind of show that the parameterization always has an opposite effect as to what the resolved eddies are doing. And that's one of the key takeaways, that in this FOSSIs, it's not that they're trying to either have both positive anomalies or negative anomalies, they're always opposite of each other. Here are some references, and with that, I'll take questions. And shout out to Elizabeth Maroon for the podium.
Hi, nice talk. Thank you very much for that. Marine heat waves aside, I'm curious if you looked at just SST variability generally between the two simulations, like if you just did point-wise correlation of SST, if the high-res has an advantage there.
So that's a good question. Mean state and point-wise correlation, the Northwest Atlantic region in general, the high-res is much better represented in low-res. Globally, it's a different story. Globally, there are regions where it's warmer and colder, but high-res still is better observing the SST anomalies and mean state SSTs. But I don't know about global, but Northwest Atlantic, yes, high-res has a better representation.
So have you looked at the variability, sorry?
Not at the variability, no, just like not interannual variability or decadal variability, no.
Okay.
Just
Thanks.
mean state, thanks.
Okay, could you back your sixth slide?
Yeah.
I have a quick question. Do you think the results are caused by the geography, I mean the open of the channels instead of the resolution?
Yeah, so high-res clearly has more resolved coastal representation, and also the bathymetry is also important. So one thing, we haven't looked into that yet, but I would assume that definitely resolving those coastal processes. I'm not sure how the runoffs are integrated in this model, but coastal processes definitely help in resolving that. Also, the Gulf of Maine has kind of a very interesting bathymetry where south of Gulf of Maine, there is actually a deeper region that shows up. And that region is small enough that it might not be resolved in low-res FOSSI because it's 1 degree, but it is resolved in high-res FOSSI. And that's the region where we also see that huge positive anomaly going in towards high-res. So yes, but I don't have a way to show it yet.
Thank you.
Thanks. Okay, thanks.
Our next speaker is Tedra Lowe, that will talk about CSM, how CSM has more subpolar North Atlantic water mass transformation than other models. Please go ahead.
Hi, everyone. I am Tedra Lowe. I'm a grad student at the University of Wisconsin. I'm working with Elizabeth Maroon, just like Rudra. I'd also like to thank my collaborators, Stephen Yeager and Feng Zhu as well, for all of their help. So to begin, I'm sorry, just a warning, if you can't see some of the lines on my plots, all of my stuff's on Scratch, so I wasn't able to access the things that I wanted to, but I'll try my best. So I'll start by introducing water mass transformation, which we've heard about a little bit throughout the talks. Basically, water mass transformation is the amount of seawater transforming from one density to another. And those density changes occur through buoyancy forcing, and through the Walling framework, we're able to relate overturning circulation to water mass transformation. Oh, and here's a schematic showing that. And water mass transformation can be broken down into two different parts. We've got water mass transformation at the surface from heat and freshwater fluxes. We've got water mass transformation also from mixing, and that's due to internal processes. But in the subpolar North Atlantic, we've got these outcropping isopycnals at the surface, and so overturning circulation can largely be related to water mass transformation at the surface. So to calculate water mass transformation, we've got a density flux, and to get the density flux, we just use the surface heat and freshwater fluxes, and we sum up, so say we take these isopycnal outcrops, we just sum up the fluxes or the density flux over that range, and you're able to get a water mass transformation. And if water mass transformation is positive, that means we're moving towards heavier density classes, and if it's negative, that means we're moving towards lighter density classes. And I'd also like to highlight that I use the Python package XWMT. It's an awesome package. Jan-Erik Tesla works on it, Graham McGilchrist, and it also uses the TEOS10 equation of state as well. So that brings us to the goal of my talk here, and that's to investigate the differences in subpolar North Atlantic overturning circulation between CESM2 and other FOSSI models like Rudra introduced before, and that participated in the OMIP simulations. And so the objective here will be to analyze water mass transformation and AMOC in the OMIP models. And as a reminder, OMIP 1 is forced by CORV2 forcing, and OMIP 2 is forced by the JRA55DO forcing. So to compare the OMIP models, we wanted an observational benchmark to compare them against. And to do that, we constructed observation-based estimates of water mass transformation. And I used the ACOM set, which probably not a lot of you are familiar with because no one ever uses it. But it basically just couples data together. You take the model components out and you just replace them with data. And the cool thing about this is that I can use JRFD5DO forcing as well as the CORV2 forcing, which is the same forcing as the OMIP models. So we can have a more direct comparison to these observational benchmarks to the OMIP models. And so basically I just hijacked the CESM coupler in the bulk formulae, and I input these data sets, and to get a spread in the fluxes, I use different sea surface temperatures. So here I use HAT ASST and OASST, and then for sea ice, I just use HAT ASST sea ice, and then for runoff, we've got the JRFD5DO and the Dye-Trent-Berth. And so when we calculate the fluxes, here's an example of what that looks like. These are the surface heat fluxes. When we use the two different sea surface temperatures and the two different atmospheric forcings, we're able to get 4 different surface heat flux fields, and we only get 2 different freshwater flux fields because it's not really impacted by the sea surface temperature. And then we just input those into the density flux, and we're able to calculate water mass transformation. And to make sure that our data sets are self-consistent, we wanted to use the same sea surface temperature from the density field that was used for the surface fluxes. And so we've got the 2 different flux fields from HAT ASST, and then 2 different surface density fields from HAT ASST matched with EN4 and ISHI. And if we do that same thing with OASST, we're left with 8 different observation-based water mass transformation benchmarks. And so here are the 8 benchmarks that I have computed. In the subpolar North Atlantic, we can see there's an obvious spread in the water mass transformation. And so to get a better feel of where this spread is occurring, I broke down the water mass transformation into these different areas here. And we can see that in the Nordic seas, there's definitely a large spread in the water mass transformation, as well in the subpolar gyre too, and that is what's contributing most to the spread in the subpolar North Atlantic water mass transformation. And the subpolar North Atlantic is just a sum of all of those regions. And so now, sorry, it's really hard to see the gray shading. But now if we compare the observational benchmarks, so any benchmark that uses CORV2 forcing, because we're looking at OMIP 1 models, it's hard to see, but let me see if I can use the pointer. There we go. There is the observational benchmarks. The subpolar North Atlantic water mass transformation from the OMIP 1 models is shifted towards heavier density classes, and then the majority of the water mass transformation is also a lot stronger than the observational benchmarks. And if we look at the different regions, we're able to figure out where this spread is coming from, and we can see in the subpolar gyre, the southeast region, there's a large spread in water mass transformation in the backs, and it's also shifted towards heavier density classes. If we're looking at the Erminger Icelandic and Nordic seas, we see a large spread in the density classes of the max, and it's also it's too strong compared to the observations. And then last, if we look at the Labrador Sea, we also have water mass transformation that is too strong in these models. And to point out CESM2 relative to the other models, you can see that CESM2 has some of the strongest water mass transformation compared to all the OMIP models and the observations. And again, we can see that comes from the Labrador Sea and the Ermengarde Icelandic Seas. And then the same behavior occurs in OMIP2 as well. You can see the gray shading, the observational benchmarks. Here I'm just using the benchmarks that use the JR55 DO forcing. And again, we see the large spread in the subpolar gyre and shift towards heavier density classes, a large spread in the Ermengarde Icelandic Seas and Nordic Seas, and too strong of water mass transformation in the Labrador Sea. And also, we still see that CESM2 has some of the strongest water mass transformation in the subpolar North Atlantic, again, attributed to these two regions. So if we're looking at the AMOC string function at 45 degrees north, you can also see that there is there's stronger transport in CESM2 compared to the OMIP2 models, and so that pink curve there. And I'd also like to mention that this data is processed by Liz and Steve, so thank you for that. And when we are looking at transformation maps, so transformation across, say, a specific density class, here I'm using 36.5, we can pinpoint locations of strong transformation. And so if we're just looking at CESM2, we can see compared to some other models that we've got strong transformation, water mass transformation in the Ermengarde Icelandic Seas, and it's hard to see here, but there is stronger water mass transformation in the Labrador Seas. So the key takeaways of this talk is that most OMIP simulations have water mass transformation that falls outside the observational range. The maximum transformation generally occurs at heavier density classes than the observations imply. And we've got strong biased water mass transformation that we attribute to the Labrador and Ermengarde Icelandic Seas. And there is additional OMIP spread that comes from the southeast subpolar gyre. And lastly, CESM2 has some of the strongest water mass transformation and AMOC among the OMIP models, and that's because of the Labrador Sea and the Ermengarde Sea. And that's it.
Questions?
When we look at OSNAP, we see like a strong seasonality in the bias, and I'm wondering if you have tried to look at seasonality in the water mass formation to see if that we can relate them essentially.
Yes, so I have looked at seasonality. Those plots are a little hard to understand, so I will definitely talk to you more about that after this, and I can show you those plots.
So, nice talk. How much do you trust those observations?
That's a good question. Yeah. I do think the JR55DO set is a little bit better than the Core V2. But I think for this instance, I wanted to use those data sets because I wanted to compare them to the models. And they're created to force the models. So I think it would definitely be better than using reanalysis data sets for this case. But yeah, it's hard to trust surface fluxes. It's rough. Yeah.
Any questions for Tadra? If not, let's thank her one more time. And our next speaker is Liz Maroon, and Liz will talk about process-oriented diagnostics of the subpolar North Atlantic for ocean and couple model development.
Hi, I'm Elizabeth Maroon, and I'm working with, I guess, the other, last half hour worth of folks. Thank you to the Ocean Model Working Group for giving my group so much time. I really appreciate it. You did not need to give me a talk after them. That's very kind of you. So this is going to be a little bit different of a talk. This is not going to be so much a science talk as a diagnostic talk. We don't often talk about how we diagnose our models during the development process, but that's really what this talk is about. So this is a project that Steve Yeager and I have to put together process-oriented diagnostics for the NOAA Model Diagnostics Task Force package. And Tadra talked about a lot more of the science aspects of this. This is going to be kind of a mock-up of what our deliverable is going to be looked like for getting into that package, as well as we hope into Cupid. So there's been a lot of contributions. You just heard from Tadra. You'll see some similar plots on this. But here at NCAR, we've had contributions from Brendan Myers, Feng Zhu, Dylan Oldenburg, and Tegan King. So this has been much a team project. So the problem is that climate models have struggled with sea surface temperature and salinity fields in this northwest corner region since basically flux correction ended. So when we let the ocean and atmosphere talk to each other, you get big biases in the Gulf Stream and North Atlantic Current, and this leads to what's been dubbed in this very colorfully, the blue spot of death. And you can see it in CMIP 3, you can see it in CMIP 5, you can see it in CMIP 6. So why does this occur? It's because they're getting the Gulf Stream and the North Atlantic Current in just the wrong places. So I've got the upper ocean 200-meter temperature bias here on the left. Let's see, can I point? Yeah, cool. Up on the left, and then here's the upper ocean salinity bias on the right. In the gray contours are the climatological fields from EN4, and so you can kind of imagine for the isotherms, that's where the Gulf Stream and North Atlantic Current is. So the reason we call this the northwest corner is because you got these corners just sort of turning. So what this means is that you got the Gulf Stream in the wrong place, so you're going to get this bias. In climate models, you have this bit more shifted the North Atlantic Current, more to the east, and so you've got this fresh and cold subpolar water that gets into this area a bit differently than you otherwise would expect in observations. So really, this is an ocean model issue. This is not a coupled climate model issue. This comes from the ocean. And it's not just one issue. This is interrelated with a bunch of other things going on in ocean models. As one example, colder and fresher northwest corner biases are related to AMOC strength. So here on the x-axis, we got the northwest corner bias, and then the y-axis, we got AMOC strength at 45. This is an ocean-only OMIP models, and there's a very clear relationship, especially when you add all the cycles in. If you have a bigger bias, you're going to have a weaker AMOC. So it'd be really great to reduce this bias in CMIP 7 models because this has downstream impacts on the atmosphere for North Atlantic atmospheric circulation and in Europe in teleconnections. So that's really the goal of our diagnostic suite, is to help developers point what kind of processes might be going on in this region to try and improve it on the fly. So features of the package that we hope to get in soon, hopefully this summer, is we're going to be really leveraging the OMIP simulations to give a quick look at how is your model doing relative to what CMIP 6 OMIP simulations were. There'll be an AMOC and density coordinate tool that will show you what AMOC looks like in density coordinates. There'll be the observational benchmarks for water mass transformation that Tadra just presented, which are particularly ideal for comparing to OMIP. And then we're going to connect some of those biases to water mass transformation. So in the time remaining, I'm going to kind of quickly go through what some of this is going to look like. Again, with the Casper outage last week, these are not the figures that I had hoped to have, but I've got it all mocked up anyway. So feature one, this is what Brendan Myers and Steve Yeager have been working on, particularly over the last about half a year. And so this is comparing an underdevelopment run to the suite of OMIP simulations. So we've got here on the left is the bias in upper ocean 200-meter temperature. This is in a development run provided very generously by Gustavo Marquez. I have no idea what run it is, but this is just for us getting the diagnostic right. So this is the bias. You can see that the two features I pointed out before, so the Gulf Stream bias in that warm area, so Gulf Stream detaching too far north, and then the wrong turns of the North Atlantic Current are present. But the cool special sauce that Steve and Brendan have worked hard on is ranking these errors relative to the OMIP suite. So this is taking the absolute magnitude of the bias and comparing it against the same thing from each of the OMIP models. So in red, that would indicate the worst model. So this is saying that our in development run CSM3 in these regions is more biased than anything in all the OMIP models. In the, here's the 50th percentile. That's saying that CSM3 is falling, right in the middle. And then in blue, it says CSM3 is the least biased. So this is a quick look at saying, where is our simulation doing in comparison to other ones. And Steve and Brendan have put together a ton of other fields for this that are related to North Atlantic processes. So here, for example, is salinity. Again, you see those kind of the salinity and temperature and biases are going hand in hand. Fresh and cool with warm and salty. And then we've also got the bias rank similarly. Another feature that will be in the package is looking at where the biases in your model fall within the OMIP spread. So here in yellow is this under development run, and then we've got the temperature bias on the x-axis and the salinity bias on the y-axis. So even though it looks like it has some pretty big biases, it's actually in the middle of the pack, and that is because the temperature and salinity biases largely compensate. This is density now. So the density biases are weaker than the individual temperature and salinity biases, and that means that when we're looking in the OMIP model ranked space, CESM3 isn't as bad as most of it's actually on the better side compared to the OMIP models. Of course, you've got compensating errors going on here. If you have temperature that's not doing so hot, that's going to impact surface heat fluxes in certain ways that may not be ideal. But hopefully the combination of these figures together will give you, the developers, a quick idea of what's going on. So feature 2, over the last couple of years, I've been translating the CESM2 AMOC and density coordinate code from stuff that Steve Yeager had worked on and others have worked on here for years into something that can be more model agnostic and applied to any CMIP model. So this here, I've got a test model. It's not CESM, and I'm not going to tell you which model it is. So on the left, we've got AMOC in sigma coordinates. So this way is the direction you want to think as you're densifying down. So this is a random test model, and then on the right, I've got the OMIP multi-model mean. So a few things you can tell really quickly from this package, from this figure, is that this test model is a lot weaker, and its deep western boundary current, so down here, is occurring at a much lighter density class than in the multi-model mean. And those two things are linked. When you have a deep western boundary current that is occurring at denser classes, you tend to have a stronger AMOC. So these two things are going together. I've highlighted a couple of places that are of particular interest for this package, just for this talk. So the northwest corner exists in these latitude bounds in green, and then in blue is a particular area of interest because that's where you see the most OMIP spread in where the AMOC is on each density class. So those are areas of particular interest. So this is courtesy of Tedra Low. Now that we have AMOC, we know that surface buoyancy forcing largely balances, not entirely, but largely balances the AMOC in the North Atlantic. So this is part of that you'll see. So the black line is AMOC at 45. The red is the heat transport part. And you can kind of, so if you're comparing, we want to compare purple and red. So purple is the total water mass transformation, black is the AMOC. Largely the same, they're not identical. Where they're not identical, it gives you a measure of where interior mixing is actually important. And one thing Tedra did not show is that CESM implies less of a role for water mass transformation in interior mixing than other OMIP models. Then you can also break down water mass transformation into surface heat fluxes versus freshwater to get a sense of how much those are contributing. And then you already saw a version of this from Tedra, so you can then break down water mass transformation throughout the total subpolar North Atlantic over here on the left into the different regions to get a sense of where you should be looking at the other processes. So North Atlantic Current, then the subpolar gyre, Nordic Seas, Erminger, and Labrador Seas. So grade shaded region is again those observational benchmarks built from core and JRA forcing with OISST, HAD ISST, EN4 at ISHI. And then the different colored lines are different CESM2 simulations. High res and low res, you can see high res here in this dashed blue is actually doing pretty well compared to the two low res here in black and red. So a quick snapshot of, are you getting at least regional versions pretty well? So this is where we try to connect everything back together. So how do we connect water mass transformation in this kind of bulk basin-wide sense and AMOC in a basin-wide sense to what's going on in various specific locations? So what we've got here is this blue test model that I showed before for AMOC. And this is water mass transformation, also very, very weak, particularly when you stick on here, we've got this observational benchmark from Tedra. You can see that this model is very weak, and automatically you can tell, okay, this must mean that the density fluxes, in particular probably the surface heat fluxes, are way too weak. In another model, though, the surface heat fluxes might be okay, and instead what might be the issue is the isopycnal outcrops. So that's what we've got here in the next two panels. So observations here, these are observational benchmarks. In the yellow-red shading is you take the water mass transformation and you break it down into where exactly it's occurring. And then the blue shows you the frequency of occurrence of a specific outcrop at that time. So this is 36.6 sigma 2, corresponds to right here on the purple line. And so it's showing you that most of the transformation that's occurring for this blue line is occurring in observations at least, in the Erminger, a little bit in the Lab Sea, also up here in the Nordic Seas. But in this test model, you can see you don't actually have those isopycnals available, and you only have transformation occurring up here. So this would suggest that you should start looking at what's causing the density biases. So go back to the figures we started with. How much density bias do we have up there? And then figuring out, is it coming for temperature or salinity, and building it back that way. So in summary, this is a quick mock-up of something that we plan to get into the NOAA Model Diagnostic Task Force in the next couple of months, and hopefully right after that we'll get into QPID also, so that it will aid in CESM3 development. It features a lot of leveraging of the OMIP suite to kind of give you a sense of how you're doing compared to the past ocean-only models. It'll have the AMOC sigma calculation in it that's model agnostic, as well as a lot of water mass transformation decompositions and observational benchmarks that gives you some sense of how you're doing. And before I conclude, I want to bring one update from the NOAA Model Diagnostics Task Force about something that we're working on, which is Jupyter notebooks. So something we've talked about a lot is how, you know, everyone in this room pretty much is doing model diagnostics of like one piece of another. But this doesn't necessarily end up into the packages that that go into the development. And so one thing that we're trying to think about is, you know, everyone's got Jupyter notebooks, and if we can streamline how we get those notebooks into packages like the MDTF, like QPID, like GFDL's packages MAR, or like Australians, it makes maybe Jupyter notebooks more plug and play into different, you know, you can have the same diagnostic notebook going into multiple different frameworks at the same time. So in particular, Danny Coleman here at NCAR and John Crasting at GFDL are thinking, mocking up various notebooks to figure out how do you make, you know, kind of one interoperable notebook to plug and play into different packages. So I wanted to bring that to community attention to think about how do we get more of all of the work that all of us are doing into the model development, and maybe, you know, easy streamlined notebooks that are already plug and play for a bunch of different frameworks is a way forward. Thanks, happy to take a few questions.
Questions for Liz?
Stuff. I was wondering, in the ranking plot that you showed, it seemed like there are a lot of fine scale features that maybe could be coming from models having dipole errors because you're not exactly representing the location of water masses or gyres exactly the right place. I was wondering if you'd considered some kind of model-specific diagnostics, for instance, using the model's own hydrography to define the subpolar gyre or something like that, as a bit more custom way of doing that.
That's a really cool idea. We hadn't quite considered that, but certainly that could be done.
Thanks.
I guess I'll add to that and say that OMIP simulations can be a bit of a bear to work with. So simple first, but I like the idea.
Questions? If not, let's thank Liz one more time. Our next speaker is Paul Hall. Hi, Paul, I see you're online. Welcome. And Paul will talk about theory waves in CSM3.
Hello, can everybody hear me?
Yes, we can hear you.
Yes, we can.
Great, fantastic. Welcome from rainy Providence. You have much better weather out there, I'm told. My name is Paul Hall. I'm a software engineer at Brown University, where I work with have been working with Baylor Fox Kemper to develop a theory waves module, which is sort of an empirical approximation of Langmuir mixing that can be used within CESM. And I'm here to provide an update on where that is. This is more of a development talk and less science. So for background, theory waves really started out, the theory wave story started out over a decade ago with the recognition that in global climate models, oftentimes you'd find that the mixed layer depth, especially in the Southern Ocean, was being underpredicted. So it was too shallow, as demonstrated here, you know, in the I don't know if you can see my pointer or not, but in panel B here with the control run, this is from Ching Li's 2017 paper, compared to the observations in panel A of the mixed layer depth in the Southern Ocean. Ching approached this problem by saying, well, let's look at the effect of Langmuir mixing on this and see if that explains part of the problem. So he developed a parameterization where he used an enhancement factor, Langmuir turbulence enhancement factor, that was derived from Stokes drift profiles from an empirical wave spectrum that was generated from WaveWatch 3, which he coupled into CESM. And in fact, using WaveWatch 3 to enhance Langmuir mixing or to account for Langmuir mixing did improve the ability of CESM to reproduce the mixed layer depth in the southern hemisphere, in the Southern Ocean. The difficulty with this, of course, is that WaveWatch 3 as a prognostic wave model is very computationally expensive. So then the question came about, is there a better way to do this? And Ching, working with Baylor and some others, developed theory waves, which is an analytical approximation of the Langmuir enhancement factor that comes from empirical wave spectra. So it's a very lightweight calculation, and it's based on empirical data. Ching developed this in his 2017 paper and actually implemented it within CESM within the CV mix package inside POP, the POP model at the time. And running theory waves in that context, this empirical simplification or simplified model of the Langmuir enhancement factor, as you can see in the panel labeled E over here on the right, yielded, again, is similar to WaveWatch 3, a much better mixed layer depth in the Southern Ocean than models that didn't have this sort of Langmuir enhancement in it. So the theory waves itself, the issue there, of course, is that the theory waves that he developed within POP or within CV mix is kind of hard to access. So what we've been trying to do is try to take theory waves out of CV mix, not actually take it out, but just make a second module or a standalone module of theory waves that we could then substitute in for WaveWatch 3 so that you could use this relatively lightweight calculation as a component within CESM in cases where you want to account for enhanced mixing in the upper layer of the ocean due to Langmuir mixing. So the idea is that this approximation that we're using, it's based on, again, the Langmuir spectrum, or the Langmuir enhancement factor, which comes from the Stokes drift profile, which is derived from a Phillips spectrum of the wave state, which means that it's WinC only, there's no swell, it's just local wave state. It's a beautifully simple model in that the inputs to it are just 10-meter wind speed, wind stress, and then the boundary layer thickness at a location, and then you get the enhancement factor out from that can be fed back into the wave model, or into the ocean model. This is just an overview of the sort of the equations, what we're actually solving in the theory waves module. And anyway, our immediate goal over the last several months has been to implement theory waves as a component within CESM as a low-cost alternative to WaveWatch 3. And again, the idea is that it would be useful in cases where you want to account for Langmuir mixing, but you don't want to take on the computational expense of a full prognostic wave model like WaveWatch 3. It is not a complete replacement for WaveWatch 3 in any way, shape, or form, but it does give you the Langmuir mixing ideally at very little cost, additional cost. Our approach has been to develop this as a drop-in replacement for the WaveWatch 3 component in CESM. And to do this, what we've actually done is we went to the WaveWatch 3, we actually just took WaveWatch 3 starting from the Dev Unified 0.0.13 tag and used it, sort of hollowed it out and plugged in the theory waves module to the WaveWatch 3 equation, short-circuited the WaveWatch wave model equations, the main solver, and replaced it with the theory waves approximation. To use this then, it's great because we can just drop it in directly for WaveWatch 3. We don't need to do any make any changes in terms of having designated comp sets or anything like that. Anytime you run WaveWatch 3, you could just substitute in theory waves by pointing to the theory waves interface repo URL in the CESM.git module file. That's how we've implemented it right now. And we're using this whole idea of using the theory waves as the shell. It saves us time in development because we can use the existing nuopsy cap and all of the existing I/O functions of WaveWatch 3. That also ensures a certain amount of consistency between the different wave models. So we have the same outputs coming out. So anything that any variables that you're expecting will come out from theory waves that would normally be coming out from WaveWatch 3. The difference there, the main difference there is that there are a number of parameters that aren't solved for in theory waves, in which case we're just passing out empty values or fill values. The wave elevation spectrum, for instance, which is a big part of the computational expense of WaveWatch 3, we aren't outputting right now. The other difference is that we did have to modify the nuopsy cap a little bit just to bring in wind stress from the atmosphere to calculate the Langmuir, to calculate Stokes drift and the Langmuir enhancement factor. Whereas WaveWatch, that's done internally, it calculates its own from just the wind speeds instead of the wind stresses. So it's a simple replacement, and we've been able to test it out now within CESM 3, thanks to help from Gustavo. We've actually run a test case now with CESM 3 and the Alpha 06B tag. The comp set, it's MOM6 plus the wave model, in this case theory waves, and data atmosphere with JRA forcing. We're using the E factor, which is the enhancement factor, the Langmuir enhancement factor wave method to incorporate the Langmuir enhancement factor and its effects into the ocean model. And we're using the VR12 method for your vertical turbulence within that. The run, in this case, we're doing 20-year runs, and I've done a case with WaveWatch and a case with theory waves just to do comparison to show that we are, in fact, reproducing relatively well for the purposes of enhanced Langmuir mixing what WaveWatch 3 would give you with our theory waves approach. So I apologize for the not great quality of the maps. I went easy on this. So the model up top, this is just the final month of the run, monthly average at the end of the 20-year run, for sake of comparison between the case with WaveWatch 3 at the top, theory waves on the bottom. These are the predicted Langmuir multipliers. You can see that overall the patterns are relatively good. Consistent, same ballpark at least. The theory waves model does not have, it misses out on some of the peaks of the Langmuir multipliers. And it also loses, and this is by design, it actually has to do with the formulation of the Langmuir multiplier within theory waves. It can't have values of the Langmuir multiplier less than 1. So theory waves will only enhance mixing. It can't actually diminish the mixing, whereas if you're using WaveWatch 3, you will get some diminishment in the mixing or attenuation of mixing under the right set of circumstances. And you can see that in the dark blue colors here in the WaveWatch that aren't WaveWatch output that aren't reproduced entirely in the don't quite get that dark in the theory waves model. Comparing a little more directly, or you can see here, this is just taking the wind speed versus the Langmuir multiplier from the model that's generated by WaveWatch 3 versus theory waves. And as I said, in theory waves, you can see very clearly here that you don't have values less than 1 for the Langmuir multiplier. And again, that's by design. That's just the nature of the algorithm. Whereas in WaveWatch, you do get those values that are less than 1, where you will actually reduce the amount of mixing as a result of this Langmuir enhancement factor. It attenuates it. But that's in a small minority of cases. And doing more of a comparison here, this is a scatter plot of the two, where we've got WaveWatch 3 across the output of the Langmuir multiplier for WaveWatch 3 across the x-axis. The vertical axis, we've got theory waves. The red line shows what would be a 1-to-1 correlation. The gray plots, the gray dots is the scatter plot of all the values, and then the contours are just densities, with the outermost one being the 20%. So, and maxing out at 90% with the yellow contour in the middle. So you can see that for the most part, it does a reasonably good job of reproducing the basic trends in the Langmuir multiplier. So theory waves is reproducing, it's in the ballpark with what you would get with WaveWatch. In terms of the mixed layer depth that comes out of this, and again, I apologize, the maps are not the best, you can't see the continents, but you can see that the overall pattern of the mixed layer depth that results from the two different approaches is very similar, and you plot them up as a scatter plot, and you can see they're pretty correlated with a one-to-one correlation. So we're actually producing an appropriate deepening of mixing of the mixed layer with the theory waves approach. In addition to those, we actually can also, through theory waves, generate some wave statistics from metrics that, again, WaveWatch 3 generates internally in a more rigorous way. What we're doing here is we're using approximations for, in this case, significant wave height, assuming a Pearson-Moskowitz spectrum instead of the Phillips spectrum as the source here. And you can see it's just something. It's not meant to be an exact comparison because it's not quite apples to apples when you do this. But it shows that even if in terms of producing these metrics like significant wave height, was it peak frequency, mean frequency, things like that. If you can within theory waves get the output that you are getting. In terms of metrics out of the WaveWatch 3 model itself. And these are all output to the history files for the wave component. So in conclusion then, I just want to say that theory waves reproduces, we've demonstrated we have it as a standalone module now that we can replace WaveWatch with, and you get the same patterns for the or similar patterns, general patterns for the Langmuir multiplier and the boundary layer depth with theory waves that you see with WaveWatch. Theory wave provides faster performance than WaveWatch 3. Just doing the simple swap out that we did of the main wave algorithm led to a 41% decrease in the wave component runtime. So for this particular model, at least for this particular case. And this is very simple. We expect to be able to get much more significant improvements with refactoring. Right now, we have a lot of overhead running the model for, again, because we used the WaveWatch 3 component as a starting point. There are a lot of routines that are being used right now, a lot of code that's being run that doesn't need to run because we're not using it for the theory waves approximation. But we started with just, okay, let's swap out the guts and the main wave model routine and see what we get. But without any further tinkering with the actual numerical values that we'll be getting out, without the actual solutions that we'd be getting, we could just, by removing unnecessary routines, we expect we'll be able to trim this time down even more significantly. Looking ahead to the future, we hope to be able to interchange this with WaveWatch 3, but also with Pickles, which is another wave model that's in development right now with Mo Mahel. We've been working with him on that, and with Brandon Reichel to sort of standardize the outputs between the 3 different wave models. And then going forward, I'm happy to answer questions, but actually I have a question for you, and maybe more particularly for Gustavo and Alper and others in the room who are on the development side, is that how should we go forward moving from here? How is it best to make something like theory waves available for the community to use? Right now it's as simple as just substituting a URL in the Git module file within the CESM sandbox that you're using, and which saves on the necessity of making separate comp sets or anything like that. So it's completely interchangeable. But I'm not sure that that's necessarily the best approach, and I'd be curious to know what you think. Thank you.
Would you answer the question, Gokhan?
going to answer the question, but I mean, I guess it's a glass is half full of half empty thing, right? The plots that you showed comparison of the WaveWatch 3, the full system versus the theory one, I mean, it depends upon interpretation. It may be really bad or it may be really good, and the gross features are similar. However, the boundary layer plot that you showed, they looked similar to the extent that it's pretty much the, yeah, this one. So can I interpret that thing in your test case, whether you use WaveWatch 3 or theory wave model, waves do not really matter?
So, yes, except that if you were to compare this to a case with no waves, then you'd get significant differences. The difference between theory waves and WaveWatch is insignificant. The patterns are the same. It's if you don't account for waves at all that you get into trouble, and especially in the southern.
Right. I mean, the question is, in that case, the follow-up would be, there are so many differences between theory and WaveWatch in the results, yet this doesn't change. So why is that?
That's a very good question. You know, I think it goes back to and Baylor would be a better person to ask about this, or Ching, the details of the numerics. I am just on the implementation side, but I think it goes back to the formulation of theory waves. You can see that for the most part, you may have some differences that are small here in terms of the Langmuir multiplier as a function of wind speed, which is primarily what's driving this. But the cluster doesn't vary much, right? It's always between 1 and 2. It's a little bit more mixing than you would have without the waves. So it's a little bit of deepening. But you know, and where the differences arise, you know, it can be a little distracting seeing these values of the Langmuir multiplier lower than 1 that you get with WaveWatch that you don't get with theory waves, and the bigger spread that you get with WaveWatch, which is again related to the fact that WaveWatch, as I understand it, takes into account the sea state in terms of developing the calculating the stress that then goes into calculating the Langmuir multiplier.
Question for how to bring this into CSM. Unless Alper has something to say, have you put some thinking into it? Otherwise, we can get back to you later, because this is the first time I'm being confronted with this question, so I don't have much.
Yeah, no, you can get back to me later. I'm just floating it out there. So, you know, we're at some level we have this thing that we've demonstrated. And again, it's not anything new. It was, Ching had developed this within CV Mix, but it's just very hard to access within CV Mix as a user. And this sort of breaks it out and makes it more explicit for people to use. But yeah, we're open to.
But I'm just wondering your current version. So if I didn't misunderstand, you implemented this within WaveWatch 3, or is it a separate code base?
So what we did was we started off with the WaveWatch 3 code base. I just cloned it and created my own repo from it, and used everything from WaveWatch in terms of interfacing. So we used the nuopsy cap, we used the output to the history files and all of that, so we didn't have to rewrite that. All we did was we short-circuited or bypassed the wave model itself at this stage. So the component of the code where you're calling, W3 wave mod, within WaveWatch, we've just replaced that with a call to theory waves. And so there's all this overhead associated with WaveWatch, the WaveWatch code, which is making it slow still, that we need to go in and trim out now that we have some sense that everything's working.
Got it. So again, we should probably take the technical details offline, but I suppose it'll be quite straightforward to add it as a alternative wave model into CESM. But I was also wondering, in terms of both scientific and technical maintenance and support, what do you envision? Like, let's say we added this into CESM3. What next? How do we keep developing it? How do we support it? How do we answer inquiries from communities in terms of both science and technicalities.
That's an excellent question, and that's something that we would have to work out between ourselves. I suspect that right now the idea is that we continue to support theory waves itself from here, from our end, just like you would with other community models. But that's an excellent question.
We're running behind, but thank you so much again, Paul, and we'll be in touch. Let's thank Paul one more time.
Thank you.
Our last speak before the discussion is Joshua Cope. I'll let you read your title because it's a little complicated.
Hi, my name is Josh Coop. I'm a postdoc at CU Boulder, and I'm going to be talking about something a little bit different, phytoplankton. So I'm going to be showing some relatively preliminary results on some stratospheric aerosol injection simulations, or SAI, and I'm going to be looking at how the ecosystem model and changing it from 3P1Z to 4P2Z might affect how ecosystems respond to SAI. So what is SAI? I've included the very long acronym here for you to read at your leisure. It's a lot of you may know already, but it's 10 simulation ensembles using CSM2 with Wacom6 as the atmosphere, POP2 and Marble 3P1Z, so slightly older version than what's going to be the default. And sulfate aerosols are injected into the stratosphere at 21 kilometers. And the goal of these simulations is to keep global surface temperatures at 1.5 degrees Celsius above the pre-industrial mean. Meanwhile, CO2 continues to go up following the SSP2 4.5 emissions. So as CO2 radiative forcing goes up, aerosol forcing also has to go up, and there will be consequences to that. In order to achieve this goal, this controller algorithm was developed. So the aerosols are injected at a couple of different latitudes. So while we want global surface temperatures to stay at 1.5 degrees Celsius, we also want temperatures of the pole to temperature gradient to stay the same. We don't want the intertropical convergence zone to move too much. That could be problematic for the monsoons. So this controller algorithm will put different amount of aerosols at different latitudes to control both of these two things. And then finally, as I said before, this model used 3P1Z configuration. So there's no explicit calcifying phytoplankton. Despite increasing CO2 and ocean acidification, it's important to know how the marine organisms might be affected by their environment, and then how their environment would then be affected by them. So in order to bridge the gap between these old simulations with no explicit calcifying phytoplankton and our desire to know how they respond, I ran a simulation, another ARISE ensemble. It's only one simulation, so I don't know if I can really call it an ensemble, but it has a 4P2Z configuration, so it has the explicit coccolithophores now. So they can update carbon, they can produce calcium carbonate, and they also, their shelf thickness can change as a function of aqueous CO2, which would theoretically affect how they would do out in the wild. And as a refresher, I've said 3P1Z and 4P2Z a couple of times, but I might as well reiterate what that means. The 3P1Z there's 3 phytoplankton, small phytoplankton, diatoms and diazotrophes, and then there's a grazer class, a zooplankton, that will eat all of them. For the 4P2Z, which is a little more complicated, it's essentially 3P1Z with the coccolithophores. And then the zooplankton are a little more complicated. So the zooplankton are divided into 2 different size classes, and they can both graze on the phytoplankton, and then one of the zooplankton will eat the smaller zooplankton. And this is supposed to be a little bit better for controlling blooms. Some details about the simulation. They start in 2015, and at around 2035, we hit 1.5 degrees Celsius above the pre-industrial mean. So that's when the sulfate aerosols start to get injected into the stratosphere. And then the simulation runs until 2070. So let's take a look at the physical climate state. What's going on in these simulations? Did we accomplish our goal? The gray shading here on the plot is the ensemble spread for the 3P1Z simulations. So 1900 through to the current day is in gray, and the yellow shading, if you can see that. Yeah, the yellow shading is SSP2 4.5, the control run, and then the purple shading is our aerosol experiment. The red line is the one simulation that I ran with the new, with the 4P2Z, and you can see it pretty much, it mostly falls within the 3P1Z ensembles, which is good. Adding coccolithophores didn't affect the physical climate too much. And then the purple line is my SAI experiment. So once again, it falls within the distribution. And as we can see, the purple shading is right around 1.5 degrees above reference. So this is 2-meter air temperature. So we've accomplished our goal. We've saved the world. Well, you know, obviously, not really. We all know better than that. There's obviously going to be consequences if something like this were to actually be employed. And that's illustrated in this next plot of surface temperature. There are some unintended consequences, even just in sea surface temperatures. So what this plot on the left here is showing is the change in sea surface temperature for the last decade of the SAI experiment minus the decade before the SAI experiment. So this is the original 3P1Z. There's 10 ensemble members. And you can see SSP245, there's warming everywhere. And then there's this warming hole in the North Atlantic, likely linked to the slowing down of AMOC. Under SAI, we've done a pretty good job at cooling down most of the Earth, but the equatorial Pacific, this ENSO region, is definitely one place that we can't seem to mitigate warming. Crochet extension region is also still quite warm. And we just can't get rid of this warming hole in the North Atlantic. And if anything, it's gotten worse and expanded. So one takeaway from this is that SAI isn't slowing down, or not slowing down, it's not stopping down the slowing down of the AMOC, which is an interesting result in and of itself. How is chemistry changing? So obviously we're increasing CO2 and the ocean has stopped warming. This is going to cause an increase in dissolved inorganic carbon, which is what's being shown here. So the black is the SSP2 4.5 simulation. This is just my one 4P2Z simulation, but the 3P1Z is still pretty similar. You could see a divergence as soon as SAI begins. The purple line quickly outpaces the black line, which is indicating a lot more uptake of carbon in the surface oceans, just because there's relative cooling in the SAI case compared to the SSP2 4.5 case. Interestingly, pH is a bit more complicated. Carbonate chemistry, the constants that determine this are also temperature sensitive. So it's interesting, pH actually doesn't show that much of a difference between the SAI case and the SSP2 4.5 case. But more than just pH matters for organisms. So we took a look at the saturation state of calcite as well as aragonite. So calcite is the mineral form of calcium carbonate relevant for the calcifying phytoplankton, the coccolithophores in the model. And then aragonite is relevant for corals. And as the CO2, as the ocean continues to uptake carbon in these simulations, we see a decline in the omega calcite, or the saturation state of calcite, which indicates that it is becoming more difficult to form shells, more energy is required for organisms to maintain their shells. And just like the DIC plot, the purple line, the SAI experiment diverges as soon as SAI begins, and the decline is accelerating a bit faster for both calcite and aragonite, indicating it would be more difficult for these organisms to maintain their shells and build new shells, which suggests that they'd be much thinner and more prone to predation. And moving on to the actual title of my talk, which was, is there a difference between 3P1Z and 4P2Z? Does it actually make a difference in things like omega aragonite for corals? And obviously, I only have one ensemble member, so take this with a grain of salt. The black line is my SSP2 4.5 simulation. I have red shading to show the ensemble spread for the original simulations, and this seems to suggest that there is a baseline difference between the new 4P2Z and the older 3P1Z, whether or not that's because the calcifying phytoplankton are having feedbacks on the climate system and causing omega aragonite to be a little bit higher. Not sure at this point yet, would like to have some ensemble simulations to do a more robust comparison of these. But if you take a look at the SAI simulation for both of these, the blue line starts to, by the end of the simulation in 2070, starts to fall into this purple envelope, which seems to indicate that the new 4P2Z is a little bit more sensitive to SAI. There's maybe a little bit more of a reduction in the saturation state of aragonite. So slight model difference, maybe this model suggests more of an impact on corals for SAI. Finally, moving on to the phytoplankton response. So the model simulates phytoplankton. This is a plot just to show you what the distribution of phytoplankton, net primary productivity, looks like in the 4P2Z model, just to get a sense for when I should, the next like 6 plots are percent plots, so this is what it actually looks like. These peaks in the Equatorial Pacific and the North Atlantic. And then in the 3P1Z simulations, it's really, the phytoplankton response is mostly driven by physical climate changes. So you can see in the high latitudes, there's a 20% plus increase in phytoplankton in the Arctic, as well as in the Southern Ocean during this same time period that I was looking at for the temperature plots. And this is almost entirely driven by sea ice reduction under SSP2 4.5. I believe I have a plot of that. This is a plot showing annual mean sea ice area in the Southern Ocean, and under SSP2 4.5, you could see this decline. Interestingly, under SAI, because sea ice is not declining as much and seemed to have stabilized quite a bit, we've removed these gains in phytoplankton under SAI. So pros and cons. Phytoplankton don't do as well under SAI, but there's more sea ice for other organisms. Another very notable thing is that this warming hole in the North Atlantic, whether or not it's real, where the AMOC is slowing down this much and causing this much cooling or not, it's definitely having an effect on phytoplankton through temperature limitation. It's quite cold and they can't be as productive, which might have effects for fisheries. And then another thing to note is that there's this robust response in the Sargasso Sea in the 3P1Z simulation. And it won't pop up, I'll spoil it, it won't pop up in the 4P2Z simulations, which is interesting. And if we this is basically a summary of all the results I gave before. SAI causes a decline in the tropics in productivity and increases in some parts of the North Atlantic, but it is a bit of a mixed bag. In other places like the Equatorial Pacific, you don't see obvious benefits. And then moving on to the 4P2Z simulations, it's pretty much the same thing. Phytoplankton response almost looks exactly the same, where it's driven by these physical processes. It's a sea ice decline, and it's the North Atlantic warming hole that's obviously still present in the 4P2Z because the physics haven't changed, thankfully. That was a good thing that the physics didn't change. And then again, this is the response in the 4P2Z. And then finally, the coccolithophores. This is what isn't in the 3P1Z, and I can't compare to the 3P1Z because it's only in the 4P2Z. So interestingly, coccolithophores decline this is essentially showing most of the coccolithophore mass is in this great calcite belt region in the Southern Ocean. There seems to be a shift to the south for this species. So in a lot of the Southern Ocean, you see an increase there. The removal of sea ice allows for coccolithophores to thrive in the Southern Ocean, as well as in the Arctic under SSP 2.5. And under SAI, it's quite mixed. In some sectors, there's a decline from sea ice benefits, and then in other sectors, there's an increase in productivity under SAI. So For phytoplankton, it's mostly sea ice and physical attributes. For coccolithophores, it's a bit more complicated, and we think that it does have something to do with carbon availability, especially in the Pacific Ocean. And then finally, to kind of summarize everything that I said, the effect of SAI seems to be a decline at high latitudes, and that's mostly sea ice driven. And then in other mid-latitudes and tropical regions, this is possibly because of temperature being high temperature limitations being relieved because it's cooler. And that's my summary of conclusions. You can read, and we'll take any questions.
Yeah, I missed it. What is the? How are you doing the SAI? Which latitude or which height?
So, is it possible to go to a hidden slide? I think it's 30 north, so I think there's 4 latitudes, if I remember. I think it's 30 north, 15 north, 15 south, 30 south.
It's all simultaneous injection?
Yes, it's the controller algorithm.
Okay. I mean, the reason I was asking is essentially that the response of the boundary layer depth or the cold blob and AMOC is strongly dependent upon which latitude you impose the SAI. There's nothing impacting those if they're imposed south of the equator, including the equator. If you do the 15 degree, 30 degree, 45 degree injections, then you get the same impact that you are showing. So there is a strong latitudinal dependence of the strength. But anyway, we can discuss it. We have a paper on it. I can send it to you.
Yeah, I think we were using the 30, 15, 15, 30 controller, but we can talk later.
There's more questions. Can you guys connect offline? We are out of time and need to move to discussion. Let's thank Josh one more time.
I don't have any other slides for
No,
this session.
there's no number 9.
Let me check the folder. Okay, I'm downloading your slides now.
Thank you. Okay, so for the discussion, Ian and I put together a few slides, and also we hope to leave some time for open discussion. So based on what we heard yesterday morning from Dave Lawrence, Lab C was freezing, like he did not mention explicitly, but one thing that we did in the latest runs, we suppressed the submeso scale mixing only within the Labrador Sea, and that so far, fingers crossed, seemed to have helped with the Lab C freezing, and that in this time series of minimum SST in the Labrador Sea is the red line, the red time series that has gone now for over 100 years and still has not frozen. You can see the 2 black lines, the solid and dashed, are examples of cases that have frozen. So it seems like this will be, so far it's looking promising. We do have another option, which is in addition of shutting off submeso scale, we can also shut off the near surface ready component. We call it horizontal boundary diffusion. That is another possibility as well, but seems like with only suppressing submeso, we will be fine. Again, TBD. Another things that we have, another issue that we have been dealing with, which most people here will not care about, is if you go and download Beta 06, our latest sandbox, and you run a case, you will get some truncation errors. It's not in many, it's only a few locations, usually when you have steep slopes and then a thick cell next to a bigger cell in thickness. And to suppress that, we have enabled the Smagorinsky Laplacian viscosity, and that seems to have solved the problem. So here's a time series of that, how many truncations we have. Is only a 20-year run, and there's 0. And on the right, this is just from at the end of the run, a monthly mean of how the Laplacian viscosity looks like in a map. And the large values tend to occur near the boundaries. That's how this scheme was designed to do this kind of thing. It doesn't affect the key metrics if you do a case with and without the SMAG allowing truncations to occur. Like the key metrics don't change. So again, this is only for the purpose of get rid of truncation errors. We have also been playing with boundary layer schemes, like 2 different schemes, as well as the setting in KPP. So this is, we were close to putting together KPP, the new version of KPP that Bill is working on. And then I did a sensitivity run where I replaced all the vertical mixing from NCARD with GFGL's version of that, just to see what would happen. And it turned out that it improved some of the key biases that we have. One of each is the sea ice, Southern Hemisphere sea ice area, which is shown on the top left. And the run in blue, this is the out of the box. And we are comparing against the black line, which is the observational based. And then when we switch to PBL, the GFGL's vertical mixing scheme, that's the running in red, we got much better agreement with OBS. And that is because if you now look at the 2 panels on the top right, the 2 maps, that's KPP versus PBL, this is showing the SST bias, the run minus a baseline run, which is the run 170 in this case. And the purple line in these plots represent the ice edge, the sea ice edge. You can see on the top right panel that with EPBL, you get this warm bias, which is what's causing the sea ice to melt, and therefore getting us closer to OBS. And these are all fully coupled runs. In addition to improving the sea ice extent in the Southern Ocean, Southern Hemisphere rather, the switching to EPBL also improved this thermocline biases that we see in the tropical regions. I'm highlighting these regions on the bottom panel, the 2 bottom panels on the right. And KPP on the left, EPBL on the right. And if you look closely, it's improved with EPBL. And although we don't know for sure, we think that these thermocline biases might have some implication for ENSO representation. So because of that, now, Bill Lodge has been working on an energetics-based version of KPP, which when he incorporated waves into KPP, that was the original plan. So if you go in and look at his paper, I think it's 2023, that's what's in there. But we had not implemented in CVMix yet. So that's happening now. In conjunction with evaluating this new KPP, we will also evaluate the KPP plus the LF17. So that's the scheme that Paul Hall was talking about that was using CSM2 with the enhanced wave mixing on top of KPP. So these are our next steps for hopefully getting something close to what we get with EPBL. Moving on now, I borrowed this slide from, again, Dave's presentation on Monday. So this is some of the improvements that we are seeing in the equatorial ocean when we add kinetic energy backscatter. So that's the same plot that Dave showed. So those are transects of zonal velocity. Top left is OBS, top right is POP, bottom left is MOM without backscatter, bottom right is MOM with the kinetic energy backscatter. And we see that adding the kinetic energy backscatter leads to the emergence of the so-called Tsuchiya jets. We don't see them in POP, we don't see them in MOM without backscatter, and they are present in OBS. We don't show here, but we run cases with BGC and backscatter, and adding backscatter with BGC leads to a significant improvement in the bias of the oxygen minimum zones in the equator. So it's very promising. We would like to move forward with this. However, adding backscatter also seems like to impact negatively the Meridian overturning circulation, and this is the global one shown on the bottom right. And if you look in the equator at depth, you see something that it looks weird. And looking at velocities at depth, you see these pulses of high velocities coming in. So we have ideas on how to keep the near surface properties or effects of backscatter, which will lead to the improvements such as Suchia jets and consequent improvements in BGC, while getting rid of what happens at depth and deteriorates MOC. So again, those are we have two ideas, and we'll move forward with them and hopefully can maintain the benefits of the energy backscatter. And then finally is the choice of the target densities and thicknesses for the high common coordinate. So we have been using, again, out-of-the-box settings is a convoluted way that we combine the vertical grid that GFGL was using with what the FSU Navy people were using with MOM6 and HICOM1 vertical coordinate, plus some tweaks that we did it to get rid of thick layers. So it was a very convoluted way to come up with those targets. In the meantime, then Ian developed a new method for specifying these target densities given an initial TNS state. And this new method is looking very promising. We've done forced simulations, we've done fully coupled simulations, and also Jean from the Paleoclimate Working Group has done LGM simulations. So we're pretty confident that it's working together, although we need to do some further analysis to check that box. But if everything goes well, and if at least we get as good as a representation using the new method, we would like to move forward with that because, one, it can be reproducible, and two, we can apply the same method for other scenarios. And I think that's all I had here. And we can have some discussions if people want to ask any questions about these or any other topics. We're happy to answer the questions.
Since we're already a few minutes into the break, I don't want to keep you too long. If there's anybody from NCAR Ocean section here, maybe you guys could save discussion until later because we can talk anytime. But if anybody not local, but who's here and has something to say, we would welcome that. Otherwise, we could just go to break.
I was just about the Bodner, about the submeso restrictions in Lab C. Are you using the Bodner scheme, the new one?
Yes.
And okay, so you've answered the question then. Okay, so I mean, is there any way to try and actually change the length scale rather than just turn it off? Is there a contour of kind of threshold contour you can change to kind of that encapsulates the labrador sea? So you haven't got this kind of geographic mask. No.
No, one way of we thought that since it's a region where you have deep boundary depths, we could potentially modify Bodner itself to turn it off once you have deep convection. But so far you're using a mask in the efficiency coefficient of Bodner.
All right, in the absence of further questions, let's once more thank all the speakers and then go to break.
Okay, everyone. Okay, let's go ahead and get started. I'm super excited that we're actually here and celebrating, the 30th annual CSM workshop, and also getting the opportunity to recognize Warren Washington's amazing contributions to Earth system science. We've been thinking about this, Elizabeth and I and others, for at least the last year, so it's pretty fun that it's actually coming to fruition. I think we have a pretty fun afternoon and evening scheduled for everybody. 30 years, it's really remarkable, right? That a project can sustain for that long in general. And if you think about all the remarkable things we've accomplished with CSM over the years, and all the people and faces and that we've got to experience during that time. And it's really fun for everyone to, every year we come back to this workshop and you meet all your old friends, and then you meet all the new young people who are coming and with all their new ideas. And so I feel really honored and really humbled actually to be up here and leading this event in honor of CSM. And so I'm going to do a fairly predictable thing, but I think it's still going to be fun, which is to try to see how many workshops people have been to over the years, because we do have some people have been around for quite a few of these. We'll see. So I've been around. This is my 22nd workshop, so I'm no spring chicken myself, but I'm not the winner. That's obvious in terms of the longevity. But I'd also start up by let's recognize, and if everybody's ready to do a quick stand up, I want to recognize all the people who this is their first CSM workshop, and it's really fun that you get to be here for this event. So everyone, please stand up who's your first workshop. All right, so 30 years from now, we expect you to be celebrating the 60th. So then let's go for people who've been to, up to 10 workshops. Can you please stand up? If you can remember, and just go approximate. We don't need to go. Yay. You guys, you're trying hard. You're trying hard. That's good. Solid effort. Next, let's do 10 to 20. 10 to 20. All right, some former chief scientists. Okay, let's do the 20 to 25. We're going to get a little bit more fine-tuned here. All right, I do recognize all those faces. Okay, 25 to 29. All right. That's dedication. And then finally, let's see who's been here to all 30. Please stand up. Yay! We got Esther in the back there. Steve, are you standing up? No, Steve is not standing up. Jerry, Peter, Gordon. That's amazing. And probably even in some of the ones that were before, it was really a workshop. So that's exciting. Okay, so we're excited to be here, 30th annual workshop. Just quickly, this is what we're going to be doing. We have 3 fun presentations by Jerry, a tribute to Warren Washington. Peter is going to give us a history of one of the first simulations we've done way back at the beginning of this effort and 30 years ago. And Cheryl Craig is going to talk about a day in the life of a CSM developer from 30 years ago or so. I know these are all going to be super fun. And then we're going to have the inaugural, and I'm not sure if this is going to be repeated, but definitely excited to have this, the Outstanding CSM Community Service Award, because the word community is central to everything we're doing here, and you guys are all here because of this community, and we want to recognize someone, an individual who's represents that. And then we're going to have a roundtable discussion with former CSM chief scientists, and then we have food and drink and music. And Nan Rosenblum, is she in the room, or she's prepping, I guess. She's NCAR staff. Her band is here, and so that's going to be super fun after this. So And this is the list of former chief scientists, so we're going to hear from all of them. That's going to be super fun, and again, I'm really humbled to be standing here in front of all of them at the beginning of this. So we're going to start off with Jerry. So Jerry, please come on up and give us your tribute to Warren.
Thanks, Dave. And so this, as you indicated, this is going to be a tribute to Warren Washington's pioneering work in Earth system modeling and CESM. And as most of you know, Warren, NCAR climate modeling pioneer, passed away last fall. This is the first CESM workshop since his passing, and so because he played such a critical role in the history not only of CESM, but history of Earth system modeling and climate modeling at NCAR, we thought this would be a really good time to dedicate this session to his memory. So that's what I'm going to talk about. And then, as Dave said, Peter's going to say a little bit about the early CESM simulations. So Warren came to NCAR in 1963, and he was he really was on a mission to build an atmospheric general circulation model. And the idea was numerical weather prediction was a big thing in the 60s. And so when he got to NCAR, he met another scientist named Akira Kasahara, and there's a picture of them on the right there. And they said, okay, well, let's put together a general circulation model of the atmosphere. And they called it the NCAR General Circulation Model, not surprisingly, or the NCAR GCM. And so there's a few pictures, early pictures of Warren in action. The lower left is a picture that's shown a lot. Warren's actually holding up a strip of microfilm. And microfilm was the way you looked at your plots that came out of the model in the early days. It was a DD80 photographic printer. And you got these, and Cheryl's going to talk about this in her talk, you get these little boxes with microfilm reels, and you'd see NCAR scientists in this pose that Warren's in the center there at the bottom, staring at the prints that are on the microfilm reel frame by frame that you run through the reader, and then you can make little prints of them, and you see a print of one of the frames coming out there at the top. And so that's how you looked at your output from the model. Things got a little better with workstations. There's Warren in the early 80s with John Humbrecht, who was a software engineer then, with one of the workstations. But Gary Strand has a great story of how they used to do animations, because you'd actually take a 16mm camera, set it up in the Damon room, or maybe the director's conference room, and aim it at a workstation and bring up a frame of the model output from the workstation, click one frame of the 16mm camera, advance the image on the workstation, click another frame on the 16mm camera, and that's how you made animations of model output at that time. Things have gotten a little better since then, luckily. So this line came for this do something different line came from Akira Kasahara's autobiography, and he said when they started thinking about this at NCAR, they wanted to do something different, and basically different to what was being done at GFDL, because GFDL was the big powerhouse in modeling at that time. And they wanted to do something that GFDL wasn't doing. And so they wrote this line. Warren actually wrote this line, the first line in the abstract of a tech note from 1975 when he was looking back on the start of their modeling effort together. Quote, they wanted to make the model available to the atmospheric science community as a facility for numerical experimentation, as well as to fulfill a need at NCAR for studying the large-scale dynamics of the atmosphere. So from the very beginning, this is early 60s, they were thinking that this model would be a community resource and a facility. And we heard Everett yesterday use that same word, facility. The CESM is a facility for the community, for the university community. So right from the beginning, they had this vision of what a community modeling effort at NCAR should be. So they came up with the first version of the model. The first generation NCAR GCM, they called it, was in 1965. They ran it on a CDC 3600. And Betty was pointing me to some of these references, and we realized that 2025 marks the 60th anniversary of community climate models at NCAR. The first one was 1965, and so we're celebrating the 30th anniversary of CESM, which is the most recent incarnation of these community modeling effort, but it goes back to 1965. And of course, it evolved from atmospheric-only models to coupled models to current CESM Earth system models. So they kept coming up with new versions. The second generation version came out in 1968, the third generation in 1972, and because it was a community resource, university scientists were getting interested in using the model. And to use the model in those days, that meant you had to physically come to NCAR because you had to submit a card deck. Each card was a line of code, and you'd submit the card deck, and that was the model, and they'd run it through the card reader, and it would run on the computer, and you get your output on microfilm. So scientists had to come to NCAR to run the model. So you had this community of scientists that would show up every summer, and they started having these informal meetings. And I got to talk to Dave Williamson about exactly how this evolved, but they would have these gatherings of GCM users that later evolved into a users group meeting. But by the mid-70s, this was getting to be a kind of a big thing, and they realized they needed to have more organization, so they formed something called the GCM Steering Committee. It was chaired by Francis Bretherton, and when you read the mission of that committee, it basically reads exactly like the mission of the current CSM Advisory Board. So already in the 70s, all the pieces were in place for what ended up becoming this effort, now the CESM. Then there was a significant development in the late 1970s. A group of Australian scientists had developed something called a spectral model, a spectral atmospheric model, and this meant that you were not computing the equations on grid points, but you're computing them in wave number space. And so they devised this atmospheric model, they brought it to NCAR, and it became the basis for a new NCAR atmospheric model called the Community Climate Model, or CCM. So 1979 was the CCM-0A, 1981 was the CCM-0B, and this is a great line from a paper Dave Williamson wrote reflecting on the start of CCM-0B. It was intended to be a combined forecast and climate simulation model. And this is a quote from Dave's paper. They wanted to utilize the same basic code for global forecast studies, both medium and long range, and for climate simulation. Economy and increased efficiency could then be achieved by documenting and maintaining only one set of codes. So this sounds a lot like seamless prediction, which is what we're still talking about. So even at that time, they were thinking in terms of using the same model for numerical weather prediction and climate. By the mid-80s, there was CCM1, and they started holding these annual summer CCM workshops as the demand continued to increase. And so the number of participants continued to increase, and so increasing attendance became a concern, because there was concern that they wouldn't be able to fit all the CCM users into the main seminar room or any meeting room at NCAR. And so they were talking about maybe they'd need a bigger venue. And of course, this foreshadowed the move to Breckenridge for exactly that reason 15 years later. But Warren was giving a talk about this in the early 80s, and he was, it may have been a Board of Trustees talk, but he was talking about the future of CCSM, and there's going to be ever-increasing numbers of users, and we're going to have to move to a bigger facility that's going to accommodate all these many users of the model. And so he used this graphic to illustrate what he thought would be a good venue. And this is typical Warren Washington humor, right? So let's put all the CCM users in Mile High Stadium, home of the Denver Broncos. But it wasn't far from, it was actually far from the truth in terms of numbers, but it was actually the concept of increasing numbers of users was definitely happening. And this is a shot from an early CCSM workshop in 1987. You see these kind of bizarre little workstations, and by then you got away from cards. You could actually submit your code electronically. You see Warren there in the back right, and some of the other early luminaries there of the atmospheric modeling effort. You see Randy Dole in the front left there, who became a prominent NOAA scientist. Dave Erickson's in the front center there, who became an NCAR scientist later. So all these people were filling up the Damon room, and this is kind of like what the tutorial kind of looks like in some form in the present day. But I'm kind of getting ahead of myself here because we're talking about Earth system modeling. So let's go back to Warren's interest in Earth system modeling. So in the late 70s, Warren got interested in this, partly because Suki Manabe, GFDL, was already doing it. And this was the usual NCAR GFDL competition. And Manabe had teamed up with Kirk Bryan, an ocean modeler who had a coarse grid ocean model. And they were running something called a sector coupled model. And they had 120 degrees of longitude as a sector. One strip was land, the other strip was ocean, and then the atmosphere kind of covered that whole sector. And they were able to run coupled with that kind of idealized geometry just for the northern hemisphere, and they got it to run. But Warren wanted to do one better than that. He wanted to run with realistic geography, a global model with the interactive components of atmosphere, ocean, land, and sea ice, but he needed a more powerful supercomputer. So the first supercomputer defined as using vector processing was the Cray 1. It was invented by a guy named Seymour Cray in 1975. NCAR bought the third Cray 1 off the assembly line, serial number 3. The first two went to DOE labs to do classified bomb research, supposedly. It replaced the CDC 6600, which was also designed by Seymour Cray. And here's some pictures of the early kind of evolution of the Cray 1. That upper left picture, it's kind of like evokes the image of the Marines raising the flag on Iwo Jima, right? You got these engineers shoving the Cray-1, the supercomputer, the fastest computer on the planet, into the basement at NCAR to get it into the computer room. There's upper right is Warren posing there proudly next to the Cray-1, which is going to allow him to run an Earth system model. And this Cray-1 was a really weird looking thing. In the lower right there, you can see it was kind of this circular thing that all the circuit boards that had the chips on them were in those kind of vertical stacks. You could stand in the middle of the supercomputer if you wanted to, like this software engineer is doing. It had these kind of weird padded seats around the bottom that actually were covering big transformers that were handling all the electricity that was coming into it. It looked really like something out of a set for Star Trek. It kind of had this really otherworldly, weird, fake look to it. But it was the most powerful supercomputer on the planet. It was about 80 times faster than the 6600. And to give you an idea of how computing power is advanced, and there's various estimates on this, one estimate is the iPhone you're carrying around with you is about 7,000 times faster than the Cray-1. That's how far we've come with computing. But in 1977, this Cray-1 was a big deal. It cost $9 million, which is about $50 million today. And this would allow Warren to start running the first Earth system model at NCAR. Even with this fastest supercomputer on the planet, you still couldn't synchronously couple and have the ocean atmosphere communicating as the model ran. You had to divide it up in some way to allow it to be able to run at all. And so they came up with something called asynchronous coupling. And asynchronous coupling meant that you ran the atmosphere for 4 months, January, April, July, and October. Those are just 4 monthly simulations. Take the fluxes from those 4 months, fit a second harmonic to them so you get 12 monthly values, then give those 12 monthly values to the ocean, run the ocean model for 5 years. In the 5th year, you take the sea surface temperature and sea ice distributions from January, April, July, and October, give those back to the atmosphere. The atmosphere runs those 4 months, January, April, July, and October. Second harmonic runs through it, get 12 monthly values, give it back to the ocean, and it goes back and forth like that. And they were able to run 4 cycles with this kind of configuration. So Warren had expertise in atmospheric modeling. He connected with Bert Sempner, who was an ocean modeler at NCAR, and he had a coarse grid ocean model, and so they were able to put together the first, what was then called a coupled model, which we now call an Earth system model. Had realistic geography, it was a global model, had components of atmosphere, ocean, land, and sea ice. It was run asynchronously without flux correction, and produced a credible, at least for the time, simulation of the Earth's climate. And this paper was published in 1980. And I found this picture on the right there. Bert Sempner's on the left, Warren's in the middle, and I'm on the right. I was a very, very early career scientist. And I was basically amazed to be able to be working with these two really pioneering climate modelers as they put together something that had never been done before. And this was really exciting because this was something that I didn't think I would ever get involved with, but it was really exciting to work with Warren and Bert on this model. Well, this is what came out, and it looked like planet Earth, which was a good thing, right? So you look in the upper left, that's the mean temperatures from the atmosphere, the models, the 2 panels on the top, the observed are the 2 panels below. Looks roughly like the observations the model does. If you look at ocean heat transport from the ocean model in the lower left there, the ocean was transporting heat northward, north of the equator, southward, south of the equator. That's a good thing. Look at the sea surface temperatures there, kind of in the middle panels, the computed sea surface temperatures on the top, observed at the bottom. Tropics were too cold, high latitudes were too warm. It was a very diffusive model, but there's some sea ice was able to stick around there in the Arctic, so that was a good thing. We're looking at ocean currents, and you see the gyre circulations from the computed currents on the top there compared to the observed at the bottom. So this was considered to be a success because the model didn't blow up. We got something that looked like Earth, and so this was a good step forward to benchmark subsequent efforts. But even in the early 80s, it was still too expensive for Warren to run fully synchronous global coupled models, especially for the climate change work that he had gotten some funding from DOE to do. So a number of workarounds were devised. One was running the atmospheric model with a surface energy balance, or swamp ocean, which would come into equilibrium very quickly because it's just to have a surface energy balance like a wet surface. A non-dynamic slab mixed layer ocean, which we're still using versions of that type of configuration today. You could get double CO2 and get that to come into equilibrium in like 30 years or so. But then finally, NCAR got another new supercomputer, the Cray XMP. It arrived in 1986, and then that allowed Warren to run a fully coupled global Earth system model, synchronously coupled, without flux correction, for an increasing CO2 run for decades, and two experiments were done, an instantaneously doubled CO2 experiment and a transient experiment, which is kind of a new thing, a new wrinkle for the field, where you had CO2 increasing at 1% per year. And that was published in 1989. And that model, the NCAR model, was that put NCAR in the kind of the head of the line in terms of international global coupled climate modeling, as evidenced by these four plots here. These are climate change plots from the four modeling groups in the time of the early 90s that were doing these experiments. This is a figure from the 1992 IPCC update to the first IPCC assessment report. GFDL at the upper left, Max Planck from Germany in the upper right, NCAR lower left, and UK Met Office in the lower right. And you look at the patterns of temperature change, and some of these things still look familiar, right? So if you look at the Arctic is warming faster than anywhere else. High latitude warming is something we're actually seeing now in the real world. Land's warming faster than the oceans. Southern oceans were kind of warming less than anywhere else. So even in these early attempts at global coupled modeling, you see some of the things we still are seeing in models today. So CCSM, or the acronyms, Peter's going to sort all the acronyms out. Whatever turned into CESM, started in the mid-1990s, which is why we're celebrating this 30th anniversary year. And when this was kind of getting going, Warren was actually leading work on the use of the massively parallel computer environments in the late 1990s. And this ended up being the DOE NCAR Parallel Climate Model, or PCM. And the reason that Warren did this was that Dave Bader, who was our program manager from DOE, said, you know, if you guys can come up with a model version that can run on massively parallel computers, I can get you a ton of computer time at Los Alamos. And we said, great, you know, this is really going to be great for us. So with some coding and recoding and to get it to run, we were able to run the parallel climate model. And before then, the vector architecture on machines, you just run everything on a long array of data, but on parallel machines, you distribute the computations between thousands of individual processors. And this step forward into parallel computing was summarized by Andrew Weaver in a quote from a paper he wrote a number of years later. Moving from vector to parallel codes opened up a whole new realm of possibilities. It allowed for better representations of the physics to be incorporated, higher resolution models to be run, and for those same models to be run for longer times. Parallelization was revolutionary for climate science. And so this was going on as the CSM, or CSM, whatever it is, was being developed, and these two efforts ended up being merged around 2000. So the scale of this effort is kind of interesting to look back on. I mean, you look at this room full of people. The Earth System Modeling Group, which we didn't call, it wasn't called that, it was called the Climate Change Research Group. It was at NCAR, looking at climate change coupled model simulations. There was 4 of us in 1989. Myself on the left, Tom Betke, Linda Verplank, and Warren. This was the extent of the DOE-funded climate modeling effort at NCAR. It expanded in 2005. This picture on the right is the Climate Change Research Group at NCAR. And you can see some familiar faces in there. Of course, Warren's on the left. I'm there. Haiyan Tang is third from the left. Gary Strand is in the back row there. Stephanie Shearer in the front. You see Dave Lawrence in the center back there. He was part of the DOE-funded effort doing climate change research. Vince Whalen, Julie Arblaster in the front. Reto Canuti in the back row there, getting toward the right. Aishu Hu and Lawrence Buja. So that's how this has been growing ever since, and it's gotten to be a bigger and bigger thing. And then, of course, CSM, or CSM, or whatever you want to call it, came along in the mid-90s. And Warren ended up being a co-chair of the CSM Climate Variability and Change Working Group. Actually, it started out being Climate Change Working Group, and then it was merged to become the Climate Variability and Change Working Group. And he was a co-chair of that group from 1999 to 2015. And before that, he was CGD director from 1987 to 1995 during the formative stages of the CSM. So if you look at these pictures on the left, this one on the upper left, I don't know where I got it. It's a poor quality photo, but it was from the second Breckenridge workshop in 1997, out on the patio there of the village condos. The reception is myself, Bert Sempner, John Weatherly, and Warren. The lower left was from the 2007 CCSM workshop at Breckenridge. There's Warren with Jay Fine from NSF. He's a program manager from NSF, and he played a critical role in his support for this whole CCSM effort. And it was really his support that made a lot of this possible. So Warren was influential in the community modeling effort at NCAR starting in 1965 all the way through to using CSM in concert with the DOE funding at NCAR. And here's a few more pictures. In the upper left there, anybody that was at one of the Breckenridge workshops recognizes the dreaded 10-mile room. This is this massive room where we had all the plenary sessions. It was also the room where the roof collapsed due to excessive snow cover, which then shut down our visits to Breckenridge for the CSM workshop. But that was the scene from the plenary. You can see and this is a picture that somebody took at the dinner in 2007. That's Warren and Mary on the left there, Kevin Trenberth in the center, Rick Rosen, and Phil Cameron Smith, and Warren and Mary on the right there in Breckenridge in 2011. So to kind of sum up, Warren was a pioneer in Earth system modeling at NCAR, first with the community atmospheric model in the 60s and 70s, then the first NCAR Earth system model in the 80s, then the PCM in the 90s, and CSM in 2000s. And Warren's legacy lives on today in the CSM effort that we're here talking about this week. Thanks.
Thank you, Jerry, for that excellent tribute, and obviously you showed us how much we owe to Warren and what we're all able to do here. Without him, who knows where we'd be. So next up, Peter's going to sort of talk about, I think, the birth of CSM and CSM.
Invent it by one of these things. Pigment. Okay. Can you remember what you were doing 30 years ago? I only just can, but I'm here to talk about what we did close to 30 years ago. We did this thing called the CSM run. It went for 300 years. So in 1995, a group from the Climate Division, the Atmosphere and the Ocean Group got together and started coupling models that they had. But in early 1996, each of those groups had a new version of their model. The Atmospheric Group had a new version of CCSM3, Community Climate Model 3, and it was called a climate model, even though it really was only an atmosphere and land. And they had this new version with a resolution of T42 times 18 levels. T42 is a resolution of around 2.8 degrees. The land component, land surface model 1, ran on the same grid. And the ocean section had a new ocean model called the NCAR CSM Ocean Model, NCOM. Its resolution was 2.4 degrees zonally, and meridionally, it was 1.2 at the equator, up to 2.3 degrees at higher latitudes, and it had 45 levels. And there was a sea ice component called CSIM. This ocean component we were all proud of because it had two new parameterizations that had been developed in the ocean section. One was a new vertical mixing scheme called the K-profile parameterization, KPP, pioneered by Bill Large, and a new parameterization of the effects of mesoscale eddies that weren't resolved in these models at about 1 degree. So the mesoscale eddies were determined not only to diffuse along surfaces of constant density, but the new feature was that they had an effect that was also due to advection. These were new, and we were proud of this, and we finally put it in this new model with higher resolution than we'd used before. So we put these together. No changes of any parameters from what the atmosphere and the ocean model had set up as their best versions of the model. We ran for 10 years, but unfortunately, the land component didn't have a river runoff scheme. So all the net precipitation minus evaporation that was occurring over land was lost to the system, wasn't going back into the ocean. So the global average salinity in the ocean was rising quickly, and so the run was stopped. And we had to decide what to do. And I sort of vividly remember an afternoon meeting when we all got together and said, what are we going to do? We thought that producing a river runoff model that none of us knew how to do would take many months, 6 at most, probably a year, and we didn't want to wait that long. So we came up with a scheme that in fact took a day to implement. We multiplied the precipitation from the atmosphere by a time-varying factor which was determined by the globally averaged evaporation divided by precipitation over the ocean and the sea ice. This meant that we increased the precipitation from the atmosphere to the ocean instead of producing river runoff. The advantage of this was that this was the simplest thing we could do to ensure conservation of water. But the trouble was that fresh water was going into the ocean, not where the rivers came out into the ocean, but it was basically in the areas of the ocean where the precipitation was highest, so basically in the intertropical convergence zone. But it did conserve water in the model. And in my view, the best way to characterize that is it should be viewed as a very poor river runoff scheme. So, in May 1996, which was the date of the first meeting in Breckenridge, where we were there in May, where what we remember most is it snowed, and there were only 2 restaurants open because all the others had closed. So we had trouble finding something to eat. But in May 96, the run was restarted, and it ran at about 2 years per day on the Cray YMP. And we stopped after 300 years, which was, I think, in October 1996, because the salinity distribution in the ocean had got really poor by then because of this factor of what we were doing. It was becoming too saline, where the Amazon should have been coming out, and not nearly saline enough under the intertropical convergence zone. But to our, I think, correctly described as a complete surprise, the surface temperature of this model adjusted in the first 10 years, but then after that, it maintained pretty much the surface temperature of the globe. In fact, if you look at these in the averages are drawn in the lines from the years 10 through 290. There is virtually no drift in that globally average surface temperature. And in fact, if you wanted to, you could pick particular years near the beginning and the end of that run where the global drift was precisely 0. The drift was something in this one we did as something like 0.02 degrees per 100 years. So this completely surprised us. Most groups, not NCAR, when they put together their models, couldn't maintain this surface temperature. And they had to use these flux adjustments, which were arbitrary fluxes of heat and fresh water between the atmosphere and the ocean in order to maintain a current day surface temperature. So this we all thought was a big deal. So there were some subsequent events that I want to describe. Byron and I were the nominal heads of this, one from the atmosphere, one from the ocean group, but really we were all in this sort of together. But Byron, Beauville, and I wrote up a short paper on this CSM1 run, and when you got a big deal, you submit it to science. It was rejected because one reviewer said we'd use salinity restoring in the run. Sea surface salinity restoring had been used in the ocean spin-up run, but not in the coupled run. In fact, when I think about it, if we'd used salinity restoring, the salinity field would have looked a lot better than it was. We probably could have run this for more hundreds of years, because if the salinity had looked better, we probably wouldn't have stopped it. But we didn't. We wrote back to the editor that the reviewer was incorrect, but he still rejected the paper. So the first paper that I ever had rejected was what I think was my most significant contribution to a real science in my career. I've only had a couple other things rejected, but this was the first, and I think it was the most significant result of my career. That expanded paper was then published in the Journal of Climate in June 1998 as the first paper in this June edition. And as you can see, it's reasonably thick, and it contained 20 papers that were all describing this CSM1 300-year run. I think because it was such a big deal, the editor, chief editor there, Dave Randall, thought it appropriate to have a whole issue on this CSM1 run. First time that I think had ever happened. There were more subsequent events. Some were subsequent after others. So, at the next annual workshop, we heard a rumor that really the CSM1 run went for 350 years and the climate had gone off the rails. So we chose to conceal this, ignored the last 50 years, and only showed up to 300 years. Thinking about it now, I think this is the first time I came up against a conspiracy theory. This, let me assure you people, was fake news. We stopped the run at year 300 because the salinity distribution had got so bad, and we did not run it beyond year 300. The next thing we found out was that Jay Fine, already mentioned as our chief sponsor, program manager at NSF, told us that the then GFDL director had written a letter to him saying that we must have cheated in some way because all climate models needed flux adjustments in order to maintain the present day climate. Now, I don't know about others, but I never saw this letter, but Jay Fine assured me that he had it, and he asked us, had we cheated? And we said, no. We put those models together with our best parameterizations for each component. We put them together, and it ran, and we didn't need flux adjustment to maintain the present day climate. Incidentally, that GFDL director, when he left GFDL, came and bought a house in this region. And UCAR immediately hired him. But he apologized to us for actually writing this letter. So that confirmed that this letter was indeed written. So, in conclusions, this run was the first long run to maintain the current temperature climate without the use of flux adjustments. I still think it was a pretty big deal. Maybe we were lucky, maybe we were good. It was due to improvements in both the atmosphere, but I think also especially the ocean component. Those two components that I talked about, KPP and eddy invection, have been used in many, many models since. In fact, when I look it up, between them, those two papers have 6,300 citations. So they've been used a lot. The next group to do something about it was the Australians. They put together a new ocean model that had those two parameterizations in their climate model, and that reduced the required flux adjustments over the Southern Ocean by a factor of 10. The flux adjustments over the Southern Ocean in their model originally were somewhere between 250 to 300 watts per square meter. That's because it had a significant improvement south of the ACC and in the Southern Ocean. They put together a new version, and when they found out what flux adjustments they needed, they were more like 25 watts per square meter. But they didn't actually, they still used flux adjustment. So the next group that used a non-flux adjustment version was in fact the Hadley Center. It was the next non-NCAR group to run without flux adjustments and maintain the present day climate, and they did that in the very late 1990s, around 1998, 1999. And then in the 2000s, most other climate modeling groups started to run models without flux adjustments and maintain the present day climate. This, I still think, was quite a big deal. So thank you for your time.
Thank you, Peter. That was fun. And I thought one of the most controversial things was that the first workshop was in May. We don't do the workshop in May. The workshop's in June. So, okay, so last up, we have Cheryl Craig, and she is going to talk to us about technology. And also, she's a software engineer, and just want an opportunity to recognize the massive contribution of all the software engineers into the CSM effort. So it's really great to hear from Cheryl about her experiences, her early days as a software engineer here at NCAR.
Well, thank you all. I have been at NCAR since since 1980. But I've not been working on CESM that long. But these are memories that I have of my early days of working at NCAR. So what I want to do is, we always talk about how supercomputers have enabled us to do our CESM model. You know, we've brought in a lot of extra physics, we've increased the resolution, all this wonderful stuff, and it's all because we've got supercomputers, right? But there's also other things that happened that if they didn't happen, we wouldn't be here today. So let's take a look at what a typical day of using the technology of the 1980s and early 90s, what that would look like for us doing our CSM work. So this would be just prior to that first NCAR or CSM workshop. So when we head into work, I don't know about you, but one of the first things I do is check my email. What's come in? But email didn't exist. Before there was email, there were memos. Okay, if you look at this, it pretty much looks like an email. You know, it's got the to and the from and the date and the subject and then what's being discussed. But it's on paper. So this is how things came to you. So, you know, if a head of a group wanted to send out an email to everybody in the group, they'd send it to the secretary or to the division director. And the secretaries, that's what the admins were called back then, they would stamp on the top of the memo the date that it was received. And then they would go to the copy machine and they'd make copies for every single person in their group. Then they'd put it in your mailbox. So you went to your mailbox, your physical mailbox, several times a day to see what memos had come in. Well, even phone calls were more complicated. NCAR had one phone number. So everybody that was being called came in on one phone line. The switchboard operators answered the phone, said, oh, you want to go to extension whatever. They would transfer the phone to your personal desk phone. But there weren't answering machines on these phones. So if you didn't answer a call, after a certain number of rings, it went back to the operators. They had a list of, here are the secretaries associated with this person. They'd send it off to one of the secretaries. She'd take a message on a piece of paper like this, leave it on your desk, and that's how you found out who called while you weren't at your desk. Okay, so now we're done reading our emails. We're done with our phone messages. It's time to work on CESM. But there's no personal computer. So instead, you submitted your code on Fortran punch cards. So at the top of the card here, it does say, let's see, here we go. You can see this is the line of code that has been punched. And you don't have to read the punches, that's what the machine does, so you could actually read the top of your card. It was one card per line of code, and it had an 80-character limit. But you didn't even get 80 characters. The first 5 characters were for labels, and labels were used extensively because we didn't have modern structures like while loops and do loops. You had go-tos, and they used a label to tell what line of code to go to. The 6th column was for continuation. So if your line of code went more than the 80 characters, column 6 had a comment or had a character in it, and that indicated to the computer this is still the same line of code. So basically, you had 66 to 74 usable characters that you could use for each line of code. So how you would do this is you'd sit at your desk, you'd write out your program, and then you would carefully punch out your punch cards. Now, every typo, once you type something and it says an S and you meant a T, that card went into the discard and you started over. So you typed it very carefully. So there was a room in the first basement in NCAR that was filled with card punch machines. And if you look here, you can see here is the deck of unpunched cards. So you could go grab some of those unpunched cards, put them in your machine, and then use that to punch the cards for your card deck. Now, a typical program was either grouped together with a rubber band, or if you had a big program, you'd put it into a box. And if you wanted to change some lines of code, you had to go to your box of cards. You'd look for, okay, that card that said, you know, the wrong thing, and you pull that card out, you'd put your new card or cards in. So card decks, you took downstairs to the first basement to where the computer room was, and you'd come back maybe in an hour or two later to see if it was done. And you were lucky to get a handful of jobs done. How many of us, when we submit a job to Rachel, we sit there and we go, is it done yet? Is it done yet? Well, back then, you actually physically walked downstairs to say, is it done yet? No, I've got to go walk back up and come back later. So code lived in your card deck. That is where it lived. Once you submitted your deck of cards and you got your output out, it didn't exist in the supercomputer anymore. So you kept track of that deck of cards. So your output was given to you in a computer printout. And this is what they looked like. This is actually a copy of one of my programs that I wrote back in 1984. I didn't want to keep the deck of cards, so I actually printed out what the program was, just to archive it. Okay, so how many boxes of punch cards would it take to store all of the atmosphere model CAM or CESM? So CAM's about 1 million lines of code. CESM is 5 million. Okay, so you would be taking 515 boxes of cards downstairs to run CAM, or almost 2,500 boxes to run CESM. Remember, you get to haul this up and down every time you run. Okay, as NCAR got wired for networking, cards were replaced with VT100 terminals. These are simply dumb boxes. They had absolutely no processing power, and they were a shared resource. So if you wanted to do some editing and you couldn't find a VT100, you went and did something else. But basically, it was a keyboard, a monitor, and a network connection. That's what it was. Okay, if you wanted to share data with somebody external, you used 7 or 9 track tapes. You got to work out, this thing is heavy, okay? Most of the time, you needed more than 1 tape. So your arms were really good for carrying tapes up and down. If you wanted to protect for reading and writing, you had these write protect rings, and I can't remember whether it's put it in or take it out. But you would put these in or take them out, depending on whether you wanted to read or write. You had these floating all over your desk drawers. So they were 6250 BPI tapes. They were the best tapes out there. They held 175 megabytes of data. They took about 6 minutes to read or write this entire tape. So the operators would take the ring off, and then your tape is inside. Now, tapes were stored down in the racks in the computer room. So if you remember that picture that Jerry had with the Cray 1 at the front with the guy standing in the middle, if you looked at the back, that whole back was this tape storage area. Okay, so let's take a look at a recent run that Cecile made. This isn't even a big run. This is just kind of a modest run. It's a 1 degree atmosphere only 20-year run. It's not even fully coupled. She used almost 125 gigabytes of data and produced 428 gigabytes of output. Okay, so let's say all we had were these tapes to run on. So she would use over 3,000 tapes. The stack of that would be almost as high as a giant sequoia. Now, it would take 324 hours just to read and write. It's almost 13 and a half days. That is not counting that the operator has to come, find that tape, put it on the rack, and then you could read it. So it would, it would have probably doubled or tripled that estimate. Okay, so your run is finally done. Now it's time to visualize your data. But of course, personal computers didn't exist, and graphic packages were in their infancy. So you used a tool like NCAR Graphics. It was known as Autograph in the early days. It was black and white, as we've seen from the plots that were shown, and it evolved to color over time. And as was already mentioned, output came onto our microfilm. So it was a string of plots. If you wanted to see that 50th plot, you had to zoom through 49. You probably overshot most of the time. You had to go back. But that's how you would find the plots you wanted. Now, microfiche was something that was a little easier to eyeball. You could at least see, well, that's the plot I want. So you can kind of zero in on where you wanted to go. And then as we got color, they came out with color slides. And they were nice because you could eyeball them. And what was really nice about them is if you wanted to save a slide, you could just pull it out and save it. And this was replaced by digital storage pretty quickly at NCAR. So there were special viewers to view microfilm and microfiche, and the library had a number of these viewers that you could use. And then, as Jerry mentioned, if you wanted to make a printout, they had thermal printer paper that would print out. But it was really kind of a bad quality, and if you left it on your desk and the sunshine came in and hit that paper, it would turn all black. So you needed to physically store all your graphical output. So the microfilm was in a box like this, the microfiche was in a paper sleeve, and then color slides were in boxes like this. So if you wanted one picture off of this to save for posterity, onto your bookshelf it went. If you wanted to tweak a graphic out of this microfilm and make one change to one plot, you get a whole nother realm, a whole nother reel to keep track of. So a side effect of all this paper, non-digital age is you needed to physically store everything. You can see this in the evolution of my office. I've got several file cabinets that are full of things. You know, this printout came from that file cabinet. Nothing from the last 10 or 20 years is stored in them because it's all stored digitally. Okay, we're at the end of the day. We've gone home. We want to check on something on the computer, but there's no internet. So you needed to use a modem. Now, a modem would tie up. How many of you recognize that sound? So a modem would tie up your phone line, your single phone line into your house. So you had to get all your kids off. You had to negotiate with your spouse that you could use the phone line, and then you could call into work. 300 baud modems were economical, but they were really, really slow. It's 300 bits per second. So 1200, 2400 were nice upgrades. Now, another thing to consider is that if you lived where it was long distance, so Longmont, which is just 10 miles down the road, was long distance to NCAR. So not only did you get to call into work, but you got to pay long distance charges to call into work. So there were two big technology advances that I think got us to where we are today. And I really think that without them, CESM as we know it would not exist. And they are the personal computer. Digitally, we can store everything on there. We don't have journal articles in file cabinets and drawers of them. We can go and we may have collections in our directories on our computers, and we can find them pretty quickly. And then the internet. We can electronically share information with colleagues all over the world. We don't need manuals on our bookshelves to look up, well, what is the Fortran definition or statement for this? And where would we have been without Zoom? I mean, we've used it for this meeting. We used it during the pandemic. It's a way that we just can share with people worldwide. And without the internet, it wouldn't have been possible. So without all the advances in technology, CESM as we know it would not exist. And while technologies improve the way we write and debug our programs, store our data and program files, display our results and work from home, there's one thing that I think still has remained the same. And that's writing code can be very frustrating at times. This cartoon from 1998, I think, is as relevant today as it was back then. So thanks for listening. I welcome any questions or comments. And as a side note, I asked ChatGPT to put together this collage. I specifically said, put in Fortran punch cards. I did it several times. It never showed up. ChatGPT doesn't know what I'm talking about.
Thank you, Cheryl. That was
Sure.
excellent, really fun. Can you go back, Kelvin, to our presentation? Okay, great. Thanks, everyone. That was a lot of fun, a lot of walk down memory lane for some of us. Right, so now we're going to go on to the new outstanding award for community service, but I just wanted to put up this as another way of sort of visualizing the time history of CSM. These are the award winners for the CSM Distinguished Achievement Award. 25 years of that, so we started doing this award in 2001, and I'm not going to read through all the names here, but it's fun to just see, you know, who is involved in the CSM activity over the years. And all these, not all these, but most of these are reflecting contributions, scientific contributions, model development contributions, or software engineering contributions. But there's nothing on here that really captures, you know, the community aspect of what we do. And so that's why we introduced this new award this year for the Outstanding Community Service Award, and it will recognize one or more people for the dedicated service or support to the CSM research community. And I'm going to try to build tension here by not announcing it, but just describing this person. You guys will get it very quickly. But this person embodies everything that the word community in CSM stands for. She works tirelessly to support the development of the coupled model, helping and shepherding the development team by managing and tracking the always growing set of simulations and analysis as required. She is passionate about enabling users of CSM and is one of the driving forces behind our CSM tutorial activities. In particular, she is one of the leads of the CSM Tutorials on the Road activity at AGU, AMS, and other venues like the WC conference in Kigali in Rwanda. She is always ready and eager to help anyone who needs help, and now she is leading our efforts to develop robust end-to-end workflows for CSM to make the lives of all CSM users easier going forward. So you guys have all figured this out. The award winner is Cecile Hane. We have this beautiful award. So I'll just say I'm proud to have Cecile as a colleague, and I cannot think of anyone more deserving of this award. So congratulations, Cecile. Okay, thank you. So now we're going to move on to the former chief scientist. So all the chief scientists, please come up and here sit at the table, and John is going to then take over this sort of roundtable discussion.
Dave's done so much already that I thought it was reasonable that he could have a break now. So he's not one of the chief scientists around the table, and he's sitting down there. And I wonder whether we ought to just thank Dave for all the work in putting this together, because this session and the whole meeting wouldn't have happened without him. I think we have some slides. So we're going to go through, these are all the chief scientists, and the one we haven't got with us today, because he's not with us anymore, is Byron. We heard a little bit about Byron in the talks, and I have one story about Byron, because I knew him when I was here the first time around, and he basically said, I work miles more, he was talking about the time cards that we had to fill out. And he said, I work more hours than this. You have to put in 80 hours for the 2 weeks that were done. And so he entered one with 160 hours and then got paid for 160 hours. And then spent a long time trying to correct that process afterwards, basically. But I also wanted to just see if Jeff had got any recollections he'd like to make of Byron as well, because you were around.
Yes.
I think you might have to hold it.
Oh. Yes, I first came to NCAR in 1978. Byron came a little later, and I can remember the day that he walked down the hall to my office and said, how would you like to learn how to run a GCM? And I learned how to, I was very reluctant to do it, but he tutored me in running the model, and we became very close colleagues. At that time, we were both working in the stratosphere, simulating the stratosphere, and worked very well together. Byron could be quite volatile at times. So we all had to accommodate that. But I think in retrospect, thinking back in the selection of Byron as the first chair of the Scientific Steering Committee, because I was a possible candidate for that at the time, it was the best choice. Because Byron not only had a tremendous expertise in science, atmospheric science in particular, atmospheric dynamics, but he had an incredible knowledge of computer science and what it took to couple two models together, and all of the expertise that was required working with software engineers and scientists. So he was a perfect choice for that and shepherded the SSC quite well. And I think we should all be thankful for Byron's tremendous contributions and efforts to this community model.
Thanks, Jeff. So now we're going to go along the line, and I think we'll see some. I'm not sure these are current pictures, but we'll and as we go around, I'll ask you to kind of introduce yourself and answer question one, which you're aware of, which is some interesting and poignant and potentially funny moments during your time as a chief scientist. And let me start by saying that actually my first ever job was at NCAR in CGD, and my first ever boss was Jeff. So I got my first job from him. So, and let me also, before I hand over to him, say happy birthday in front of everyone. He's given up his birthday to come and tell you a story. So over to Jeff.
Well, thank you, John. I was also Cecile's first boss. So, you know, there are a lot of stories I could tell, but I can't. There's the infamous conga line dance at one of the Breckenridge meetings that even a UCAR trustee was a participant in. But yeah, I thought about this a lot in terms of funny stories. What I would like to take the time to talk about is, and Dave mentioned this, you know, we're all sitting up here as chairs of the SSC, but I think many of you know, and many of you have been part of this, tremendous amount of work, tireless work by so many people over so many years to make this modeling effort a success. And it wasn't clear it was going to be a success. And here's a little story that I can tell. There was a handful of us went up to the director of NCAR at the time to propose that we do this. We take this on. We couple atmosphere, ocean, ice, land, and get a coupled model running. It would be a community effort, be open to the community. And it was Bob Serafin at the time, and Bob said, okay, write something up. And so we wrote a proposal up, a group of us, and we took it up to him and gave it to him. Little did we know that he sent that proposal out to NCAR staff, some NCAR staff, and a university community. And I didn't find this out until many years later. The responses to that, whether NCAR, the proposal, was overwhelmingly negative. The feeling within the university community and many scientists at NCAR was that we weren't up to the job, that CGD couldn't do it. And luckily, Bob decided to neglect that opinion from the community, and he told us to go ahead. And so with the help of Bob, Rick Anthes, and most importantly, Jay Fine at the time, we were able to start coupling the model and create the simulation that Peter talked about. And I know this history because many years later, the person who had held within their hands those reviews gave them to me. And I still have them. Some of them have names on them. So I don't even know what to do with those reviews, but I still have them. So that's my funny story.
Thank you. Next, I'm going to go over to Bill, who, again, I have to appreciate because he's our current CGD advisory panel chair, but also the only person that isn't actually local, that's had to come and fly in for this session. So thank you for doing that as well.
Thank you, John. And I have vivid memories of you as a postdoc, including some rather physical interventions to make sure that I continued drinking with you. Like Jeff, I'm also struggled with how to come up with anecdotes that are suitable for an audience, most of whom I have not had the pleasure of meeting just yet. And I'm not sure if I want to start off with a particularly spicy anecdote as my means of introduction. Sort of what happened in Breckenridge stays in Breckenridge, I think is our byword here. My memories of working here were that we had a lot of very strong personalities, and that the strength of those personalities was really made the job incredibly fun. I joined in 1996. I'm pretty sure I did not have a Southern accent, but I was immediately picked on as someone who came from Tennessee. Jim Hack, whom I hope is listening, and who's now resident in Tennessee, was one of the lead teasers, and one of the great pleasures in my toward the end of my stay here was when he announced he was going to Oak Ridge. I gave him a very politically incorrect cookbook called Roadkill, for supper, and I think I doubt he still has that cookbook. Likewise, we were also, some of you may have run into Paula Fisher. She's now the head of the ASP program. Paula was, at that time, our administrator and very much responsible for keeping us in line. She was the person who, I'm very sorry to say, insisted that I take down the life-size cardboard cutout of Austin Powers from the early movies involving him as a secret agent. This was an animatronic figure, so it would talk when you walked by. And I think she got rather tired of hearing Austin Powers talk in the office. She also accused me of being a princess, so you've heard it from me. And I wear the tiara proudly, but yeah, she figured me out fairly early as someone who liked to travel a lot and had a particular lust for accumulating frequent flyer miles. The last thing so I am going just strictly with humor here, Jeff. Yeah. The last thing I'll mention, Mariana Vertenstein, who was here and was the head of the Climate, the software engineering group. I learned a lot about her life history. She's Romanian, her mother is Romanian, actually survived the Holocaust, fled Romania in the early 1960s with Mariana as a very young child, and worked in Boulder for many years as a piano teacher. Actually got written up in the New York Times. And during COVID, actually, at the tender age of 93, Mariana's mother switched to entirely online instruction using Zoom, which you just heard about, which was quite amazing for someone at that life stage. Mariana and I loved movies together, and many of you may remember there was a video store on 28th called the Video Station, closed 8 years ago. And Mariana, in one particular moment, decided to tell me that there was a movie she really wanted me to watch. And it was a Romanian black comedy called The Death of Mr. Lazarescu. And I remember renting that from the video station on physical media. And my wife and I made it about 15 minutes into the movie and then subsequently turned it off. I looked up the plot this morning on Wikipedia, of course using the internet as one now does. And just the plot came back to me. It's an evening involving an elderly gentleman who it turns out has intestinal cancer and is refused service by multiple hospitals. And the movie ends, and this apparently is a moment of particularly high humor, with emergency surgery involving a brain clot. And this was Mariana's attempt to draw me into Romanian humor. And I think that did not particularly succeed. For any of you who've been tracking her career, I think she's now in Norway, right, at Cicero. I look forward to meeting her again at some point soon so we can trade new movie suggestions. So with that, let me turn the floor over to Peter Gent. Peter, you're on.
Thank you, Bill.
So my story involves that every year the chief scientist has to go to NSF and give a 2-hour presentation on what the CESM project has achieved over the last year. And this is in front of the CSM advisory board and several program managers from NSF. We don't get reviewed before we do something, but NSF reviews everything that they give money to. So we got reviewed retrospectively from every year. And as you can imagine, this is fairly high stress for the CCSM chief scientist. One of the reasons why we've all gone this color up here. Now, one of the years when I did this, I'm not sure whether it was Jay Fine, but someone had asked me to give a part of my presentation as to if we were given sort of all the money that we could think about, how would we use that money? And so I proposed something like, several new scientists, some project scientists, some more software engineers, etc. And in the end, the total cost of that increment would be $4 million a year. So this was in the morning of the first day, and we all went to lunch. When we reassembled after lunch, Jay Fine came in and said, "Peter, you've asked for $4 million, and here it is." He gave me these 4 fake things that look like dollars that say on them, $1 million. Then he said to me, "Spend that money wisely." Jay Fine was my favorite program manager, and he did an enormous amount for this project.
Over to you, Jim.
I wish some of those old records would be destroyed somehow. So Peter, I just have to say, I'm actually jealous of your gray hair. I'm not so gray, but you've retained your hair. So that's one thing. So just stepping back very briefly, I'd just like to really thank Dave and John and Elizabeth and all the people currently involved in putting this workshop together. This is a great week, as always, and this is a really fun event and a special event, and thank you. And just Jerry, for your remembrance and of Warren. People who know me know this, but maybe some of the people that I haven't had a chance to talk to very. I'm only here, and I was only at NCAR because of Warren. Warren hired me as a postdoc in 1990, and so I had the pleasure of learning a tremendous amount of Warren's deep knowledge of the climate system for 34, 35 years that I knew Warren. But even more than that, just the incredible mentor that Warren was to so many people. I learned a lot from Warren, and it's just so nice to be able to honor his memory. In terms of my time as a CSM chief scientist, I think I struggle with funny stories, sort of like has already been said. I can think of some funny stories, not funny stories that I really want to tell today necessarily, but one of the things that came to my mind, I think I'm probably unique among all the people up here in that I am willing to bet $4 million that I am the only chief scientist who has never written a single line of code for CESM. I think that's true, yeah. For the record, for my PhD, when I was a grad student at Purdue, I worked with an atmospheric general circulation model, and I wrote some code and did some stuff for my thesis, but not with CSM. And that actually brings me to the point that I want to make in terms of my role as a CSM chief scientist. As you've already heard today, you've heard names like Byron Boville, and then the three gentlemen to my right who preceded me in terms of being a chief scientist of CSM. Here I come in to this tremendously important and successful project engaging such a wide swath of the broader community, and I'm not a modeler. Okay? I'm a climate scientist. I understand atmospheric and climate dynamics and coupled variability, but I'd never actually done that, and I was fairly nervous taking on this role. It's just a matter that all of you, the entire community, everyone is so deeply dedicated to the mission of CSM. It was actually one of the best and most memorable jobs that I've ever had, having the honor of serving as chief scientist, because it's just a great community to work with, and everyone's pulling in the same direction. Everyone has the same, commitment to the mission of CSM. And so it was just a wonderful couple of years. I will say, one story that I can share that has always stuck in my mind is that while I was chief scientist, a lot of work obviously happened in developing from CCSM, the coupled, or the coupled community climate system model, into an Earth system model, CSM. A lot of that work had begun before I was actually chief scientist, but while I was chief scientist, we actually formally released version 1 of CSM. And that was a lot of fun. It was also a lot of hard work. There were some decisions to make, and et cetera, et cetera. But I remember one meeting in particular of the CSM or leadership team that I was leading that discussion that day. And at that time, Bill Large was director of CGD, and Bill came walking into the room with Francis Brotherton. And Francis has already been introduced, but if you don't know Francis, he was also a pretty strong personality. He was director of NCAR, I think, from 1973 to 1979 or 80 or so. In those days, he also served as president of UCAR at the same time. Pardon me? I think director of computing as well. Okay. But he's really, a legendary field. One of the things he's very well known for is really promoting the concept of Earth system science, the interconnected components of the Earth system, and the importance of trying to represent all of those. So here is this legendary person that comes into the room that's played all these roles at the organization, and little old me is leading this meeting about how we're going to finalize and release CSM1, and I'll just always remember that as one memory. So I think I'll just stop with that. I don't have really funny stories, but it's just a great honor to have served in this role.
Now over to Marika.
Hi, everyone. So it's such an honor to be up here with this group of people and to be at this meeting. And Dave gave us this prompt. And so I've been trying to think of something funny. And for those of you who know me well, maybe I just don't do funny. Because instead I get really emotional and I think of heartwarming things, and I don't know, that's just who I am. And it has been an incredibly important part of my career, and I am gonna get choked up because this is what I do, to be a part of this project. This project has touched so many people and so much science, and being a part of it and getting to be the chief scientist of it for several years was just an incredible honor. I don't know why this happens. I get like choked up at television commercials and stuff too. So this is just, yeah, part of what happens. Anyway, so I was trying to think of something funny. That didn't happen. Or that happened, and then I realized I couldn't share those stories either. So instead, I tried to think of something that happened during my term as chief scientist that I was particularly proud of. And so what came to mind is the CESM1 large ensemble, and I see Jen over there. And this effort involved a huge number of people, and the CESM project really enabled this to happen. We provided resources, computing resources, human resources, but it only happened because we're a community model. And it required the leadership of Jen Kay and Clara Desser and Paul Kushner, who was serving on the SSC at that time. And without that group of community leaders, it wouldn't have happened. And so I felt like my role in that was just to let those people do their thing and enable them and give them resources. And it had an enormous impact. I mean, for those of you newer to the field, this idea of doing a large ensemble of simulations, really being able to quantify internal variability was very new. And so it's had an enormous impact. It's led to multimodel efforts to do similar things. It's enabled a huge amount of science. And it's one of the things that happened during my term that I'm very proud of. So, yeah, thanks.
Hi, everyone. Oh, wait.
No, you can. You're welcome to go in. I've got you.
Well, that's good. You guys didn't find the 1990 picture. Deer in the headlight kind of picture. I still have it if you need it. A few things. I mean, this is an amazing group of people. Actually, Jeff is the reason why I started getting involved in CESM. I was doing atmospheric chemistry. So I'm actually probably the only chief scientist who was not a CGD member when I was selected. So I was doing atmospheric chemistry, but he decided that chemistry was actually super important, so we should have a chemistry climate working group. So that's how I got into this. But Jeff also told me that the way to have an interesting career is to switch topic every 10 years. And so I didn't quite do that, but since I left NCAR, I've been picking up the pace of switching jobs. So it's about the same. On average, I've got every 10 years now. Following a little bit. So my most memorable part of being the chief scientist. So I was in the development phase for CESM2, which was a major step in complexity in the type of processes that were being represented from CESM1, chemistry being one of them. And especially aerosols. And so one thing that we really tried hard was to really come up with a sequence of things. So this is where we are, this is where we need to be, and we're going to be so, and then we're going to leave to the very end the simplest thing, which was to change the emissions, because what could possibly go wrong? And sure enough, we did one change of one file, and all hell broke loose, and we had a cooling 20th century, which was clearly not observed. And so the thing that then, and clearly we're not as good as Peter as putting one version of the model that works right there. I was like, when does that happen? But for me, the big thing was like two things. One was this was like a few weeks before the CESM workshop, and so I was filled with like what should I do? This looks terrible. We're not ready. What should I do? Should I say, everything's fine? We're working on it. So that was and I decided not to. And so I came to the workshop, and because I think this is important. This is what this community is built on. You have to trust what's in there. You have to understand what's good, what's not good. You have to know what is happening. And so I was really, really honest about that. We got a fair amount of flack for that. There was an article, I don't remember in which, like Science or whatever, basically saying, what the heck are those people doing? Do they know anything about science? Blah, blah, blah. But I thought it was critical. I was more ready to take heat for that than to show that it wasn't working. And then again, we had to like, okay, how are we going to solve that? And we could have gone the let's increase the precip by a little factor so that it's okay, we can fix it in a day. And we could. There were very, very explicit discussion on putting a limiter somewhere. Things are going bad. Let's just put let's cut it off. Yeah, it's okay. It's just one line of code. But no, we decided, and then it was incredible because it was amazingly disappointing because we had been working probably about a year and a half putting this model together, and the last thing we were supposed to do was enough to break it. So we went back to drawing board and spent 6-8 months rebuilding. CESM still had interesting behaviors that we discovered with a little more testing, but still I feel that this was definitely the most critical event that I had during my tenure there, and so I'm glad Gökhan picked up the pieces and finished putting CESM2 together when I became CGD director. But so that's my piece.
And last but not least.
That's probably the day I started working at NCAR.
Yeah.
Yeah, that's the picture.
That's probably the picture, yeah. I mean, Peter Stock reminded me, I started working at NCAR in August of 1992. And even though I was hired to work on an upper ocean model, Saravana and I were talking about it yesterday, I ended up, my task was essentially putting GM, mesoscale mixing parameterization, and help with the KPP, that two items that Peter mentioned. So my life, since August 1992, has been all related to CESM, or CSM, or whatever the acronyms have been over the years. And I wanted to, I mean, again, we got the cues from Dave, but I couldn't think of anything really funny. And I have too many poignant anecdotes that I don't want to say here. But one thing that in early days, we didn't really have working groups at that time. And then we had, I don't know, quite a few of us meeting in director's conference room. Now it's the oceanography conference room. And we called them Principal Investigator Group. And that's called PIG. So we had PIG meetings. And when we had a smaller group of us meet, we called them the Piglet meetings. And I don't know how long that effort or the naming convention continued. Then it became the whatever the co-chairs meeting and all that stuff. But when we said, oh, I'm going to a Piglet meeting or a Pig meeting. So related to my sort of time as the chief scientist, I think, I mean, one of the biggest challenges that community faced, I coincided from the dates, as you can tell, with the COVID period. And I remember our conversations with Elizabeth and many others. How the heck are we going to continue the momentum, the community momentum that we mentioned here? Because we were planning for an in-person meeting in 2020 in July, or June, sorry. And then we didn't know what to do because NCAR got shut down in March, and everybody thought that it would be only for a few days, maybe a few weeks. And we know that it lasted so many years. But that has been a rather challenge, I think, for the community and for us, just to make sure that what CESM is doing continues forward. And I mean, Elizabeth spent quite a bit time, and what we tutorial, we had to switch everything to remote, and that was, I think, quite a challenge. However, just to echo what Jim said, I think it was you who said it, but it is, I mean, then you realize that how committed and how really people are come together around a particular thing. In this case, it's CESM, and you realize that not only NCAR staff members, but the community in general are really, really committed to CESM. And because of that commitment, I think, we were able to pass that COVID period, and now we are back in person, which is really great to be here. And I'm really be honored in the company of all these great people here.
Thank you for that. I was just checking how long we'd got. I didn't want to stand between food trucks and music, beer and people. But we've got a couple more questions, of which I think we could go along and just choose one of these to go along. So I wonder whether you might choose actually from questions 2 and 3 and choose which one you want to answer. So there's opportunity to share your thoughts on the future of CSM, or Earth system modelling as a whole, or what you think has been one of the most impactful CSM activities, which we're particularly interested in right now because this US government's got some funny ideas. So let me go start. We'll go in the same order again, I think. So I'll go to Jeff first, and yeah, just choose one of those two.
I'm going to answer both of them. Very quickly, the future of CSM. We're in a very difficult time right now in this country with regard to science. And I think it's extremely important that each of us take any opportunity we can to learn to communicate what you do as individuals, as scientists, in language that is understandable to as many people as possible. You know, Richard Feynman once said, if you can't explain the science that you're doing simply, you don't understand it. And I think that's true. And so each of us as scientists has a responsibility more than ever right now to communicate to as many people as possible, your neighbors, your community, the science that's being done with CESM in a language that's accessible to the person you're speaking to. And as many of you know, this was a big thing with me just before I left NCAR. I was talking a lot about how to better communicate the science that we do. And unfortunately, scientists still are struggling to learn how to communicate their science in a way that most people understand. So I think that's number one. Given the situation that we're facing as a nation right now. The second issue, what was the second issue?
Impactful, or
the impact.
Kind of combined, I think.
Well,
in your answer.
I'm going to say, you know, for me, it's the openness of this whole process. From day one, it was decided that our code would be open to the community, that we wanted the community to be involved. This was not an NCAR-centric activity. It began that way because it had to, but it very quickly through the working group structure, the purpose of the working group structure was to entrain as many of the university community as possible to be participants, not just in using the model, but in contributing to the development on the model. I think you have to realize that at that time, and I still think it's unique, but at that time, no other modeling center was doing that. No other modeling center allowed anybody to look at their code. No other modeling center was giving their code to anybody that wanted it. And the communities that were working on developing those models was very closed. And what made CSM and CESM unique, and still tremendously unique, is its openness. And I think that is truly something that needs to be continually touted to the world, that we truly are a community Earth system modeling activity.
Thank you.
Yeah, likewise, I'm going to answer both questions simultaneously. CESM has built a really phenomenal cadre of early career scientists through its history. The fact that it's been made openly available to graduate students and postdocs has allowed many, many scientists to cut their teeth on a bleeding edge tool and to learn how to do climate science. And I can speak from personal experience of being mentored by Jeff. The CESM also holds itself to a very high standard. So it's not just getting a plausible answer for what might be the right reason. The standard is getting the right answer for the right reason. And that it's very much baked into the way that CESM works. It's baked into the way that the model has been shared with the community. And I can see it as a member of the CGD advisory board, how much effort goes into continually refining the model to make sure that it is accessible to even more people and even more broadly used worldwide, several thousand installations worldwide at current count. If you were to ask me what its legacy will be 30 years from now, I think it's going to be the fact that all those early career scientists whom you've trained, either directly or indirectly through your mentorship programs, through your training directly or by just sharing the model with them, those scientists are going to go on to train their own students and their own postdocs. So this is, the CSM is like a wave that's propagating and having a bigger, the ring of impact is just continually growing with time. It's remarkable how successful it's been. So I would really applaud the institution for having thought up the idea of being brutally open and living in a glass house. That model has proven to be remarkably successful. And just think about all the people who've launched their scientific careers and gone on to do great science with CESM. And I think it's evident that the model has proven itself to be literally unique worldwide in its success as a climate model. So thank you.
I want to just point out in an early meeting when we were designing this, Suki Manabe was there, and he said, beware of building a glass house. People will feel compelled to throw rocks at it.
So, starting at the meeting last year, I was really impressed with the results that have been got from the high-resolution version, the one that used a 1/4 of a degree atmosphere and a 1/10 of a degree ocean. There's a 10-member ensemble of that, and one of them really produces the change in the surface temperatures from around the globe that quite closely resembles what actually happened over the last 25 to 30 years. I was really impressed with that, and more recently, I've been working with John Fasulo, who shows me that the sea level rise that's produced in that version most closely agrees with observations of sea level rise that have been made over the last 30 years. So I was really impressed with that one run. It's interesting that it doesn't look very much like the ensemble mean, but it does look like what the Earth has done. And when you run a 1/10th degree ocean, you don't need that lousy parameterization of what those mesoscale eddies do. Answer the third question, I think the education part has been really unique. For many years now, I've given a talk at the tutorial, and I think that introducing those tutorials has been extremely good to educate the upcoming people in how to use and run a climate model. So.
Feel sorry for everybody to the left because I don't know what you're going to say by the time we get down there, because but you'll come up with something. I have confidence. Yeah, I'm going to just reemphasize a couple of things and then maybe one or two additional thoughts. In terms of impact, I mean, for me, it is the C, right, in CESM, the community aspect of this, the openness, the transparency that Jeff spoke to. I think it's just hard to overemphasize how critical that has been. And I think it's just, you know, it's a model and it's not perfect. But when I think about the community that it is engaged, spanning these disciplines, I mean, we talk about interdisciplinary science and just thinking about the range of people here in this room. You look at the working groups, all the different working groups, the communities that convene under the names of those working groups and then all come together. It's really just staggering, the science that has been enabled by all of the work that has gone into CSM. And it's been successful because of the C, because of the community aspect. So I just want to second that. You know, I spent most of my career at NCAR, but I've spent the last 6 or 7 years at Colorado State University in an atmospheric science department, and I have graduate students now, and I have postdocs. And one of the things that I do want to take a moment to mention in terms of impact, yes, the training, Cecile, thank you for the tutorials and all of the staff that are involved in putting those tutorials together. It's not trivial by any means. That's important, learning to run the model and whatnot. But the data sets, the community data sets, right? I mean, my students have just feasted off of the large ensemble data sets, off of the Mesa Clip project, the relatively high resolution runs, which I think I agree with what Peter Gent just said. Really fascinating, interesting runs to look at. You know, the experience in analyzing climate model data and comparing to observations and whatnot that's enabled by the effort that goes into producing community data sets and then analysis tools, right? And all of that. I don't want that to get lost. It's more than just whatever, 4.5 million lines of code, right? All of that effort has been remarkable. In terms of future directions, God, that's a tough one, right? Because of everything that I just said, the importance of all the different CSM activities and supporting the broad community, you don't want to lose any of that. And that's always been a challenge, right, with CSM. There's just more and more and more, and you don't want to take anything away. I think CSM, as Everett Joseph said yesterday, it is a facility. It is a community facility. And how to keep that community facility, like Jeff says, talk about it, et cetera, et cetera. But when I think about new directions, I guess I just want to say that, you know, I'm excited by tomorrow's cross-working group sessions on how CSM can leverage machine learning. Machine learning is revolutionizing in AI, you know, many aspects of our field. And so CSM not being behind the curve on that, but engaging with that and thinking of the advantages that can bring is really important. And then as Peter was just saying, you know, high resolution in the context of like Ping Cheng's talk yesterday, 10 to 25 kilometer kind of resolution is really amazing. some of the improvements. I get it. Resolution is not a magic bullet. It's not everything. There's all this other science that needs to be done, paleoclimate applications and whatnot, but I think the high resolution aspect is really, really interesting. And then the ultra high resolution, right? Thinking about kilometer scale modeling. And there's been projects like Dave Randall talked about yesterday, Earthworks, Storm Speed, these growing efforts in developing kilometer scale resolution. And I think that that's a really promising direction, not only because of the benefits in simulated climate, but different ways the modeling system, even more communities, the modeling system can entrain as we move into the future with that kind of ultra high resolution capability where you can do weather forecasting and prediction, tropical cyclone studies, I mean, all these kind of things that you can do now, but perhaps arguably even on a firmer scientific ground moving forward by ultra high resolution. And I think about the talks by Hansi and Paula yesterday, engaging with communities like insurance and reinsurance companies and water managers and city planners and the kind of opportunities maybe that ultra high resolution might bring to CSM moving forward. And dare I say it, but even the current administration, right, with their focus on economic prosperity and national security applications, and I think there's interesting things to think of how those higher resolution versions of CSM can be brought to bear on sort of shorter time scale predictions, the Earth, what is it, Yaga? Earth prediction across timescales, Earth system prediction across timescales initiative, in the central role that a higher resolution version of the model might play. So I think that's a really exciting future direction.
Thanks. So Jim kind of stole my thunder a little bit. As you said, it's going to get harder as it moves down the table. I just want to echo what other people have said in that I think the community is what makes CESM special. And I think, the fact that we have such an engaged community is amazing. And, it improves all of our science and it helps us build better tools and all of those things. I think the science is heading towards there being new communities to engage with, much like Jim just said. That includes practitioners, that includes machine learning experts, data scientists, et cetera. I think we're doing a really good job in training some of those communities. I think the work that's being done with machine learning and building parameterizations that are machine learning based or emulators, things like that, we're definitely doing that work, and that community is, I think, being incorporated very seamlessly within the CESM umbrella and framework. Other communities are harder, I think, practitioners, local communities. I think there's efforts underway there. We saw great talks yesterday from people that are more in the practitioner space. I think we need to be really thoughtful about how we also incorporate those communities within the CESM umbrella. And learn from them in terms of what information they need in light of the extreme changes happening in the climate and how we're going to deal with those. And that's a really hard problem because all of those problems are local problems, right? Or a lot of them are local problems. We can improve resolution and provide more useful information at those scales, but how to scale that up, every community is unique. Every location is unique. And so I think it's a challenge for us. So thankfully, Dave's in charge, and I'm sure has brilliant thoughts about how to do this.
No pressure.
But, I think it's something that we should be really thoughtful about how we do that work and how we do it in a way that is possible, but also involves the right communities and, learns from the people that are being impacted by the kinds of changes we're seeing in the climate. So it's, maybe it's a challenge for us, but I also think it's critically important. So yeah, I'll just end with that.
Thank you.
All right, so indeed, being at almost the end of the line makes it a little harder. But one thing that has not been mentioned, I think, is one of the strengths of CESM is its portability. I mean, the fact that you can run CESM on so many platforms almost without trouble is an achievement that very, very, very few, if any, groups out there has actually tried. And it's a problem. I mean, it makes it really hard. It's limiting. You can only do, you can only write a code so well. It has to be working on so many platforms. But then it really enables people who want to do science, who don't have access to blah, 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 supercomputer, they can actually do science. They can actually use that. And I think that's a strength. And this is all due to the work that Mariana and all the software engineers of CESM are enabling. And I think it's a really immense bonus to the research community to have that. On the impact, one thing that since I left NCAR, I've been on the private sector side of things and seeing from a little bit closer some of the work that is being done, good and bad, on climate impact and how climate impact are being taken into consideration for decision making. And my very limited view of that is that it is critical for a group like CESM and all the scientists involved to develop the best models they can. Because in the whole process that Marika has described of generation of information, the place where fundamental science will be put is here. And if it's not done here, it's not done. Downstream, people are going to do as quickly, as cheaply as possible to get the answers that they need. And so the responsibility of this group is to make sure that whatever data are being generated, large ensemble, everything, CMIP, which I was amazed when I went to McKinsey. People were like, CMIP 6, CMIP 6, CMIP 6, CMIP 6. Everyone knew about CMIP 6. Everyone used CMIP 6. If there is no CMIP, there is no information about future climate conditions. That's just the bottom line. So I think it's really critical to have the science. Going into the future, I think it's the connection, and I see Hansi there, and she remember some of the discussion she had a few years back, again, when I was at McKinsey, and I think there was some of the most brilliant views on how to actually combine what CESM can offer, something like decadal prediction, which I think is an amazing capability, with a twist. How do you go further? How do you go to the next level? How do you build what actually is realistic, usable information that people will want? And so I think this is really trying to find and build those partnerships with people outside that can really take CESM and the impact of CESM to the next level, is to make sure that we can't do everything. But what we do, we have to do it very well, because afterwards people are going to be relying on that. So, thank you.
I'll cut it short since I was going over my list. There's nothing left here for me to say. But I just wanted to stress the community aspect as everybody else. And over the last several months, I'm more and more realizing that it's always good to go after the next shiny thing. But however, under the circumstances, I think we need to be mindful of protecting foundational and basic science. Because if we cannot protect that, the next shiny thing will not be there. So I think we need to be really sporting basic science, basic Earth system modeling science, and foundational science. And while also pursuing high, ultra-high, AI/ML, GPUification, and all those efforts at the same time, while at the same time, with perhaps reduced resources, sporting the community needs all the way from coarse resolution to ultra-high resolution. And that requires essentially a hierarchical modeling approach that each group or each section can learn from each other. Thank you.
Thank you. I guess it's just for I guess it's just for me to try and reflect on that to wrap up before we go and have some fun. So I've been in CGD just under a couple of years now, apart from the time I was in before. And the most striking thing I've come across, and you know, people ask about what's it like in the job and things like that. It's the passion of the people, the passion of the staff in CG, that's the software engineers, the scientists, and the administrative staff, about delivering quality models, science, and as has been touched by all the chief scientists, engaging with the community. And then, having been in CGD and engaged with the community, I've recognized the passion of the community and I'm wondering whether we rebrand actually, so it's PCESM. It's the passionate community system model. Maybe that will bring in some funding as well from some sponsors. But yeah, that's what's really struck me. But it's there in all the chief scientists. You know, that passion hasn't gone away. People have come through and led this, and they're still passionate about it now, and that's what's so amazing, and I really appreciate all their comments and everything. So one massive big thanks, and let's include Dave in this as well now. Some big massive thanks for the chief scientists and their passion.
Okay, so let's go celebrate. We got food and alcohol and other drinks, and we have a food truck out there. We definitely need people to go to the food truck, otherwise we're gonna like get in big trouble with the food truck company. they're gonna kneecap me or something like that probably if we don't buy enough meals. So I really need you to go out there and get that. Let's have fun. Thanks again to all you guys for coming here. It was really, really fun and really appreciate it. So see everyone. Thanks a lot.